Welcome to Data Structures and Algorithms. Optimizing data structures and algorithms is essential for building efficient and scalable back-end systems. Developing these skills, along with leveraging AI-powered tools like Microsoft Copilot, will enhance your ability to improve performance and handle complex challenges in modern application development. We will begin by introducing fundamental data structures such as arrays, linked lists, stacks, and queues, examining their characteristics, operations, and efficiency. Then we will compare their performance trade-offs and explore how they apply to common back-end challenges. Next, we will explore sorting and searching algorithms, implementing efficient techniques like quicksort and binary search to optimize data processing. We will analyze their performance trade-offs and determine the best strategies for improving search operations in back-end systems. Then you will examine tree and graph structures, understanding their role in organizing and processing data efficiently. You will implement traversal and search algorithms, assessing their impact on back-end performance and scalability. Next, you will explore advanced algorithmic techniques, including dynamic programming and greedy algorithms to solve complex back-end problems. You will apply hashing for efficient data retrieval and evaluate different approaches to optimize system performance. Finally, you will refine your ability to optimize algorithms and data structures using Microsoft Copilot, leveraging AI-generated suggestions to improve efficiency. You will implement complex algorithms, assess Copilot-assisted code, and apply optimizations to enhance scalability and performance in back-end applications. Efficient data structures and algorithms are the foundation of high-performance back-end systems, enabling scalability, responsiveness, and optimized resource management. That's a lot to cover. Let's get started. Welcome to Introduction to Data Structures. Efficient data management is essential for building scalable and reliable applications. Understanding how to structure and optimize data enables you to improve performance, streamline operations, and solve complex challenges. We will begin by introducing key linear data structures such as arrays, linked lists, stacks, and queues, and explaining how they store and manage data efficiently in different programming scenarios. Next, we will implement these data structures in a .NET Core environment, exploring how to perform essential operations like insertion, deletion, and traversal to manipulate data effectively. Then we will analyze the performance of these data structures using Big O notation, learning how to evaluate time and space complexity to optimize code and improve efficiency. After that, we will configure distributed caching in .NET Core, discovering how it enhances application performance by reducing database load and improving response times. Finally, we will apply cache expiration policies, learning how to manage data retention and optimize storage efficiency to maintain system performance and reliability. By the end of this module, you'll be equipped to make informed decisions about data structures and enhance the efficiency of your back-end system. Behind every app and website is a well-organized system for managing data. Arrays and linked lists are foundational to this organizational system, and each is uniquely suited for handling data efficiently. Knowing how they work is key to building robust applications. In this video, we will identify the features of arrays and linked lists, including memory allocation, access patterns, and when to use each structure. Let's begin by exploring the structural features of arrays and linked lists, starting with the array memory model. An array memory model defines how data in an array is represented, allocated, and accessed in the computer's memory. Think of an array like seats in a theater. Each seat is next to the one before it, so you can go directly to any seat. This setup is great for quick searches since each item has a fixed position in memory. Arrays typically store items in a memory block called a contiguous memory layout. Contiguous memory layout is a way of organizing data in computer memory where all the elements of a data structure are stored in a single, uninterrupted block of memory locations. This means each element is located next to its neighboring elements with no gaps or empty spaces. For example, imagine you have a row of 7 seats, each labeled for a day of the week: Sunday, Monday, Tuesday, and so on, all the way to Saturday. Each seat is right next to the one before it, forming a single continuous row. In an array, each piece of data, like each day of the week, sits right next to the other in memory, just like the seats. Now that we understand array memory models, let's explore how linked lists store data differently. A linked list structure is a data structure made up of individual elements called nodes. Each node contains data and a connection or pointer to the next node in the sequence. Linked lists are important because they provide flexibility in storing and managing data in memory, making them ideal for situations where data needs to be frequently added or removed. For example, imagine a line of people holding hands. Each person only knows who's next to them. To reach someone in the middle, you have to go person by person. Each node in a linked list holds 2 parts: the data itself and a pointer that specifies where to find the next item in the list. This flexible setup is useful when the number of items changes often. Next, let's explore access complexity, which is affected by how data is arranged in memory and determines how quickly you can access data in arrays and linked lists. Since arrays store items right next to each other, you can quickly access any item by its index. This efficiency is called constant time access, represented in big O notation as order of 1. This notation signifies that the time taken for the operation does not change as the amount of data increases. Constant time access means that the time it takes to access an element in the data structure remains the same, regardless of the size of the data structure. For example, imagine you have a library with bookshelves. Each book has a unique number, and you know the exact location of each book on the shelves. Whether there are 10 books or 10,000 books in the library, you can find a specific book in the same amount of time. However, in linked lists, each item points to the next, so you must move through each item to reach the one that you want. This is called linear time, or order of n, because the time increases with the list size. Linear time describes the efficiency of an algorithm where the time it takes to complete grows in direct proportion to the size of the input data. For example, imagine you're painting a fence. The time it takes depends directly on its length. If you double the length of the fence, it will take you roughly twice as long to paint it. In this video, you learned about the features of arrays and linked lists, including memory allocation, access patterns, and when to use each structure. With a deeper understanding of their structure and access patterns, you'll be prepared to make the best choice for efficiently storing and retrieving data. Behind every undo button on a web interface or online transaction is a system that organizes and streamlines actions. Stacks and queues are powerful data structures that make these everyday experiences possible. In this video, we'll explain the practical use cases of stacks and queues in software systems. To begin, let's examine some use cases for stacks and queues, but first let's define what stacks are. A stack is an abstract data type where elements follow a last in, first out, or LIFO order. In other terms, the last item added to the stack is the first one removed. Think of a stack of dinner plates. You can only add to or remove plates from the top of the stack. So the last plate laid on the stack is the first one taken the next time you need a plate. This structure is valuable when the most recent action is the one we need to access first. For example, a commonly used feature that employs a stack is the undo feature. The undo feature allows users to backtrack through recent actions in an application. A stack stores each action so that pressing undo removes the most recent one first. This can be useful, for example, in a drawing app where each brush stroke is added to a stack as you make it. Each time you select undo, the app removes your last stroke, then the one before that, and so on. Another common use case of stacks is how browsers track page history. For example, when you open a new page, it's added to the stack of pages you've visited previously. When you press back, The browser removes the last page you visited and returns to the previous page. Now that we have explored stacks and their use cases, let's examine queues and how they process items in the order they arrive. A queue is an abstract data type where the first in item is the first out item, or FIFO. It works just like a line at the ticket counter. The first in line is the first to be served. Queues are essential when tasks must be handled in the order in which they arrive, ensuring fairness and efficiency. Imagine, for example, a printer managing multiple print jobs. Each job enters a queue as it's submitted, and the printer processes them one at a time in the order in which they arrive. Using a queue ensures no job jumps the line, and each task gets handled fairly. But how do you handle tasks that don't need attention right away? That's where a task queue comes in. A task queue is a system for organizing and managing tasks that don't require immediate attention, like sending emails or processing uploads. For example, imagine a video sharing platform where users upload videos. Each uploaded video must be processed and encoded into multiple formats before being accessed. Instead of immediately processing uploaded videos, each request is added to a task queue. The system processes these tasks individually in the background. This allows the platform to handle uploads efficiently without overwhelming the system. Queues are also essential in API request management, especially in high-traffic systems. A queue helps manage incoming API requests by handling each in order so the system doesn't overload. Imagine several users trying to make a reservation in a restaurant app at once. Each request goes into a queue, and the system processes each one in turn. This prevents overload and ensures everyone's request is handled fairly. The app can efficiently process multiple requests using a queue, keeping the system balanced and responsive. In this video, you learned about the practical use cases of stacks and queues in software systems. Stacks and queues help create the smooth, intuitive interactions we rely on every day in our software. The type of data structure that you choose when trying to determine how to manipulate data in your application is going to be important in terms of how the data structure works based on the needs of your application and how performant they are for what you're trying to do. So in this screencast, we're going to look at two different data types, and we're going to demonstrate how to implement arrays and linked lists in .NET Core. We're going to look at these two types of data structures and try to illustrate how they work. I've got two methods in this console application, basic linked list method and linked list method. The first one is just an array. What we're doing in this method is filling the array, this array of strings called card deck with 4 different names of cards. And then we're going to write out to the console the card deck's name. You can see here we're using a for each loop, and we're going through each card in the card deck and then writing out what that card is. Now with an array, you can go directly to a specific card if you wanted. You can say card deck and then in brackets put the index of the card that you want. But in this case, we're just going to go through each card and write it out. So I'm going to run this to show how it works. What's interesting about this array is that we're setting all the values up front. You can actually add items to some arrays. Once the array is set, you can't add or delete items from it. In this case, we're just adding them all at once, and then we can print them out. The second type of data structure we want to look at is a linked list. And the beauty of a linked list is that you can add and remove items from that linked list as you need to. In this case, we're creating a linked list of strings, which again is just a structure of string values called sorted cards. And then you can see in the next line of code, we're doing sorted cards.addList. We're calling that method and passing in what we want to add to the sorted cards list. As we need to, we can use that add last method, and it will put items into the linked list as we need them. So when we do this, we're going to add these 4 items instead of all at once. When we instantiate the sorted card objects, we're going to do it in line here in process, and then we can print them out just like we did with the array. When we run that, we're going to get essentially the same results, different order because we're adding them in a different order, but we are able to add those items individually. Now we also can remove cards from the linked list, And I'm going to do that next. So I'm going to add another few lines of code. We're going to remove some cards. So we're going to remove the jack of clubs, which is the first item in the list. And you can see we're calling sorted cards.remove, which is that method that will essentially allow us to manipulate that linked list. And then we'll write out the cards again. So in this case, we should see two lists. I'm going to clear the screen here so we can see it a little bit more clearly. The first one will have the 4 cards, and the second one should have 3 cards. All right, so we've got the sorted card deck, 4 cards in that one. And then when we called that remove method, obviously it pulled the jack of clubs out of the linked list, and so now we've got 3. In the linked list, we're adding each item individually, and then we can pull out items individually. In the array, we're setting the entire array up front, and it doesn't give us as much flexibility to add and remove. Again, some arrays are a lot more flexible than others, depending on the language you're working in, but linked lists have these built-in methods that make adding and removing items convenient. So the type of data structure that you use will be highly dependent on your needs and what you're trying to do in your application. Arrays tend to be a little bit speedier as long as the data set's static and consistent. Linked lists tend to be a lot more flexible, so it's all dependent on what you need to do. The type of data structure that you choose for your application has a lot of importance in terms of how the data structure works and how performant it is based on the type of data that you're working with. So different contexts will demand different data types depending on what you're trying to accomplish. So in this screencast, we're going to demonstrate the creation of stacks and queues with insertion, deletion, and traversal operations. So we can see how these different data options work and the context in which they can be used. We have 2 methods. One's pop and push, and one is in queue and dequeue. So we're going to look at a stack first and how a stack operates. You can see in this code we're creating a variable called action stack, and it's just a new stack of strings. And then we call the push method on that action stack object, and we're just going to push onto the stack these 3 items. The last item in our list, the last line of code here, is writing to the console, and we're going to use the pop method on that action stack. And the pop method will essentially just take off the last item that we put into it. Think of the undo feature in an application. The undo feature undoes the last item that was performed, and that's how a stack works. You push things on, and then when you use the pop method, you pop things off of that stack. So this is a first in, last out model, FILO model. So let's go ahead and run this, and we can see how this works. We pushed on hello, and then world, and then another world. And then when we use the action stack pop, you can see it deleted the last world in the list. So now it just says hello world in that stack. We only have 2 items left in that stack. So that's a very specific type of data structure that works in very specific circumstances. Queues operate very similarly, and we're going to go to our next method here in queue and dequeue. This is a first in, first out data structure. We're going to create a queue of strings called print queue. And again, this is illustrative of a context in which this type of data structure works. So you can think of a printer queue where you're sending documents to a printer. Fairness would dictate that the first document that made it into the queue should be the first one that's printed. So first in, first out. And you can see we're in queuing, which means we're just adding to the queue these different documents. Here they're just strings, they're not actual documents. We're just writing document1.pdf to the queue, and the same with the other 2 items. And then we're going to go through this entire queue, and we're going to dequeue. So then that means we're just going to push off of the queue individual items. Notice we're not specifying which item we want to push off, because when we call that dequeue method, the queue will automatically start at the top and work to the bottom. So we can see each one being pushed out of the queue as we run the application. So let's run that application now with this new method. We have a while loop here, and it's checking to make sure the count of the queue is not 0. And each time it does that, we're going to use that printQ.dequeue method. It did them in the order in which they were added to the queue. And the same works with the stack. Every time you dequeue or pop, you remove the item from the queue or from the stack. This eventually got to 0, which is why the program ended, because every time we called that dequeue method, It essentially deleted the item from the queue. So these are just two types of data structures that you can use in your application. They both have different purposes depending what you're trying to accomplish. And you can explore these based on the needs of your application and use the one that's most appropriate. In this lab, we're going to implement arrays, linked lists, stacks, and queues with key operations in Visual Studio Code. In step one, you're setting up the project. You're going to use the .NET new console command to create a new console application where we can implement these different types of data storage structures. In step two, we're going to implement an array for calculator inputs, and that's what we have here on screen, the array method. I'm calling it here, and then we'll run them all at the end of the lab to see how they work. But this is the first one, the array, and it's essentially just a dictionary or a database of strings. So we have a string with the brackets indicating it's an array, and we have the expressions variable, and we're creating a new string array type. And then we're going to fill it with these mathematical calculations, 5 plus 3, 10 minus 2, etc. Then we write the calculator history, and it's just a for each loop. We can use this construct, string expression and expressions, so we fill expressions with each of these items. This construction here creates an exp variable pulling each item out of the expressions object that we created above, and then just writes that out to the console. It's very simple. Array is a very simple, straightforward way to store data. In step three, we're going to implement a linked list for calculation. Here's our linked list method. We create a linked list with the type of string called results. We're just instantiating a new linked list object. And then we add to the bottom of the list each time results add using results.addLast. These are just string values, result 8, result 5, etc. And we're just adding those to that linked list. And then we're going to pull off one of the items. We're going to remove a specific result, which is a really nice thing about linked lists. We can say result.remove. We'll pull out result 5, which would be the second item in our linked list. And it just goes right to that item because we gave it the specific name and then pulls that out. And then it gives us the updated calculation results. These are just strings, but it's going to go through each item in the result linked list and then print each item out to the console. In step 4, we're implementing a stack for undo history. Very similar to the previous methods, we're going to create a stack called undo stack and just instantiate that object. We're going to push onto the stack 3 items, entered 5 plus 3, entered 10 minus 2, entered 7 times 4. And then we're going to undo the last action. We're going to create the string variable last action equals undo stack.pop. So we're popping an item off of the stack using that pop command. And then we write out to the console the action that we're undoing. So you can think about an undo list here. This is where stacks really show their power. So that's the stack method. In step 5, we're going to implement a queue for pending calculation. So here, similar to the previous methods, we're going to create a queue object. This one's called calculation queue. We're just going to instantiate that object. And then we're going to use the command enqueue to add items to the queue, calculation queue.enqueue, and we add those 3 items there. And then we're going to create our next calc variable called string, and that's going to contain whatever value is the result of calculation queue.dequeue. When we dequeue an item, we'll get that result back, and it will print that item to the console next calc. Let's go ahead and run each of these. It just listed each of the items that we added to our array here in the order in which we added them. Just went through, we put them in as a single entity, and then we'd use that for each loop to run through and print them to the screen. For our linked list, we added 5 items to the list, and then we removed result 5. That's missing from our list because we didn't put the original list up. We just had the updated calculation results, and that item 5 is missing. Same here, we push items onto the stack, and then we pop off the last item. So we're undoing 7 times 4, which is the last item we pushed on. That's the first one that pops off. And in the queue, it's just the opposite. We add items to our queue using enqueue. And then when we dequeue, it starts at the top. So this is a first in, first out approach. Stacks are first in, last out. And with our queue, we enqueued all of these items into the queue. And then when we call the dequeue method, it pops that first item off, which is 15 plus 5. These are 4 different ways that you can store data and use data structures in a .NET application. As your projects grow and handle larger amounts of data, small inefficiencies in your code can cause significant slowdowns. Big O notation empowers you to measure and compare algorithm efficiency, helping you choose the best solutions to keep your applications fast and scalable. In this video, we will explain the meaning of Big O notation and how it describes the efficiency of algorithms. To begin, let's define Big O notation and explore why it's important for measuring algorithm efficiency. Big O notation is a way to measure how the time or memory required by an algorithm or operation changes as the size of the input grows. Rather than focusing on exact timing, Big O emphasizes the growth pattern, whether steady, linear, or exponential, allowing you to evaluate efficiency across different scales. Now that we have defined Big O notation, let's explore some of its concepts, starting with its simplest form, order of 1, or constant time. Order of 1 or constant time means an operation takes the same amount of time no matter the input size. Take, for example, accessing an element in an array using its index. Whether the array has 5 items or 50,000, you can go directly to the element, and the time the operation takes to run doesn't change. This consistency of time use makes order of 1 unique. Now let's explore a slightly different growth pattern with order of n, or linear time. Order of n describes operations where the time required grows directly proportional to the input size. For example, searching for a specific value in a list involves checking each item individually. If the list doubles in size, the time it takes to complete the search also doubles. This proportional relationship defines order. Next, we'll examine a more complex type of Big O notation, order of n squared, or quadratic time, which can grow very quickly. Order of n squared describes the operations where the time required grows significantly faster as the input size increases. This often happens when you have nested loops, one loop running inside of another. For example, imagine an algorithm designed to match every user in a database with every other user to identify potential connections. As the number of users grows, the algorithm's processing time increases dramatically because each user is compared with every other user. This rapid growth in computation is a characteristic of order of n squared, making such algorithms inefficient for large data sets. Now that we've explored the time complexity related to Big O notations, let's examine their space complexity. Space complexity is the amount of memory an algorithm uses as input grows. For an example, if an algorithm needs to store data in a new list as it processes each item, the memory use grows along with the input. When working with large data, managing space complexity helps prevent memory issues, especially in applications with limited memory like mobile apps. In this video, you learned about the meaning of Big O notation and how it describes algorithm efficiency. This knowledge will help you build and maintain applications that remain fast and reliable, no matter how complex or large your projects become. When working with data in an application, the data structure that you choose can have a big impact on performance depending on what your app needs to do and how large the data set is. You can use Big O notation to help measure the performance of a specific type of data construct. In this screencast, we're going to demonstrate how to apply Big O notation to analyze operations for arrays, linked lists, stacks, and queues. 4 different types of data structures. We've got 4 methods in this console application. Each method uses a different type of data structure, and we're going to use these data structures to illustrate how Big O notation works. So in the first one, demonstrate array access, this method, we just have a simple array of ints, numbers 1 through 5. And what we're going to do is go directly to the index of that array, index 2, which should produce number 3. Now this is an order of 1 big O notation because regardless of how big the array gets, we can add numbers indefinitely. No matter how big the array gets, we can always go directly to the item that we want by referencing its index. So it doesn't have to traverse the entire list to get to the item that we want. And that's what makes indexes so fast, is that you can go directly to the thing that you need. So I'm going to go ahead and run this. It's going to pick out the item in numbers at the item 2. It produced number 3, and it didn't have to go through the whole thing to get there. The second type that we're going to look at is linked lists. So let me comment out the first method, and we'll go to the second method. Now this linked list has an order of n. We create this linked list of same numbers 1 through 5. We're going to go through each item in the list and print out the number. This is an order of n because the burden on the application will increase as the data set grows. We only have 5 numbers here. If we had 100 numbers, it would take obviously much longer, much more processing time to get to, say, number 98. It would have to traverse all the nodes in that linked list to get to that single item. It's more costly, but it can have its purposes in certain contexts. Again, big O notation just helps you to be aware of that. So when we run this, we should get a list of numbers 1 through 5. It's just done that for each loop and traversed the entire list to get to that number. All right, the next one we're going to look at is a stack. And in this case, we're going to push things onto the stack and then pop things off of the stack. This has an order of 1. When we push an element on and pop it off, we're able to do that the first and the last. And so it's just operating on each of those items in the stack. So we can demonstrate that. We'll run this real quick. Push and pop, we added a 10, and then we added a 20, and then we dequeued, which we removed the first element, and then we wrote that item out that we're removing, which is the last item on the stack. In our application, we're demonstrating how big O notation can help you understand the impact of a data structure like this. And then the final one is a queue, and we'll run this program. So here again, this is an order of 1 for big O notation. Queues operate similarly to the stack, or just things go in order. And then when you dequeue, you're popping off the first. So this is first in, first out. Stacks are first in, last out. There's just a different data structure and how the methodology that we use to get data in and out of it impacts performance. So we'll go ahead and run this. Similarly, this one had the first item pop off because that was the first item in, whereas the stack had the last item as the one that popped off when we used the pop command. For the queue, we use dequeue. It does essentially the same thing, but against queues. Now you'll notice both of those are an order of operations of 1 because they both operate in a very similar way. It's just how the data structure is set up. You can use these different data structures in various contexts, and they all have their relevance. There's not one that's better than the other in the abstract, but in specific contexts, some of these data structures will work better than others. And using big O notation to be able to determine the value of these can help you as you're trying to figure out which type of data structure to use in your application. As applications grow and increase in complexity, handling data quickly and efficiently becomes a real challenge. Without the right strategies in place, data access can slow down dramatically as usage grows, impacting user experience. Distributed caching is one of the powerful tools that help applications scale to meet increased demand smoothly. In this video, we will explain the core concepts of distributed caching and its role in scaling applications. Let's begin by defining distributed caching and exploring why it's crucial in high-traffic applications. A distributed cache means that the cache stores data across several servers instead of keeping it on only one to reduce latency and provide consistent data. This setup speeds up access to frequently registered information, from multiple locations, so users get the same speed and reliability no matter where they are. For example, imagine an online store with users worldwide. By storing product data in a distributed cache across servers in various areas, the store can load pages quickly for customers everywhere. Now that we've examined distributed cache, let's review some key concepts that make it effective in handling high demand, starting with what a cache hit is. A cache hit occurs when requested data is found in the cache. This allows the application to retrieve it quickly without querying the database. For example, a customer accessing a popular product page can load that page much more quickly if the data is in the cache. When requested data is found in the cache and retrieved directly, response time is significantly reduced, improving scalability and enhancing the user experience. So if a cache hit is when the requested data is found in the cache, what do we call it when the data is not found in the cache? We call that a cache miss. A cache miss occurs when the requested data isn't in the cache, forcing the application to have to retrieve it from the database. This increases response time and puts additional load on the server. For example, if a customer searches for a unique item that hasn't been cached or visits a web page for the very first time, the application has to go back to the main database to get the information, which takes longer. By storing that data in the cache after this first request, the application is prepared for the next time it needs it. Another key concept of distributed caching is cache invalidation. Over time, data in the cache can become outdated, so cache invalidation removes or updates old cache entries to keep data accurate. This process is an important mechanism to maintain data consistency between cache and the underlying data source. For example, if product availability or prices change, cache invalidation ensures users always access the most current information. Cache invalidation is even more important in a distributed cache because it keeps data consistent across multiple servers. This ensures all users have access to the same accurate information. Now let's explore horizontal scaling, which we use to make distributed caching even more effective for large-scale applications. Horizontal scaling means adding servers to handle workload more efficiently. This approach works well with distributed caching because it helps the system handle more requests without slowing down. Horizontal scaling allows applications to keep up with growing demand and higher user numbers by simply adding more servers, each one contributing to a faster and more reliable user experience. Now that we've explored the key concepts of distributed caching, let's combine them in an example of distributed caching in action. Imagine a typical online retail store with hundreds of thousands of products in its database. During the busy holiday season, their servers are being overwhelmed by web traffic. The store can use a distributed cache to fix this issue and ensure its users can access data quickly. Cache invalidation also keeps product data accurate, while horizontal scaling allows the store to add more servers as traffic grows. This way they maintain speed and accuracy even with a larger amount of users, demonstrating the benefits of distributed caching. In this video, you learned about the core concepts of distributed caching and its role in scaling applications. Distributed caching is a key to helping applications scale. By spreading data across multiple servers, distributed caching provides fast and reliable access even as demand grows. This ensures that users always have a smooth experience. Distributed caching allows applications to handle thousands of users without slowing down and degrading the end user experience. This foundation allows systems to stay fast, responsive, and reliable even under heavy load. In this video, we will describe common tools used for distributed caching and their specific use cases. Let's begin by exploring different distributed caching tools and their use cases, starting with Redis, a caching tool designed for quick, temporary storage. Redis is a tool that stores data in a computer's random access memory, or RAM, instead of on the hard drive. This makes Redis incredibly fast and ideal for handling data that changes frequently, like user sessions. Redis is often used to store data that keeps users logged in across different pages of an application because it can handle frequently changing data. For example, every time you navigate to a new page in an application without having to log in again, Redis is likely helping in the background by keeping that session data ready for quick access. Now let's explore SQL Server caching, which is designed to handle stable, consistent data that doesn't change often. SQL Server caching is a method of storing frequently accessed data within a SQL Server database that allows applications to quickly retrieve information without repeatedly querying the main database. By caching stable data, SQL Server caching reduces the load on the main database and speeds up overall data access, resulting in a more responsive user experience. SQL Server caching is ideal for data that doesn't change often, like product catalogs or reference tables, because it integrates with SQL databases to ensure data consistency and reliability. For example, if you visit an online store and can access the same reliable product details every time you browse the catalog, SQL Server caching probably ensures those details load quickly and accurately without overloading the database. To explore how these tools work together, let's consider how a company would use Redis and SQL Server caching to provide a smooth customer experience. Imagine a company that wants to create an optimal online customer experience. The company might use Redis to manage temporary data like user sessions that keep customers logged in while they visit different parts of the application, such as their user wish list and customer service pages. Additionally, Redis could store frequently changing product catalog data like real-time stock availability or personalized recommendations. At the same time, they could use SQL Server caching to manage product details that update less frequently, like item descriptions, pricing, and specifications, as well as policy guidelines and FAQs. By using both tools, the company ensures a fast, consistent, and reliable user experience, balancing quick access to session data with reliable information about products. In this video, you learned about common tools used for distributed caching and their specific use cases. Distributed caching tools like Redis and SQL Server caching unlock applications' potential to be fast, scalable, and ready for growing demands. In this lab, we're going to implement distributed caching using Redis in a .NET Core application. I've got a console application here, and we're going to set up this application to use Redis caching. Got my dependencies installed, and I also have Redis running in the background here. This is running in Windows subsystem for Linux. I've got Redis installed in that subsystem, and then I launched it, and now it's running in the background so we can use it. The first thing we want to do is set up our main method, and we're going to set up a services collection object called services, and then we're going to use that object and set options for our Redis cache using add stack exchange Redis cache method. The configuration is going to be localhost 63779, which is what Redis listens to on a local machine. And then we're just giving it a random instance name called sample instance. We set up that service with those options, and that's setting up the Redis cache in step 1. I've got a console application here, and we're going to set up this application to use Redis caching. Got my dependencies installed, and I also have Redis running in the background here. This is running in Windows subsystem for Linux. I've got Redis installed in that subsystem, and then I launched it, and now it's running in the background so we can use it. The first thing we want to do is set up our main method, and we're going to set up a services collection object called services, and then we're going to use that object and set options for our Redis cache using add stack exchange Redis cache method. The configuration is going to be localhost 63779, which is what Redis listens to on a local machine, and then we're just giving it a random instance name called sample instance. We set up that service with those options, and that's setting up the Redis cache in step 1. In step 3, we're going to test for data consistency. Now we're going to make sure that we can handle multiple users accessing the product data at the same time. We're going to keep track of how many times a product page has been accessed by storing a counter in Redis. So here we're just writing into a new key called shared counter.
and we're going to set our cache value at get string async. So we're going to pull whatever data is in that key out. We're going to set a counter equal to the cached value if it's not null. If it is null, then we're going to set it to 0. Otherwise, we're going to increment the counter by 1. We'll always increment the counter by 1, even if we get the data from the cache. And then we're going to pass whatever data we send in. It's either going to be 0 on the first try. Subsequent, it'll be n plus 1. And then we'll set that cache counter here in this line. That's an await function. That's an async call. And then we're going to write out to the console that we updated the counter, and we're going to show the counter number for how many times that counter has been hit. So now we can keep track to ensure that we know how many times the cache has been called, and we can do something with that if we want to. Let's go ahead and run this. Down at the bottom, we didn't have anything in the cache. We're fetching the data from the database. We're essentially populating the data with those items. So that was the first call that we made. And now we have data stored in the cache, and there's 3 products. We were able to pull that out. We updated our counter. This is 7. This is because I've run this demo multiple times. Every time I've run it, it's updated that counter in the cache. That number's up to 7 because this key has been populated 7 different times. And now we can know that cache is continually being hit. Those are 2 ways that you can work with a Redis cache. And this lab just gives some simple examples of how you can implement simple calls to a Redis cache in .NET.
It would be frustratingly slow if every piece of information you accessed online had to reload from scratch each time. This can be prevented using cache expiration policies, which ensure data is available when needed to keep it accurate and up to date. In this video, we will describe the different types of cache expiration policies and their purpose in maintaining data accuracy. To begin, let's examine what a cache expiration policy is and explore some different types of policies used to manage caching. A cache expiration policy is a rule that sets how long data remains stored in the cache before being removed or refreshed. Cache expiration policies enhance efficiency by managing memory usage, preventing the cache from overloading with outdated data. Additionally, they maintain data accuracy by refreshing or invalidating cache data when necessary, ensuring users access current information. Now that we understand cache expiration policies, let's explore some of the different types of policies, starting with absolute expiration. Absolute expiration removes cache data after a set time, no matter how often it's accessed. This is useful for data that updates on a strict schedule, like daily financial reports or weather forecasts. Even if someone checks the data just before expiration, it will still be removed when the scheduled time arrives. For example, a weather app might clear cached weather data every hour. This way, users always receive fresh updates, even when they check the app multiple times. While absolute expiration follows a fixed schedule, sliding expiration keeps data fresh as long as it's actively used. Sliding expiration resets the expiration timer every time the data is accessed, keeping it current as long as it's used. Sliding expiration works well for frequently accessed data and shouldn't expire when used, like an online shopping cart. For example, consider a shopping cart on an e-commerce site. Sliding expiration can keep the cart data active by resetting the timer each time the user adds an item. As long as the cart is in use, it won't expire, making it well suited for data that depends on user activity. However, in some situations, data needs an immediate update that only manual invalidation can handle. Manual invalidation allows the system or user to clear cache data manually, especially if it's outdated. Manual invalidation gives full control over data updates, which is important for content that changes unpredictably and needs immediate accuracy, like blog posts. For example, imagine a blog where posts are often updated. When an article is edited, the cache can be manually cleared so visitors see the latest version right away. Finally, time to live, or TTL, is a policy that sets a strict limit on how long data stays in cache, regardless of access. Time to live sets a maximum time for data to stay in the cache before it's automatically removed, regardless of access. Unlike absolute expiration, which removes data at a fixed time, TTL starts counting down from when the data is cached and removes it after a set duration. TTL is helpful for temporary data that doesn't need to persist forever, like login sessions. This helps manage storage and prevents old data from accumulating. For example, website session data often has a TTL of 24 hours, meaning each session expires after one day, whether it's used or not. This helps protect user data by limiting how long a session remains valid, reducing security risks. In this video, you learned about the different types of cache expiration policies and their purpose in maintaining data accuracy. Choosing the right cache expiration policy helps ensure your data stays accurate without sacrificing performance. Choosing the right expiration policies keeps data fresh, improves performance, and conserves memory. Factors like data volatility and access patterns determine how long cache data should persist, and optimizing these policies ensures efficient, accurate, and responsive applications. In this video, we will explain how to choose appropriate expiration policies based on application needs and data patterns. To begin, let's explore the criteria for selecting the appropriate data expiration policy, starting with data volatility. Data volatility refers to the frequency and extent of changes in data over time. Highly volatile data like stock prices or real-time sensor readings change rapidly and unpredictably, while low volatility data like archived records or historical reports remain stable for longer periods. Data that changes frequently needs to expire quickly to stay relevant. For example, a shorter expiration time is essential on news websites where articles update throughout the day. This way, users always receive the latest updates with minimal delay. Now that we have explored data volatility, let's examine access patterns and their influence on data expiration policies. Access patterns refer to how often data is accessed by users. Access patterns help dictate what expiration policies should be used in different scenarios. For example, if we expect users to access the data on our site relatively frequently, we might choose to implement a sliding expiration policy that keeps data cached as long as users continue to interact with it. Imagine a popular social media post that thousands of users view daily. Its sliding expiration keeps it readily available and loads it faster each time it's viewed, avoiding frequent cache resets. Now that we have explored access patterns, let's examine how memory constraints affect expiration policies. Memory constraints are the limitations on storage capacity that influence how long data is retained before being automatically deleted or archived. Like access patterns, these limits help us implement the most appropriate expiration policy for any scenario. For example, to avoid cache overload in systems with limited memory, we might choose an absolute expiration policy that clears data at regular intervals. Consider data such as news articles about an event that is happening at a specific date and time. Setting an absolute expiration for after the event happens will remove the data when it's no longer relevant, making room for newer data. Finally, let's explore how consistency requirements influence data expiration policies. Consistency requirements refer to the degree to which data needs to be kept accurate and consistent across an application. Consistency might be maintained when data is deleted or archived to prevent issues like stale references or discrepancies between different parts of a database. Expiration policies must define how expired data is removed without disrupting workflows, ensuring dependent data remains intact and system integrity is preserved. For example, imagine an e-commerce checkout process where inventory and pricing data must remain precise and up to date consistently. By using manual invalidation, the system can ensure that customers always receive the current stock and prices, preventing any discrepancies during checkout. In this video, you learned how to choose appropriate expiration policies based on application needs and data patterns. Choosing the right expiration policies ensures that data is fresh, memory efficient, and accurate, helping you deliver smooth, reliable user experiences.
In this lab, we're going to implement cache expiration policies using Redis in a .NET Core application. I've got a simple .NET Core console application here. I've also got Redis running in the background. I'm in Windows Subsystem for Linux, and I've installed Redis in this Linux instance. This is running in the background for us. The first thing we have to do is install the dependencies. So we're installing the caching distributed dependency and the extensions dependency injection. With those libraries, we can now use Redis in our application. In our main program, the first thing we're doing is setting up our main method. It's an async task method so that we can use async method calls when we're working with our cache. Then we set up our services collection. We create an object called services that's using the services collection library. And then here's where we're using the services, the add stack exchange Redis cache options. So we set the configuration to localhost 6379, and then we just set an instance name. That can be anything. Cache example is the name we're using. Redis does typically listen on port 6379, so that's fairly consistent. Obviously, we're here on a local machine, so this is all localhost, but on localhost, it will listen on that port number, and then we can set our instance name to whatever we want. Then we set up our provider services, our build services provider, and our cache uses that provider object and uses the get required services iDistributed cache to interact with the cache once that's set up. In step 2, we're going to apply absolute and sliding expiration for our cache. Now we're using the distributed cache entry options where we can set our absolute expiration, which is the current time plus 10 minutes. What that means is regardless of what's in the cache, after 10 minutes, it will expire and refresh. The next call to the cache after 10 minutes will refresh. We also are setting a sliding expiration. If the cache is hit and data is drawn from it, within 2 minutes, it will reset. So that expiration will continue to reset up to 2 minutes. If someone hits the cache and then at 2 minutes and 1 second, no one hits it, it will expire. Otherwise, it'll refresh every 2 minutes and keep whatever's in the cache in there until it hits 10 minutes, and then it will expire using that absolute expiration. Here we're doing the from minutes is 10, and the from minutes for the sliding is 2. The absolute has to be greater than the sliding, otherwise the sliding expiration will never be hit. Then we set a string for our cache, which is a sample task with a key of task key. And our entry options, we pass that into that method, set string async, and then we write out to the console that work has been done. And then in step 3, we're going to implement manual invalidation. These lines of code, 24 and 25, will invalidate the cache automatically, but we also will give ourselves an option to invalidate it manually. Here we're setting our task key and sample task along with our cache entry options again. We're setting that string async. In this third step, we've created this invalidate cache method. We pass in the cache and we pass in the cache key so we know what key we're working with. This method will essentially remove the cache item using that key value. So whatever is at that key in the cache will get removed, and we'll write out to the console that's been done. To trigger the invalidation, we're going to read from the console. So you can tap the spacebar or press any key on the keyboard, and then that will call invalidate cache using that await invalidate cache method. And it'll pass in the cache and pass in the task key as the key, and then it will invalidate the cache. So let's go ahead and run this. Our Redis cache is set up and it's complete. We have a cache entry set with absolute and sliding expiration. So now there's an item in the cache called sample task. And now to invalidate that and remove it from the cache, we can just press enter, and that item at the task key has been invalidated, which means it's no longer in the cache. And that's setting up Redis cache in a .NET application for this lab. Choosing the right data structures plays a critical role in building efficient and scalable applications. Each structure offers distinct advantages that influence performance, memory management, and data organization.
Gaining a deep understanding of their implementation, analysis, and optimization helps ensure that your back-end systems operate smoothly and handle data effectively. We began by exploring fundamental linear data structures, arrays, linked lists, and stacks and queues, examining how they are organized and manage data to support efficient processing in various applications. Then we worked with a .NET Core environment to build and apply these data structures, focusing on performing essential operations like inserting, deleting, and traversing data to ensure efficient handling and manipulation. Next, we examine how these data structures perform under different conditions, using Big O notation to assess their time and space complexity and identify opportunities for optimization. After that, we set up distributed caching in .NET Core, exploring how it minimizes database strain and accelerates application response times for improved performance. Finally, we implemented cache expiration strategies to control data retention, optimize storage usage, and ensure consistent system performance and reliability. Understanding how to implement and optimize data structures is crucial for building high-performance applications. Applying these concepts effectively will improve system efficiency, enhance data management, and support scalable back-end development. Welcome to Sorting and Searching Algorithms. Efficient data processing is critical for back-end development, and selecting the right algorithm can significantly impact performance. In this module, you'll explore fundamental sorting and searching techniques, learning how to optimize data retrieval and organization for scalable systems. We will begin by exploring fundamental sorting algorithms such as bubble sort, quick sort, and merge sort, understanding how they organize data and their role in efficient processing. Next, we will implement these sorting algorithms in a .NET Core environment, analyzing their performance to determine how time and space complexity impact real-world applications. Then we will examine searching algorithms, learning how different approaches help retrieve data efficiently from various data structures. After that, we will optimize search operations by applying binary search, leveraging its speed and efficiency when working with sorted data sets in back-end systems. Finally, we will compare sorting algorithms, evaluating their strengths, limitations, and best use cases to make informed decisions when designing high-performance back-end solutions. By the end of this module, you'll have the skills to implement, analyze, and optimize sorting and searching algorithms, ensuring efficient data processing in back-end systems. Let's get started with the fundamentals of algorithm efficiency. Sorting is used everywhere, from organizing files on your computer to ordering items for quick access in apps. Understanding how sorting algorithms work is key to building efficient systems that process data smoothly. In this video, we will describe the mechanics of bubble sort and the scenarios where it is a suitable choice. To begin, let's define bubble sort and explore some of its key concepts. Bubble sort is a sorting algorithm that repeatedly steps through a list, compares adjacent elements, and swaps them if they're in the wrong order. This process repeats until the entire list is sorted. This algorithm is called bubble sort because based on the defined sorting order, the largest or smallest element bubbles up to its correct position at the end of the list with each pass. Now that we've explored what bubble sorting is, let's examine how the bubble sorting process works. Bubble sort works by comparing and swapping elements in a list until the entire list is sorted. For example, if we start with the simple list 5, 3, 8 and need it to be in ascending numeric order with the largest numbers building to the right, the bubble sort algorithm first compares 5 and 3 to determine which is numerically larger, swapping them to get 3, 5, 8. It then compares 5 and 8, leaving them where they are since they're already in ascending order. This process would repeat for larger lists until no more swaps are needed, and the list is fully sorted based on the defined order. Since the bubble sort process has many steps for each reorder, it's ideal for small data sets where simplicity matters more than speed. For example, it's great for sorting a short list of scores or names for a class project or attendance roll. However, it's not the fastest for large lists like complex financial ledgers or large data sets. Now that we've explored bubble sort's process and ideal use cases, let's examine the time and space complexity for using bubble sort. Remember that time complexity is how long it takes to sort a list as it grows, and space complexity is the amount of extra memory required by an algorithm to execute relative to the size of the input. First, bubble sort has a quadratic time complexity of order of n squared, meaning that as a list grows, sorting takes significantly longer with each added value. This makes bubble sort a suitable choice for smaller lists, but impractical for larger datasets. Bubble sort also has a space complexity of order of 1, meaning it requires a constant amount of memory regardless of the size of the input. This makes bubble sort a memory-efficient algorithm that is useful for systems with limited memory. In this video, you learned about the mechanics of bubble sorting and the scenarios where it's a suitable choice. Bubble sort may not be the fastest algorithm for large datasets, but its simplicity and low memory usage makes it a valuable tool in certain scenarios. Efficient sorting is essential for handling large datasets. Choosing the right sorting method can mean the difference between smoothly managing data and facing frustrating delays. In this video, we'll explain how quicksort and merge sort operate, focusing on use cases and performance characteristics. To begin, let's explore quicksort and how it efficiently organizes data using a special technique called pivoting. Quicksort is a divide and conquer algorithm that splits a list around a pivot element to quickly organize data. Quicksort is great for small or medium-sized datasets where high performance is needed, like sorting product lists for faster customer browsing. Now that we've examined quicksort, let's explore some of its mechanics, starting with selecting a pivot and partitioning. First, quicksort selects a pivot to divide a list, making it easier to organize. This pivot acts as a reference point to split a list, with elements smaller than the pivot on one side and larger elements on the other. Choosing a good pivot creates balanced sections, helping quicksorts run faster. For example, imagine we have a list of product prices, 83517. If 5 is chosen as the pivot, the list splits into 31 and 87 around the pivot. This helps organize data into manageable sections with lower values on one side and higher values on the other. Quicksort also uses recursive sorting for each section to sort a list more efficiently. Recursive sorting is a method that repeatedly divides a list into smaller parts and sorts each list part until the entire list is ordered. Quicksort follows this approach, ensuring that each section is processed independently before combining the sections into a fully sorted list. In our example, after dividing the list around 5, quicksort continues portioning each section. For 3.1, it selects a new pivot to sort these values and does the same with 8.7. This step in the process is what is known as recursive sorting. Eventually, we get a fully sorted list from the smallest to largest, 1, 3, 5, 7, and 8. Now that we've explored quicksort's process, let's examine merge sort to understand how it organizes data by dividing and merging. Merge sort uses a divide and conquer approach as well by splitting the list into halves, sorting each half, and then merging them back together. Merge sort is ideal for large datasets or situations where the order of equal items must stay the same. A good example could be sorting customer orders by date to differentiate newer orders from older ones. Now that we've examined what merge sort is, let's explore its mechanics. Merge sort starts by using splitting. For example, imagine you have a list of customer orders to organize, 64719. Merge sort will start by dividing the list into two halves like 647 and 19. Then split each half into individual items. This helps ensure that each of the resulting smaller parts is easier to sort independently. After splitting, merge sort starts merging the smaller parts back together. At each merge step, it compares elements and arranges them in order. In this case, merge sort compares and combines smaller lists in order. 6 and 4 become 4, 6, and then 4, 6 merges with 7 to form 4, 6, 7, while 1 and 9 merge into 1 and 9. Now, merge sort combines the sorted sublist into a fully ordered list. It compares elements at each step, ensuring that they are placed correctly, just like fitting puzzle pieces together. Merge sort compares elements sequentially, placing 1 first, then 4, followed by 6, then 7, and finally adding the remaining 9, resulting in the sorted list 1, 4, 6, 7, 9. By dividing and merging, merge sort keeps data orderly even for large lists. Now that we've examined quicksort and merge sort, let's explore their time and space complexity, starting with their time complexity. Quicksort usually takes order of n log n time complexity, which means it can be very efficient. However, with less than optimal pivot choices, it can take longer, up to order of n squared. Merge sort always takes order of n log n time complexity because it consistently divides the list evenly every time. This reliable time complexity makes it a good choice for larger lists. Finally, let's explore space complexity. Quicksort requires order of log n extra space, making it more space efficient than merge sort. This is because quicksort reorders elements within the same array rather than creating additional copies. Since it doesn't require extra storage for merging, quicksort is a good choice when memory is limited. Merge sort in comparison requires order of n extra space, making it more memory intensive. This is because it creates temporary arrays at each step to store and merge sorted sublists. While merge sort's time complexity makes it well suited for large lists, its order of n space complexity can be a drawback for very large data sets where memory is limited. In this video, you learned how quicksort and merge sort operate, with a focus on use cases and performance characteristics. Knowing how sorting algorithms operate gives you the power to organize large amounts of data effectively and make optimal choices. When attempting to arrange data in a set, whether it's an array or other types of sets of data, you can use a variety of different algorithms. There's the quicksort or the merge sort. In this case, we're going to look at bubble sort, which is a very specific way of arranging data. Each of the types of algorithms that I mentioned have different time and space complexities associated with them. So we're going to look at bubble sort particularly and compare it with merge sort and quicksort in terms of its time complexity. So in this screencast, we're going to implement bubble sort in a .NET Core console application and analyze its time complexity. I have a simple console app here, and I've got 3 different methods that we're going to call. Quicksort and merge sort just for comparison purposes. And we're going to focus on this bubble sort method, which will take this array of numbers. There's 8 numbers in this array, and we'll sort through them. The first thing we're going to do in this is clone our initial array because we're going to use it in the other 2 methods. And so if we didn't clone it, it would operate against the original numbers array, and they would already be arranged by the time I got to these other 2 methods. So we're going to clone it first, create a copy of it essentially, and then we're going to use our bubble sort method to sort that array from lowest to highest. So you can see the bubble sort's fairly simple. It's just 2 for loops and then an if statement in the middle. And you can see in terms of space complexity, it's not creating a copy of the array in the algorithm itself. Even though we cloned it above, that was just for the purposes of demonstration, but the method itself doesn't clone the array. It's just moving things around within the array itself. So from a space complexity, it uses fairly low space requirements because it's not creating any duplicates. But from a time complexity, you can see it has to run through these 2 for loops and then do this evaluation multiple times in order to get the array to be sorted in the way that we want to sort it. What we're going to do here, and there's no recursiveness in this either, right? It just calls it once and then runs through this. I'm going to place a breakpoint here in the middle of this bubble sort, and I'm going to run this. We can ignore the stopwatch for now. Because we have the breakpoint, the stopwatch is going to be longer than it normally would be if we were running at full speed. And actually, I'm going to put it at this if statement, and it'll be a little bit easier to see. But for now, we'll just look at how the bubble sort works. So I'll go ahead and start the debugger. Now it stopped at our if statement. I have a watch on the ARR variable, which is essentially the array that we're passing in to our bubble sort. And remember, that's just a copy, a clone of the original
array that we created up here. So it should be in the same order. And you can see it starts at 5, ends at 6, just like the original one. And it's going through that process now of arranging it. Because we have a watch on the variable, we can watch the numbers move around as we step through the array. It's comparing two variables at a time inside the array itself and just moving them up and down based on whether the one is higher than the other. So it goes through each of these, and now we have a different order because it moves some of them up. Now I'm going to go ahead and continue this instead of stepping through each line of code, and we'll stop at each if statement and watch how it rearranges the variables. It's moving that 1 up, 6 is now higher. Now 1's at the third position in the array. So we've got 2, 3, 1, 4, 5, 6, 7, 8. So 4 through 8 are already arranged. And now we'll just work on those last couple of numbers. And now we've got 1, 2, 3, 4, 5, 6, 7, 8. Using those 2 for loops and the if statement, it was able to go through and arrange all of those numbers using that bubble sort, bubbling them up. And we could watch the 1 kind of move up the array chain as we went through those if statements. Now we're going to look at the time complexity by running all 3 of the algorithms, the merge sort, the bubble sort, and the quick sort, and see what they look like from a time complexity perspective. I'm going to go ahead and run this in the terminal. And the output shows no difference. Bubble sort time is 0 milliseconds, quick sort time is 0 milliseconds, and merge sort time is 0 milliseconds. Now the reason for that is because the array is so small. We only have 8 numbers, and it takes no time at all to run a sort in all 3 of these for that small of an array. So what I'm going to do is create a much larger array to illustrate the difference. I'm going to use a randomizer and then create a range of elements. And let's just start with 10,000. So we're going to have 10,000 numbers that each of these sort algorithms are going to have to arrange. And we should see a difference in time. All right, so I'll go ahead and run this. All right, now we see quite a bit of a difference. So the bubble sort time took 127 milliseconds. Quick sort took 1 millisecond, and merge sort took 1 millisecond. So we don't see very much difference between quick sort and merge sort. We do see that time complexity now showing up in bubble sort when we increase the number. If we increase it to 50,000, we can see more of a dramatic difference. Now it's taking a while for that bubble sort to complete. It looked like it wasn't doing anything, but it was actually running in the background. Now we see our bubble sort time really jump up at 50,000 items in our array. So that one took a little over 4,000 milliseconds, the quick sort being the fastest at 5 milliseconds, and the merge sort a close second at 8 milliseconds. So we can see how as we add items to our array, we can see that time complexity really start to jump for bubble sorts. So bubble sorts are really good for small sets of data. They use almost no additional memory other than the original size of the data. But in terms of their time complexity, they are really impacted by the more items we add to our data set. Using a bubble sort is excellent in very specific circumstances, but you also want to be careful not to overuse them, particularly in situations where there's a lot of data. When working with sets of data, you can organize it using a quick sort or a merge sort, but each has a different space and time complexity. In this screencast, we're going to implement quick sort and merge sort algorithms in .NET Core and analyze their performance. I've got a simple console app here, and we're going to call 2 methods, quick sort to do the quick sorting of that array at the top, and merge sort so we can merge sort the same array. Our array is just an integer, an array of numbers, and we have numbers 1 through 8 for this first example. When we run this, we'll see the 2 methods run. The time difference is non-existent. They're both 0 milliseconds to run because the array is so small. It starts out with the original array, and then it will sort them. When we pass in the array, we're going to actually clone it before we use it in our method. And the purpose for that is that we're using it in both the merge sort and the quick sort. If we arrange the array in the quick sort, it would be already arranged by the time we get to the merge sort. So we're cloning it, and we're going to use this new quick sort array, which is essentially identical at the beginning to the original array that we created. And then we're going to call quick sort. We're going to pass in the copied array, 0 for the starting point, and then quick sort array dot length -1 as the endpoint for our array. This is a zero-based approach. Now we get to quicksort. We're working through quicksort as a recursive operation to arrange the data in that array. We do this check if low is less than high, and then we jump into this partition operation, which actually does the arranging. But notice that it's operating off of the array that we passed in, which is the copy of our original array. It's not creating a new version of that array or versions of it. It's not taking up more memory by creating various versions of that array. It's just operating on the array itself and moving the numbers around as needed in that array. It's also recursive because it's calling itself multiple times here. It's calling quicksort, which is the method that it's calling it from. So it is a recursive operation. Now I'm going to set my breakpoint here and run this in the debugger to show you how the quicksort works in real time. We've got our original array. I set a watch on the array variable. This is just this variable that we passed in. This is the original order, 5, 3, 8, 4, 2, 7, 1, 6. And I'm going to step into this for just the first pass. So it goes into the partition and it's going to be operating against all of those numbers, checking out the indexes for each item in the array and moving things around. I'll click the continue button on this operation. The numbers flash here. When they flash, that means they're getting moved around by the operation. Now we have 5, 3, 4, 2, 1, 6, 8, 7. 1 jumped to the top because the partition method is rearranging those numbers within the array itself. It's actually operating that way. We'll keep running it. And now we've got 1, 2, 4, 3, 5, 6, 8, 7. We're closer to the order that we're looking for. Now we've got 1, 2, 3, 4, 5, 6, 8, 7. So we've got one more to go. It's going to operate on that second half of that array. And now we've got 1, 2, 3, 4, 5, 6, 7, 8. By using that recursive approach with low memory usage, the quicksort was able to get through all of that data. Merge sort operates similarly. It's recursive, but we're going to do the merge at the end because it's going to divide up the array in a very specific way first. And then we run that merge operation at the end, which is where the things get rearranged. We're creating two new variables, left R and right R. And these are actually copies of parts of that original array. It's not going to matter because we only have 8 items in our array, but if we have a large amount of data, this would have a space complexity that's significantly larger than the quicksort because it is creating copies of portions of that original array, which does take up memory space. So in a small operation like this, it's not going to matter, but as data grows, we're going to see that space complexity go up. And we'll look at the time complexity when we do a more complicated set of integers. So I'm going to place my breakpoint at the end of the operation because of the way that the merge sort works. And then I'll run the debugger again. Now we have our merge sort at the breakpoint. We have 3, 5, 8, 4, 2, 7, 1, 6. And I'm going to continue to play it just like I did in the quicksort. All right, we've got 1, 2, 3, 4, 5, 6, 7, 8. And so the merge sort did its job, and it did it in a similar way to the quicksort, except that it's merging the data based on the two halves that it found rather than going through and arranging the array itself. We're going to do one more thing to illustrate the impact of the performance between these two. I'm going to create a random array of numbers between 1 and 100,000. And we're going to be able to see the time difference here. These quicksort time says 4,500 milliseconds and merge sort was 41,000 milliseconds. And that's only because I had put the breakpoint into the program. I'm going to remove my breakpoint, and then we're going to just let this run at full speed. The quicksort for 100,000 items in our array took 13 milliseconds to run. The merge sort took 16 milliseconds to run. If we had another 0 here and then run it again, I'm actually going to turn off the original array because there's too many numbers to show. And we run it again. So now we've got quicksort took 132 milliseconds for 1 million items in our array, and merge sort took 182. Now it's not very much different in terms of the time, but when you think of the space complexity, merge sort does take significantly more space. So that's something to keep in mind when you're evaluating the needs for what you need to sort. In this lab, we're going to implement, test, and analyze bubble sort, quick sort, and merge sort in a .NET Core application. In step one, we're just setting up the .NET Core console application. We can use these commands.NET new console, and we tell it that it's a new app. Sorting algorithms app is the name. And then we're going to switch to that folder so we can actually work with that app. I've already got the app created and implemented, so we're not going to run that command, but that's step one, is just getting that application ready to go. In step two, we're going to implement the bubble sort algorithm. The first thing we're doing here is creating a method called bubble sort. It's going to be a static void method, not returning anything. And then it uses this nested for loops to work through the array that we pass in to do the sorting. It uses this if statement to evaluate each of the items in the array. We'll go through this entire process, each of the nested for loops evaluating the array length and essentially bubbling up the numbers that we pass in the order that it needs to be, and then it will complete. We want to make sure that we're always working with our array, and we set our array J because that's the iterator that we're working with here. So we set ARRJ to make sure that we're getting that specific item in the array as we're doing our sort. In step three, we're going to implement the quick sort, which is next in the list here. We create our quick sort method, also a static void. We're going to call it quick sort just to keep it clear. And then we implement our quick sort algorithm. So you can say we have a low and a high, and we have a pivot that we're going to create. We use another method called partition to create that pivot. We're not going to go into the details of the partition method, but this is important for making sure we're getting the right partition in our quick sort. We make the quick sort method call within the method call. Essentially, it's a recursive type of algorithm. As we change the values of the pivot, then we recall quick sort and we run through the algorithm again and again until low is not less than high. And then when that condition is no longer met, then the quick sort method will exit and the sorting will be complete. That's how to implement the quick sort. We need both this recursive approach and we need to make sure we have that partition implemented as well. In step four, we're going to implement merge sort. We're going to go down here to merge sort. Merge sort and quick sort are similar in some ways. You can see we're working with left and right and a mid in the merge sort. First, we create a method, and then we compare if left is less than right. Then we're going to go into the body of our if statement. And then we're going to do this recursive call again. So we call merge sort itself, passing in the array and left and middle. And then we call it again, passing in the array. We pass in mid plus 1 so we can constantly increment along with the right. And then we're also calling another method called merge, which will bring these items together. That we're not going to go into this specific method, but this merge method is important so that we can make sure we're getting the final array in the order that we need it. But this is the basic body of the merge sort. We just call it recursively, and then we call that merge. It's structured similarly to the quick sort, except the quick sort, we're doing the partitioning first, and then we're recursively calling quick sort. Here we're doing the merge sort first and then merging at the end. Those are our three algorithms, and that's how you implement these algorithms in a .NET application. I have a main method here that I'm using to test as well, so you can create a stopwatch and test the values of each of these. We can quickly run this. This one's going to process 150,000 numbers. The quick sort took 17 milliseconds. The merge sort took 26 milliseconds, and the bubble sort hasn't completed yet because it takes the longest. The array sort is a .NET native sorting algorithm, and that is actually the quickest because it's highly optimized for this type of data, and that took 8 milliseconds. We'll give it one more second to let the bubble sort complete, and there's our bubble sort at 41,000 milliseconds, definitely the slowest. For this large number of records, 150,000 numbers, bubble sort is not the option to use if you need a number sorted quickly, but it does show the relative differences between each of these as you're running through them.
Searching for information efficiently is a crucial part of working with data. Whether you're searching for a specific product in an inventory list or a name in a contact book, your search method can impact speed and performance. Linear search is a simple yet effective approach for finding data in a list. In this video, we will explain how linear search works and identify situations where it's suitable. Let's begin by defining what linear search is and exploring how it works. Linear search is a search method that goes through each item in a list in order until it finds the target value. Imagine you have a list of eco-friendly products like reusable bags, compostable cutlery, and bamboo toothbrushes. Using linear search, you start at the top of the list and check each item until you find what you're searching for. This step-by-step process of checking each item individually is the essence of linear search. Now that we understand what linear search is, there's some things to consider when using it. Let's start by exploring when it's appropriate to use linear search with a common use case. A use case where linear search works well is for smaller unsorted lists like our eco-friendly product list where sorting isn't necessary. If you only have a small number of products and want to quickly find one without spending extra time organizing or sorting the list, linear search makes it easy to locate what you need. Another consideration when using linear search is its time complexity. Time complexity is a measure of the computational time it takes an algorithm to complete based on the size of its input. Time complexity quantifies how the execution time increases as the input grows, typically expressed using big O notation. Linear search has a time complexity of order of n, meaning that in the worst case, each item in the list might need to be checked once. For example, bamboo toothbrush is the last item in a list of products. With linear search, you'd need to check each item until you reach the end, so finding it would take longer as the list grows. This is why linear search is ideal for small lists, where search time can be kept relatively low. Now that we understand the time complexity of linear search, let's explore its space complexity. Linear search has a space complexity of order of 1, meaning that it uses a constant amount of extra memory regardless of the size of the input array. Think about searching our product list. Linear search simply checks each item in the list without creating new data, which keeps memory usage low. Again, this makes it a good choice for smaller lists where memory efficiency is a priority. In this video, you learned how linear search works and identified situations where it's suitable. Linear search may be simple, but it's powerful for situations where simplicity and speed are essential to finding what you need. You will continue to build on this knowledge as you learn about more complex types of searches. Linear search is great for small data sets that are ordered and have a very specific structure. In this screencast, we're going to explain how linear search works and identify situations where it's most suitable. So I have a very simple console application here, and in this application, I'm setting up an array of integers called numbers 10 through 50, and I'm also setting up a target. This is what we want to search for when we do our linear search. And then I have a search function, which I'll call in a moment. But by the way, we're passing in the numbers array and the target we're looking for. If the result of that function call is not -1, then we're going to write out where the element was found. And if it is -1, then we're going to say the element wasn't found. So the search algorithm didn't find what we were looking for. Very simple app. Now let's look at this search.linear search. So we've got a search class and a linear search method. And in that method, we're passing in our array and the target that we're looking for. It's a very simple operation. All we're doing here is starting at the beginning of the array and going to the end of the array and doing a comparison. So the for will go through each item in that array, and then the if statement is going to compare the item at the position in the array. So as the for loop runs through, I is going to be increased by 1 each time. That's what I plus means. So we'll have the array at position 0, does that equal the target? Array at position 1, does that equal the target, etc. If it finds it, then it returns the position number. So let's say it finds the thing we're looking for at position 5. It'll return 5 in I. That's essentially how a linear search works. Starts at the beginning and moves towards the end. In this case, we have our target as 30.
It's in position 3 in the array, but it's going to most likely return 2 because it's a zero-based situation. So it starts at 0, 1, 2. So this would be 0, this would be 1, and this would be 2. Okay, so let's go ahead and run this and see if we get the result we expect. And it says element found at index 2. So that operated exactly as we figured it would. It goes through each item in that array until it finds the item we need. Now let's put an item in here that is not in the array. Well, this is our target now, and it should tell us that item was not found. So the element wasn't found. Linear searches are very straightforward. They are a beginning to end type of search, and these can be very useful, particularly for small data sets that have a very structured setup, and there's not a lot of variability to them. This can work very well.
Finding the right information quickly can distinguish between a seamless user experience and a frustrating one. Binary search is a powerful tool for finding specific data faster and more efficiently, especially as datasets grow. In this video, we will explain how binary search works and identify scenarios where it outperforms linear search. Let's begin by defining binary search and exploring some of its key concepts. Binary search is an algorithm that repeatedly divides a sorted dataset in half until it finds the desired value. This technique saves time by focusing only on relevant sections of a dataset. Now let's consider some key aspects of using binary search, starting with a common use case. Imagine we have a sorted list of student scores from lowest to highest. Binary search allows us to quickly locate a specific score without checking each one individually. By progressively dividing the list in half, it can skip over sections that don't contain the target value, making it much faster than a linear search. Another consideration of binary search is its time complexity. Because binary search cuts the search area in half with each step, it has an efficient time complexity. This efficiency is often expressed as order of log n in big O notation, which means the speed advantage of binary increases as datasets grow. For example, imagine a search for a name in a phone book. Instead of checking each name in order, you can open it halfway and then adjust based on whether the name is earlier or later in the alphabet. By repeating this process and focusing only on the relevant half each time, you quickly narrow down to the name you're trying to find. Another efficiency when using binary search is its space complexity, which is memory efficient. Binary search uses very little memory because it only needs a few pointers to track where it's searching within the dataset, meaning its memory use doesn't grow with the dataset size. This is called constant space complexity, or order of 1. For example, while binary search examines different parts of the data, it primarily tracks 3 positions: left, right, and middle. These values are updated within the same memory space, no matter how large the dataset is, making binary search efficient in terms of both overall speed and memory utilization. It's also important to understand that binary search works with data that meets certain preconditions. For binary search to work, the dataset must be sorted, meaning that the data has been ordered. If the data isn't ordered, binary search can't effectively narrow down the target value by progressively reducing its search range. Imagine trying to use binary search to find a friend's number in an unsorted phone book. It wouldn't work. You'd have to check each page. To use binary search on a dataset, the data needs to be in order first. Now that we have explored the key concepts of binary search, let's break down how it works to find a target value. The first step is to set up boundaries. You start by setting left to the first element and right to the last element in the list. For instance, in an array 2, 5, 8, 12, 16, left is at index 0 and right is at index 4. This setup defines the initial range for the search. Next, we find the midpoint. The midpoint is found by taking the middle of the current range, ensuring the search space is evenly split. Calculate the midpoint with mid equals left plus right minus left divided by 2. This finds the center of the current range. In this case, if left equals 0 and right equals 4, the midpoint lands at index 2. This points to the number 8 in 2, 5, 8, 12, 16. Then binary search checks if the midpoint matches the target. If it does, the search is complete. If not, it determines whether to continue searching in the left or right half, adjusting the boundaries accordingly. If the target is smaller than mid, adjust right to mid -1 to search the left half. If it's larger, adjust left to mid +1 to search the right half. Repeat this process until you find the target value or determine it isn't in the list. In this video, you learned how binary search works and identified scenarios where it outperforms linear search. By effectively narrowing down large sorted data sets, binary search offers speed and precision that linear search cannot match. Binary search is a search algorithm that is really useful when you have to search for items in a large data set. Compared to linear search, which takes a start at the beginning and move to the end approach, binary search takes a divide and conquer approach. It divides a large data set into 2 parts, and then it continues to winnow down each part until it finds the item that it needs. In this screencast, I'm going to explain how binary search works and identify scenarios where it outperforms linear search. I have a very simple console application here, and in my main program, I'm creating an array of integers called numbers, and it goes from 10 to 50. So there's 5 items in this array. We're going to search for 30 in that array. It's a very small array of numbers, but we're going to use our binary search to do that. And then we're going to get the result from that binary search, which we'll look at in a moment. This is our binary search method. We're going to pass in numbers and our target. If the result of that search comes back as a whole number, then we're going to write the element where that search item that we're looking for was found. Otherwise, we're going to say that the element was not found. Now let's go to our search class and look at our binary search algorithm. So here we have the binary search method. We're passing in that array, the array of numbers that we just looked at and the target. And then we start our binary search by setting our left and right for the algorithm to be able to operate against. We're setting our left at 0, and then the right is the length of the array, but we're going to take 1 off because this is a 0-based system. So if the array length is 50, we're going to set that to 49, with 0 being the first item. So it goes from 0 to 49, which is essentially 50 items. And then we jump into a while loop here. So while this condition is true, then we're going to operate against these items in the middle of that block of code. While left is less than or equal to right, then we're going to operate against that array in this way. First thing we do is we set a midpoint in that while loop. So the midpoint is whatever the left is plus whatever the right is minus the left divided by 2. And that's going to be our midpoint. Then we start evaluating. So if inside the array at that midpoint, that index number, if that's equal to our target, then we found what we're looking for and we can return that item. If that's not true, if it doesn't equal the target, and if the array at that midpoint is less than the target, then we're going to change our left value to left equals mid plus 1. Otherwise, we're going to change our right value to mid minus 1. And then we go back up to the top of the while loop and we run it all over again. So now our mid is going to change because our left and right has changed. And then we do that same evaluation over and over again. When it finds the thing that it needs, it returns the index number, the mid. Otherwise, it's going to return a -1, which essentially means that it didn't find what it wanted. So now we can go back into our program, and we're going to run this main program against the item that we're looking for. Let me clear this. So we'll run against the small number, and it was found on index 2, which is what we'd expect, 0, 1, 2. The target is 30, and it found it with no problem. Now this is a very small array and a very small data set, so it found it very quickly. Let's see what it does if we throw larger numbers at it. It should run very quickly because binary searches operate well against large numbers. So now we're going to create an array of 100,000 elements, and then we're going to use this randomizer to pick a random ID out of that 1,000-member array. And then we're going to search for that number. Now, in a real-world scenario, we would already know what we're looking for. But in this case, we want to demonstrate how fast the binary search is
by just randomly picking any number out of that set and then looking for it. And then it'll run that binary search and should return the value that we're looking for. So now it found it at element 17,213, much larger, but it still found it very quickly. And we can run this multiple times. Regardless of where it is in the array, it returns fairly quickly. Let's add another 0 to this and make this 1,000,000 members. It returned very quickly still, even though it found it at 204,345. We'll run that a couple more times, and we're still getting very good response. That's because the binary search is taking that entire array, splitting it in half, and then attempting to look for it in both halves. We can add another 0 here, and we still probably won't impact the performance all that much. We will see a little bit of a slowdown. You can see it paused there for a little bit, but it still found it at 3,326,425, and it did it fairly quickly. There it found it at 8,507,718, but again, not much of a performance hit. So binary search is really good for large data sets, and even though we're adding a lot of zeros to our data set, the binary search is still operating very quickly because of the way that it takes that divide and conquer approach. A linear search, if it was searching 10 million records, it would have to go through from the very beginning, search every single record, and do that comparison before it found the record that it needed. So if the item was deep into the array, close to the 9 million mark or whatever, it would just take quite a bit of time because it has to do that constant evaluation of each item in the array. Binary searches with its divide and conquer approach can be much quicker. In this lab, we're going to implement binary search within a .NET Core console application and apply it to a practical use case. In step 1, we're going to set up our application. We have our main method here, and we're going to do a few things. We're going to create a couple of variables. First of all, we're going to set up an array of ints called product IDs, and we're going to pass in these IDs. So this is our real-world scenario. Let's suppose that we have a catalog, and we have a catalog full of product IDs, and we want to use binary search to find an ID in that list of IDs. So this is our IDs that we're going to pass into our algorithm. The target is the one item that we're going to look for, and that's defined down here. So if we pass in valid to get test target, it's going to return 1055. That question mark means if the type we passed in equals that word, then it will return 1055. Otherwise, it will return 1099. So if it's anything other than valid, it'll return 1099. We have 9999. We have 1055 in our product IDs, and we're going to return here 1055 so that we have something to search for. We know we're going to hit the target. We then call our binary search, passing in our array of product IDs and our target. And then if the index is anything other than -1, we're going to take that as a true condition. It did find the target we're looking for, and we'll write that out to the console. Otherwise, we're going to write out that the target was not found. That's the basic setup for our application. Now in step 2, we're going to implement the binary search function, which is down here. Here's our binary search. Remember, a binary tree has no more than 2 children. We use this right and left to refer to the branches of that tree, and then we use the mid to figure out where in that tree we are. We're using the while loop to work through that array. We're constantly shifting the mid and the left and the right to work through that tree as a binary search does. When the mid value for the index for that array equals the target value that we're looking for, then we'll return that mid index so that we can pull the value from the array at that index. And then if it's not found, we return -1, meaning that it couldn't find the value that we're looking for. That's our binary search, and that's how we implement it into this application. Now let's go ahead and run this as it is, and then we'll work with some test cases in step 3. But found our product ID 1055 at index 3, which is what we'd expect because we're sending in get test target valid, returns 1055, and it found it at the index 3, 0, 1, 2, 3. Worked as expected. Now in step 3, we're going to add some more test cases. I want to go ahead and expand our test cases. Let me uncomment this block of code. In this case, we're going to send invalid. We're going to get 1055 back just like we did earlier. In fact, we can comment this out because we already have our test cases in there. So I'll comment out this block of code so we can run these new test cases. We're going to get our test target. Here it's going to be valid. We'll get 1055 back. Run our binary search, and then it's going to tell us it found at index, whatever the index is, or it's going to tell us it's not found. And then the next one we're going to pass in is invalid. So remember, if it's anything other than valid, it'll return 999, and then it'll tell us whether it found it or not. So we can test both cases here. Let's run this now with both these test cases. We passed in 1055. We passed in the same number. It found it at index 3, which is what we had before. When we pass an invalid, which is 9999, that's not in our list of product IDs, so it didn't find it, it returns not found. So this just helps us validate that our binary search is working properly. This is obviously a very limited set of data, and so it's very fast and it works as expected. You can increase the amount of data, and as you increase the amount of data, the binary search is still very fast, and it should perform very well as you increase your data. So you can keep this very basic algorithm and just increase the data size to do some more testing. And then as you make sure that the foundational elements of this binary search algorithm is correct, then you can start to improve it, put in some error handling, and make it even more robust. Efficient searches aren't just a convenience. They're essential for making applications feel smooth and responsive. Binary search is one of the tools that makes this possible. In this video, we will describe how binary search is applied to common back-end tasks like retrieving user data from sorted lists. Before we begin, remember that binary search is an algorithm that repeatedly cuts a sorted data set in half until it finds the desired value. This approach eliminates large sections of data with each step, saving time. Now that we've reviewed binary search, let's examine why you'd use binary search for back-end tasks. First, binary search is fast and efficient for large data sets because it repeatedly divides the search space in half, significantly reducing the number of comparisons needed. With the time complexity of order of log n, it quickly locates target values even in massive sorted data sets. Binary search also has a low memory usage because it uses a constant amount of extra memory, regardless of the input size. This makes it highly memory efficient and particularly suitable for systems with limited resources. Next, binary search is ideal for sorted data because backend systems often store data in sorted structures like databases and indexed lists. This level of structure is a key requirement for binary search to work efficiently, making it a natural fit for backend tasks. However, even as datasets grow, the performance of binary search remains consistent and predictable. This ensures that backend processes continue to perform well as they scale. Now that we understand why binary search is ideal for backend tasks, let's examine some practical scenarios where it speeds up data retrieval. Imagine a platform with millions of user profiles, each with a unique ID. Using binary search, the system can quickly locate the correct user ID in a sorted list without checking each profile individually. This is essential in login systems where users expect rapid access to their data. Another application where binary search is a good fit is when working with product catalogs. Most online stores allow their product catalogs to be sorted by price, and when a user searches within a certain price range, binary search can quickly locate an appropriate starting point and quickly narrow down the search without scanning the entire catalog. This rapid turnaround response improves the shopping experience, keeping users engaged. System logs are also a great application of binary search. For example, consider a scenario where you're troubleshooting an issue by searching logs organized by timestamp. Binary search enables the system to find a specific time range, helping developers scan relevant entries without analyzing each log line. This makes the process of investigating issues much more effective. Finally, real-time auto-completion is an ideal application for binary search. Imagine an online store that offers a wide variety of products like smartwatches, Bluetooth headphones, and camera lenses, as well as drones.
The store wants to implement an autocomplete feature to help users quickly find products as they type in their search. Binary search is ideal for autocomplete systems because it enables fast and efficient searches in sorted datasets, handles large-scale data gracefully, and supports real-time user interactions by quickly narrowing down potential matches. In this video, you learned how binary searches apply to common back-end tasks like retrieving user data from sorted lists. In modern applications, efficient data retrieval keeps users engaged and systems working smoothly. Binary search gives back-end systems the speed they need to power these experiences. Binary search really shows its stuff when it's operating against large data sets. We use different types of search algorithms for different needs, and binary search is really optimal for larger data sets. In this screencast, we're going to demonstrate binary search implementation in .NET Core to optimize search operations within a sorted data set. Remember that binary search does need the data set to be sorted. That's what we're going to operate against in this screencast. I have a very simple C# console application, and I've got a binary search method here. Into that method, I'm passing in an array of integers called sorted array, and then a target, a number that we're looking for inside of that array. So in this array, or in this search algorithm, I'm going to skip this first part for now, and we'll go into setting our left and right values. So for our binary search, we do need a left and right and mid, but we'll set our left and right first. So we're going to set left equal to 0 and right equal to the length of the sorted array minus 1. This is a zero-based operation, so we're going to take one item off of the length so we don't go past the end of the array. And then we start doing our comparisons. We go into a while loop here, and the while loop will run the code inside of it as long as the condition is not met. So while left is less than or equal to right, then it will look for the specific item in that array. It does that by setting a midpoint first. So it's midpoint equals left plus right minus left divided by 2. And then if the sorted array at that midpoint equals the target we're looking for, then we return the index of where that target was found. If not, then if the sorted array at mid is less than the target, we set the left equal to mid plus 1. Otherwise, we set the right to mid minus 1, and we go through the loop again. We run that code all over again until we find the thing that we're looking for. Now, this is a very simple version of a binary search. It doesn't account for edge cases. Edge cases are those situations where the circumstances are different than what we might normally expect under standard circumstances. When we pass in a sorted array, we expect it to have values in it and then operate against those values in the search. What I've done here is at the very beginning, before we even run the binary search against the array, we're making sure that the array has items in it. So we're checking the length. If it's equal to 0, then we're going to return that there was no value found because the array just doesn't have anything in it. There's nothing to search. So we're accounting for that case by checking first instead of trying to get into the array and then getting an error or having it not run. We do the same thing at the end here. If the value we're looking for wasn't in the array that we sent in, then we want to let the calling function know by returning a -1, was not found. The other thing we're not doing in here is we're not checking for multiple values. Let's suppose our target is the number 5 and sorted array has 2 or more number 5s. This code does not account for that. What we might want to do is check the entire array for the value, and if it finds multiple values, then we send back an array with all the locations of those values or something like that. The point is that there's cases like that you have to think through and make sure that you're accounting for when you're doing a search like this so you're addressing all of your users' needs. All right, now let's look at how this works against real data. I've got multiple versions of our main function, which will go through different scenarios. But in the first version, we have an array of 7 numbers, and we're going to be looking for number 456 in that array. But we're going to use our binary search function to find that. I'm going to run this application, and it's just going to operate against that. And it found it in index 3, 0, 1, 2, 3, 456. So the binary search works as expected. Now, of course, this is a very small array. It's only 7 items big. And binary search has no problem, obviously, tearing that apart very quickly and finding what we need.
But let's look at a situation where we have a larger data set. So I'm going to comment this out and uncomment our next version of our main function. And in this one, we're going to create 100,000 randomly generated records. And then we're going to grab one item out of that array. So we're just randomly, we're going to go through the array and randomly grab an item. And then we're going to throw that into our binary search to see if we can find it. Now, obviously in a real world scenario, you wouldn't randomly grab an item out of your array and then search for it. We're doing this just for demonstration purposes. You would probably pass in a value. But since we want this to demonstrate a real world situation, we want to look for different items within that array by just randomly picking one out. And then we'll send the whole array plus the search item into our binary search and have that come back. So I'm going to run this again. And there's our user ID, which is a randomly generated number, and it was found at index 638,182. That was pretty fast. I'll run it again. It comes back really quickly. It found that user ID at that index using that method of using a while loop, left and right and mid, and constantly changing those values until it found what it wanted. Now, even at 100,000, that's still a pretty small number. If I add another 0 to that and make it 1,000,000, it should still come back fairly quickly. And again, even at that high number of records, 1,000,000 items in the array, the binary search operated against it pretty fast. I'm going to do one more demo, and we want to compare our binary array with a linear search. So I'm going to comment this out, and I'm going to uncomment this version of our main function. Now, linear search, as you'll recall, is just a very straightforward start at the beginning, go to the end, instead of that divide and conquer approach that we take with the binary search. A linear search is just taking that array that we pass in, which is going to be the same array we're going to pass into the binary search, and a target, and it's just doing a for loop. So it goes through each item in the array, and if the array index, whatever it is at that point, so if we have 1,000,000 records, it's going to go through it 1,000,000 times until the index item in that array matches the target, and then it'll return that item. Otherwise, if it doesn't find anything, then it returns -1. But it starts at the beginning and goes towards the end. So you can imagine if the item that we're looking for is at the end of the array, it's definitely going to take longer than it would be at the beginning. I'm going to comment this out and show you the small version first. We're actually setting a stopwatch, a timer, to illustrate the speed differences between these two types of searches. So we're going to set a stopwatch. We're going to run our search. We're doing that in both cases. And then we're going to return the index, and we're going to use the lapsed ticks as just ticks on the clock to show the difference in how fast or slow each of the search types are. The first thing we're going to do is we're going to use a 7-digit array and search for 678 this time. That's at the end of the search. And then we'll run and see how the binary search does compared to the linear search. So binary search, you can see, is actually longer here because for small arrays like this, for small data sets, binary search is actually more cumbersome. It takes a lot longer to perform that search because it has to do that while loop and splitting the data sets into multiple parts and then running a search against that. Linear search just starts at the beginning until it finds it, and then in a small data set, that goes very quickly. Let's comment this out now, and let's do our larger data set. And here we're going to create that array of 100,000 items and pass that to both of our search algorithms, the binary and the linear, and we'll see what does better. They both found it at index 25097, which is what we would expect. Binary search took 1,871 ticks, and the linear search took 2,146 ticks. And that's largely because of where that item was found, which index number it was found at. And you can see that binary search is starting to show a performance improvement. It actually didn't improve on the time. In this run of it, the binary search took 2,826 ticks and the linear search 1,713 ticks. It really does depend on where the item is and then how long it takes for the binary search to tear that index apart, find what it needs to find. We can increase our number and see if the binary search really starts to show up. So now we've got 1,000,000 items in our array, and let's see what happens when we run it against 1,000,000 items. Now we're starting to see binary search really show its power. And this first run of it, it found it in roughly 50 by 100 ticks. whereas linear search, it took 12,000 ticks, almost a little bit more than double the time. If we run it again, now we see even better performance. This is found at index 647,350. That's deep into the array. So the linear search, because it's starting at the beginning and going towards the end, is going to take significantly longer. But we see how the binary search using that divide and conquer approach really can tackle those larger arrays better. Let's add one more zero. So now we'll go to 100 million records and we'll see what that looks like. All right, now we can see a huge difference here. The index for this item that we want to find was at 8,202,000. It took the binary search just 3,200 ticks to find what it needed, whereas it took the linear search 216,000 ticks, significantly longer to find the same item. We'll run it again, and we're seeing the same results. So binary search at that large data set item just operates so much more quickly than the linear search, which is exactly what we would expect, right? As we take that number down, if we go to 10,000, we should see linear search greatly improving performance over binary, depending on where the item is. As we get closer towards the front of the index, the linear search is doing better. Now, even in this case, with 10,000 records, linear search is still a little bit behind binary search, which is fascinating. If we go down to 1,000 records, we might even see a better performance on linear. And that's where the linear search starts to show better performance. Binary search in a real world situation, you can see the dramatic difference as you get higher, more and more records in your array that you want to search or your data set that you want to search. Linear search does operate better on smaller data sets. So it all depends on your scenario and what you want to accomplish with using your search algorithm. In this lab, we're going to apply binary search to optimize search operations in a .NET Core application that handles API requests. On our first step, we're going to fetch user data from an API. So I've got a simple console app here. We're going to use this application to go out to an open source test API that returns user data. I've got a main method that will call this fetch users from API method. And then we're going to simply write out to the console the usernames that have retrieved. We have a users object, and we're going to go through each user and then display their username. The fetch users from API method, the first thing we want to do is make sure that our names are consistent. We have the name of fetch users from API, which is the same method that we call above here. So we want to make sure those are consistent. And then we create our HTTP client object. We set our URL. This is randomuser.me. which is that open source public API that we can test from. And then we're going to use the HTTP client object that we created above, and we're going to use the get from JSON async method to get our response back from that API. So that's just going to go out to the API location, the endpoint, and return JSON that we're going to fill this response variable with. And then we're going to populate our users object with the results of that by using this for each loop to go through and add the user to the user's object. So it's going to take those 10 results back. We're setting the results to a limit of 10, and then just fill that user's object with that result. And then we'll write out to the console the username. So let's go ahead and run this, see if it works. I went out to the API, and it fetched these users, and here's the user names that it gave us so that we can print those out to the console. In step 2, we're going to implement binary search, but in order to do that, we need to sort our list. Binary searches require a sorted list in order to work properly. We're going to add a line of code where we're going to sort that list. So we just use users.sort, which is a method that's available on the user's object, and we're going to sort by username, and that will allow us to then implement the binary search. We have our binary search method here. And I'm not going to go through the details of the method, but this does a binary search to find the item that we're looking for. We have our left and right and our midpoint, and it uses that binary search algorithm to find the object that we need. When it finds it, it just returns it. It's typically the middle point that we're looking for when we're narrowing down our search in a binary search. So it returns the value. If it doesn't have a value, then it's going to return -1. Now, I've also added some code here so that we can enter a name to search for. We'll get a list of usernames back, and then I'll go ahead and add that to our search feature so we can actually look up a specific username. In step 3 now, we're implementing this binary search, and we can actually see how it runs. I'm going to clear the console, and we'll run this application again. We have our usernames, and I'm going to search for Big Cat 280 because we know that's in that list. And then it's going to use the binary search function and actually return the user's first name and last name associated with that username. That's how the binary search works. It goes through, looks for the username that I typed in, it narrows down the items in that list, and then returns the value to my calling function. That's a very simple way to implement a binary search using an API call. And binary search on the small data set is very fast, but as the data set grows, it still will remain pretty quick because binary search is a very fast algorithm. Key points to remember is that you have to sort your data first to make sure it's in the right order, and then you can perform a binary search against it.
Choosing which algorithm to use shapes an application's speed, efficiency, and reliability. Knowing when to use each sorting algorithm can be the difference between smooth performance and frustrating delays as datasets grow. In this video, we will describe the time and space complexities of bubble sort, quick sort, and merge sort, focusing on their trade-offs. To begin, let's explore some of the performance metrics and trade-offs for each sorting algorithm, starting with time complexity. Recall that time complexity measures how long an algorithm will take to run as the dataset grows in size. Now let's compare the time complexity of each of these sorting algorithms. Bubble sort has a time complexity of O times n squared, which means it takes longer with large datasets. Merge sort consistently has a time complexity of O times n log n, so it's efficient even on large datasets. The time complexity of quick sort varies depending on how the pivot is chosen and how balanced the partitions are during the sorting process. On average, it is O times n log n, but it can be O times n squared in the worst case. When choosing an algorithm, we use its time complexity to help us understand how long it will take to run as our dataset grows. For example, if we're sorting on a small list on a mobile device, an algorithm with low memory uses like bubble sort might work fine even though it's slower. For large datasets on a server that has more processing power, quick sort or merge sort would be more efficient due to their lower time complexity. Memory usage is another key performance factor, along with time complexity, which is where space complexity comes in. Recall that space complexity is a measure of the memory an algorithm uses as it runs, which is especially important in low memory environments. Now let's compare each sorting algorithm's space complexity, trade-offs, and benefits. Bubble sort has a space complexity of O times 1, meaning that it uses very little memory, which makes it a good choice for small datasets in memory-constrained environments, or when simplicity of implementation is more important than performance. Merge sort has a space complexity of O times n. It needs extra memory for merging, which can be challenging in memory-limited systems. It's a better choice for sorting large datasets under conditions where memory usage is not a primary concern. Quick sort has a space complexity of O times log n. It uses extra memory for recursive calls, but its average memory usage is generally low. Quick sort is best suited to large datasets where the need to optimize memory usage is balanced against a requirement for high performance. Now let's examine stability, the preservation of the relative order of equal elements in sorting algorithms. A sorting algorithm is considered stable if it preserves the relative order of elements with equal keys or values. In other words, if two elements are equal in terms of their sort key, they remain in the same order relative to each other as they were in the input. Stability is most important when sorting multiple criteria. For example, if we were sorting products first by price and then in the order they were added, maintaining stability is crucial. In this particular example, knowing when to choose the right sorting algorithm can make all the difference. While bubble sort and merge sort keep the original order of equal items, quick sort may reorder them unless it's modified to be stable, which wouldn't be suitable for this application. Now that we have explored time complexity, space complexity, and stability, let's examine them together so we can better understand each algorithm's strengths and best use case. Bubble sort is best for small, simple tasks because of its simplicity and low memory use. For example, a small business with just a few employees might use bubble sort to organize its list of employee IDs in ascending order. Since the list is small, bubble sort will be memory efficient and simple to implement. Merge sort is ideal for large datasets or when stability is essential. For example, a telemedicine platform could use merge sort to organize millions of patients' records by appointment dates, while keeping patients with identical dates listed in their original order of entry for continuity. Quicksort is a strong all-around choice for fast average performance. For instance, an e-commerce company might use quicksort to efficiently sort products on their online store by type, price, or brand. This allows customers to easily group and view these items in the way that best complements their shopping preferences. In this video, you learned about the time and space complexities of bubble sort, quicksort, and merge sort, focusing on their trade-offs. Understanding time complexity, space complexity, and stability allows you to make sorting choices that balance speed, memory, and data integrity, key ingredients for building efficient and responsive applications. Behind every fast, responsive app is a careful choice of sorting algorithms that match the system's unique needs. Choosing the right sorting algorithm can make the difference between an efficient system and one that slows to a crawl under heavy data loads. In this video, we will explain how to select the appropriate sorting algorithm based on back-end system requirements. To begin, let's examine some of the factors to consider when choosing sorting algorithms for back-end tasks, starting with task complexity, or how challenging a task is. Task complexity in back-end development refers to the difficulty of implementing and managing server-side logic, database interactions, and API integrations. The complexity of these tasks depends on factors such as system architecture, data structures, concurrency handling, and third-party service dependencies. More complicated tasks usually require more efficient algorithms, while simpler tasks can use basic algorithms. For example, if you're dealing with a large data set like user logs, an efficient algorithm like merge sort is typically best because it's stable and handles large volumes of data well. For simpler, smaller tasks like sorting a quick list of debug information, algorithms like bubble sort or quicksort are faster and easier to apply. Next, let's explore data size and how it affects choosing a sorting algorithm. In the context of sorting algorithms, data size refers to the number of elements in the data set that need to be sorted. Larger data sets generally require algorithms optimized for handling big data, while smaller data sets can benefit from simpler, faster algorithms. For example, when sorting large data sets, such as thousands of user records, an algorithm like merge sort is ideal because of its consistent performance with big data. For smaller data sets, quicksort or bubble sort is often faster and simpler to use. Now that we've explored data size and task complexity, let's examine how resource constraints impact sorting algorithm choices. Resource constraints are limits on system resources like memory and processing power. Some algorithms need more memory or processing power than others. Selecting an algorithm that fits within your system's constraints helps prevent slowdowns and keeps the application performant. For example, if memory is limited, an algorithm like quicksort can be a good choice because it uses minimal memory while still efficiently sorting smaller datasets. In cases where memory limitations are less of a concern and you are working with larger amounts of data, merge sort is the better option. This algorithm is more memory intensive but handles large datasets consistently and reliably. Next, let's explore real-time sorting needs, which is another important factor to consider when choosing a sorting algorithm. Real-time sorting refers to algorithms or systems that can process continuous streams of incoming data while maintaining a partially or fully sorted order in real time. For tasks that require immediate sorting, like commercial inventory management, a fast algorithm like quicksort works best. For tasks that don't rely on immediate sorting, like nightly data backups, merge sort can be more suitable as it consistently provides stable, ordered results. For example, imagine an e-commerce platform where inventory and prices of thousands of products are updated in real time. In this example, quicksort would be ideal for keeping products and prices sorted as they change. It provides efficient sorting without using too much memory, ensuring that updated data is displayed to users immediately. For tasks like end-of-day sales reports, which don't rely on instant updates, merge sort is a better option because it processes large volumes of data with stable, consistent results. In this video, you learned how to select the appropriate sorting algorithm based on back-end system requirements. Knowing how to choose the right sorting algorithm is like having the key to unlock efficient, optimized back-end systems. With the right algorithm, you'll be able to transform data management challenges into seamless solutions. Choosing the appropriate sorting algorithm is largely based on what you're trying to do and the dynamics of the data set that you're trying to sort. In this screencast, we're going to explain how to select the appropriate sorting algorithm based on the back-end system requirements that you have. We're going to focus mainly on time complexity. All of the algorithms we're going to look at in this screencast have similar space complexity except for merge sort. Merge sort does take up more space, so the larger the data sets, that's another consideration that you'll want to give to which algorithm you choose. In this program, I've got 4 different sorting algorithms that we're going to use. We're going to look at quicksort, merge sort. I'm going to just use the built-in .NET array.sort method just to compare it to the other sorting methods that we're going to look at, and then finally bubble sort. All but the array sort I've implemented in this application. Bubble sort's here at the top. We're not going to go through this. We've looked at this in other topics, but these are just standard sorting algorithms based on the approach that we take for each one. Quicksort's next, and this is using another method called partition to divide the list into high and low. And then merge sort is similar. We've got a left and a right, and then we've got our merge function here. We're copying parts of the array into left and right, so that's going to increase space complexity as well as the time complexity that we're going to look at. So that's another consideration to make. To look at time complexity, we're going to look at 2 different types of data sets and increase the size of these data sets as we go. The first one's super simple. It's just 8 items long, 1 through 8 in various order. And then we're going to sort this using these 3 different algorithms. For each one, we're going to look at the elapsed milliseconds for the time that it takes to complete the sort for all 4 of the different sorting algorithms. So I'm going to go ahead and run this, and we'll see what each comes back with for each of the sorting algorithms for this very small data set. Quicksort, merge sort, array sort, and bubble sort, all 0 milliseconds. It happened so fast on this computer that it didn't even register any elapsed time. For really small data sets like this one, any of these sorting algorithms will do the job. It's not worth really hassling over, particularly if you're dealing with very small sets of data. You don't need to really worry about which method to choose. Now what I'm going to do is give these algorithms a much larger data set. So we're going to start with 50,000 items, just creating a random list of numbers here, and they're going to be in various order, and then we're going to use the sorting algorithms to sort them from lowest to highest. And we'll see what the difference in time is. I'm going to clear the terminal, and then we'll run this again. And we'll see if we see a difference in the time it takes. All right, so it's still running. Okay, there's bubble sort at the end there. Quick sort time was 5 milliseconds. Merge sort time was 8 milliseconds. Array sort time is 2 milliseconds. And then bubble sort was roughly 3,100 milliseconds. So clearly bubble sort takes the longest of this bunch in terms of time complexity. Interestingly, the built-in .NET array sort was the fastest because it's highly optimized for this specific type of data, which are just a list of numbers, an array of numbers. So you can see how that performs really well for this scenario.
But quicksort and merge sort are very close. In terms of milliseconds, the difference is quite negligible. Now let's add another 100,000 items to our array. Here we're looking at 150,000 numbers that we want these algorithms to sort. So I'm going to go ahead and run this again, and we'll see the difference in time. All right, so we've got our quicksort, merge sort, and array sort have already completed. The bubble sort is still working, and it will be working for a few seconds longer because it has so much to process. For this run, quicksort time is 16 milliseconds, the second fastest. Merge sort time is 24 milliseconds, and then the array sort, the built-in .NET array.sort method, was 9 milliseconds. Again, that was the quickest because the array.sort method is highly optimized for this type of data. If you're doing testing like this, you can obviously give it other types of data, see how it works with strings or binary data, and see what you end up getting back. It may differ based on the type of data that you're working with. Bubble sort now has returned, and it was 38,000 milliseconds, quite a bit different for the size of the data that we're sorting. We can continue to increase the number and look at this and see the space complexity impact. Sometimes milliseconds make all the difference. With data like this, the array.sort method built into .NET may be the best choice if you want the fastest response times. For other types of data, you might find that merge sort or quicksort works. And then bubble sort is a nice option, again, given the type of data that you're working with. If you need data to be operated against in a very specific way, bubble sort has its advantages. Even though it takes longer, there are specific reasons to use bubble sort working with the type of data that you're using.
Choosing the right algorithm can improve performance, reduce processing time, and ensure seamless data retrieval in real-world applications. We began by examining core sorting algorithms like bubble sort, quicksort, and merge sort, exploring how they arranged data and contributed to efficient computation. Next, we applied sorting algorithms in a .NET Core environment, evaluating their efficiency by measuring time and space complexity to understand their impact on real-world performance. Then we examined searching algorithms, learning how different approaches help retrieve data efficiently from various data structures. After that, we enhanced search performance by implementing binary search, utilizing its rapid lookup capabilities to efficiently retrieve data from sorted datasets in back-end systems. Finally, we assessed various sorting algorithms, analyzing their advantages, drawbacks, and ideal applications to make strategic choices for optimizing back-end system performance. Optimizing how data is sorted and searched is crucial for building efficient back-end systems. Effectively applying these algorithms will enhance performance, streamline data processing, and support scalable application development. Welcome to Trees and Graphs. Effectively structuring and navigating data is crucial for building scalable back-end systems. In this module, you'll explore tree structures and graph theory, learning how they support complex relationships and optimize data processing. We will begin by exploring tree structures, including binary trees, binary search trees, and balance trees, and understanding how they organize and manage hierarchical data efficiently. Next, we will implement tree traversal algorithms, learning how to navigate and process tree-based data structures effectively in back-end applications. Then we will examine key concepts in graph theory, discovering how graphs represent relationships and solve complex connectivity problems in real-world systems. After that, we will implement load balancing strategies, ensuring back-end systems distribute workloads efficiently and maintain performance and scalability. Finally, we will apply asynchronous processing techniques, optimizing system responsiveness and scalability for handling high-demand applications. By the end of this module, you'll have the skills to structure data effectively, improve system performance, and handle complex computational challenges. Let's get started with trees and graphs. Information needs to be organized in a way that makes it instantly accessible and efficient to store and retrieve, regardless of the amount of data involved. Tree structures help us accomplish this by creating logical pathways through complex data. In this video, we will describe the key properties of binary trees, binary search trees, and ABL trees. Let's begin by defining tree structure and exploring some of its key elements. A tree data structure is a hierarchical data structure where each node has a parent-child relationship. In this structure, a parent node has connections leading to one or more child nodes, which are directly below it in the hierarchy. It's like a family tree where each person has clear connections to others. This structure helps store data in an organized way as each level is connected to the next. Within a tree data structure, each tree consists of nodes named based on their position in the hierarchy. At the top, the root node serves as the starting point, with parent nodes linking to child nodes, forming a structured hierarchy. Now that we've explored a tree data structure, let's examine one of the most common data tree structures, binary trees. A binary tree is a type of data tree where each node has at most two children, known respectively as the left and right child. This structure simplifies data organization since each decision point has only two branches, which is ideal for tasks that involve sorting and searching. You can think of binary trees as decision flowcharts, where each choice leads to only two possible outcomes. This simple two-child rule makes binary trees useful for organizing data that naturally splits into two directions, like survey questions that offer only two options, yes and no. Next, let's examine a specific type of binary tree called the binary search tree, or BST, which organizes data in a sorted way. A binary search tree is a binary tree that maintains a sorted order, with each left child smaller than its parent, and each right child larger than its parent. This structure makes it easy to search for specific items quickly because of its sorted layout. For example, imagine flipping through a dictionary where words are organized alphabetically. If you're trying to find a word starting with N, you know where to start. BSTs follow a similar principle, making them very efficient for managing ordered data. In our example, words in a dictionary are sorted alphabetically. This order provides a natural way to narrow down where to search for a word. Similarly, nodes in a BST are organized such that the left subtree of a node contains values smaller than the node, and the right subtree contains values larger than the node. This property allows efficient navigation to find a target value. Now that we've explored binary search trees, let's examine another type of binary tree, the ABL tree. An Adelson, Velsky, and Landis tree, or ABL tree as it's most commonly known, is a self-balancing binary search tree in which the heights of the left and right subtrees differ by no more than one level. This ensures that the tree remains balanced, providing efficient performance for search, insertion, and deletion operations. When data is added or removed, ABL trees make small adjustments to remain balanced, keeping search times quick and efficient. Without this balancing mechanism, a tree could grow unevenly, making one side much deeper and slowing down searches. ABL trees prevent this by automatically rebalancing so that retrieval times stay fast and reliable. In this video, you learned about the key properties of binary trees, binary search trees, and ABL trees. Knowing the difference between binary trees, BSTs, and ABL trees helps you understand how data is organized, stored, and retrieved efficiently. Tree structures play a crucial role in modern back-end systems, shaping how data is stored, accessed, and optimized. They enable efficient organization, fast retrieval, and scalable solutions, capabilities that linear structures often struggle to provide. In this video, we'll explain the use of binary trees, BSTs, and ABL trees to solve real-world back-end challenges. A binary tree is a data structure where each node has at most two children, left and right. It's used for organizing and managing data efficiently. Programming languages rely on binary trees to break down mathematical expressions into smaller steps. This allows compilers to process operations in the correct order. When evaluating 5 plus 3 times 2, A binary tree ensures that addition happens before multiplication, following the correct sequence of operations. Without this structure, calculations would be disorganized and unreliable. Operating systems use binary trees to structure file systems efficiently. Every folder can contain subfolders and files, forming a branching hierarchy. When opening a directory like home/user/documents, the system follows a structured path instead of searching all files individually, reducing retrieval time and improving performance. Binary trees provide structure, but without specific ordering, do not inherently support fast searching. Binary search trees, BSTs, address this by adding a strict ordering rule, enabling efficient search operations. Search engines organize index web pages using BSTs to retrieve results efficiently. Instead of scanning millions of pages sequentially, the search algorithm navigates the BST structure. This approach quickly narrows down relevant results and speeds up query responses. For fast searches, contact lists use BSTs to store names in alphabetical order. When looking for Alice, the system doesn't check every name individually. Instead, it moves through the BST structure, filtering out unnecessary comparisons and finding the right match efficiently. This method makes searching through large lists much faster. BSTs improve search efficiency, but they can become unbalanced, leading to slower performance. ABL trees solve this by maintaining balance automatically. An ABL tree is a self-balancing BST that keeps search times consistent by preventing any branch from growing too deep. Databases use ABL trees to manage indexes efficiently, ensuring search performance remains stable as data grows. For example, an e-commerce site with millions of customer records benefit from ABL trees because they keep search times predictable, whether querying new or existing customers. Operating systems use ABL trees to optimize memory allocation. When a program requests memory, the system selects the most suitable block based on the ABL tree's structure. This prevents wasted space and ensures smooth performance. Tree structures enable efficient and scalable solutions, from structuring data in file systems to powering search engines and optimizing databases. Understanding binary trees, BSTs, and ABL trees helps developers design systems that handle large-scale operations quickly and precisely. Tree traversal techniques are at the heart of efficient data processing, helping organize everything from search results to hierarchical file systems, database indexes, and decision-making processes in AI. Mastering these methods opens up powerful ways to retrieve, manage, and organize data in nearly any application. In this video, we'll explain the purpose of different tree traversal techniques and when to use them. Let's begin by exploring different tree traversal types and their use cases, starting with pre-order traversal, which is useful for applications where the root node or topmost node in the hierarchical structure needs to be processed first. Pre-order traversal is a tree traversal method in which the root is visited first, followed by the left subtree, and then the right subtree. For example, imagine you need to create a backup of a folder structure. Using pre-order traversal, you'd start by copying the root folder, then move each subfolder and file. This approach maintains the folder order, making it easy to duplicate the structure as it is. Using pre-order traversal, we handle each part of the hierarchy in the sequence in which it's found, with the root taking priority. Next, we'll examine in-order traversal, which returns data in sorted order, making it perfect for binary search trees. In-order traversal is a tree traversal method in which the left subtree is traversed first, then the root, and then the right subtree. In a binary search tree, or BST, this approach retrieves nodes in ascending order. For example, imagine you're working with a database that stores customers' IDs in a BST, and you need these IDs to be listed in ascending order. Using in-order traversal, you can go through the database in a left, root, right order, retrieving customer IDs without any extra sorting. This is because BSTs naturally organize data so that an in-order traversal returns everything in order. This saves time when you need to process data sequentially. Now let's explore post-order traversal, a technique ideal for processing child nodes before their parent. Post-order traversal is a tree traversal method in which the left and right subtrees are traversed first, then the root. This is useful when child nodes must be processed before their parent node. For example, consider a situation where you need to delete files within a directory. With post-order traversal, you delete all the files in each subfolder first, then delete the folder itself. This sequence ensures nothing is left behind as we handle all child nodes before the parent. This method works well for deletion where dependencies in the hierarchy matter. Finally, we'll discuss level order traversal, which processes each level one at a time, making it perfect for handling hierarchical layers. Level order traversal is a tree traversal method in which each level of the tree is traversed from top to bottom, visiting nodes level by level. This method is often used in breadth first search, or BFS. Level order traversal is ideal for hierarchies or situations where nodes at the same depth must be processed before deeper levels. For example, imagine you're following an organizational chart and want to process data for each management level in order. Level order traversal lets you process executives first, then managers, then employees, moving from the top of the hierarchy down. This traversal is perfect for hierarchies because it preserves the order of levels, handling each layer as you go. In this video, you learned about the purpose of different tree traversal techniques and when to use them. Understanding these techniques builds a foundation for navigating data structures with purpose and precision, empowering you to choose the best method for efficient data management in a real-world application. You can traverse a binary tree in a number of different ways. It all depends on what type of data you're working with and what your goals are. In this screencast, we're going to demonstrate how to implement and test tree traversal algorithms within a .NET Core Console application. In this application, I've got two main files. I've got program.cs, which is the entry point to our program, and then a binary search tree.cs file that has a couple of classes in it, and that's where we'll do most of our work. In our main method, we've got our binary search tree object called BST. Then we create an int array of values, 50, 30, 70, 20, 40, 60, and 80. And then we're going to insert each of the items in that array into our binary search tree object. And then we're just going to call different traversal algorithms, passing in that data to see how those algorithms traverse that tree. So let's take a look at the binary search tree file. The first thing we're doing in this file is creating a new class called node. And node just stores the data. It stores the left and the root of the tree. We create that node object in our binary search tree when we're working with the data that we're passing in. In the binary search tree class, we create a node called root. So this is a node object that we've defined up here. Call it root. And then we have an insert method where we pass in the data. And root then equals the result of the insert rec method, insert record, passing in the root and the data. The insert record or insert rec method takes care of filling the root left and the root right. So we have a tree structure once this method runs. We pass in the root and then we pass in the data item. And then it does a number of if-else checks and inserts the data at the right place. This creates our tree object that we're going to work with. And it just essentially takes that array that we saw in program.cs and fills up the tree and the proper relationships for our binary tree. And then we have our traversal methods. The first thing we're going to look at is a pre-order traversal. Recall that a pre-order traversal is essentially used to, like in cloning or serializing. It starts with the root node, and then it moves to the left branches and then to the right branches. So we can see that here. It's doing a check. If the node is null, then just return. We don't want to do anything with it. Otherwise, it continues to loop and call itself, passing in the node left and node right as a part of the structure of that tree. So it'll traverse it based on the root first, and then moves to the left, and then moves to the right. The next algorithm we have is an in-order traversal. In-order traversal is used when you're displaying elements of a binary search tree in ascending order. It's going to do that null check, but then it's going to look at the left node, print that out, and then it's going to pass in the right node, and it will continue to go down that tree doing that work, traversing the tree
in the order in which it was passed in or created. Post-order traversal does exactly the opposite of pre-order. The order here of the left and right nodes come at the beginning of the function rather than running the data out at the beginning. We're running it out at the end. So it looks for that null value, and then it calls itself passing in node left, and then calls itself passing in node right, always checking whether there's null, and then it reverses the order. It starts from the end and moves towards the front, moves towards the root. This is really good in situations, for example, when you're deleting items. You want to start with all the children first before you delete the parent folder, for example. And then level order traversal is our last one. This is finding the shortest path in a tree. Here we're using a queue. We create a new queue object here on line 74, and then we add the root to the queue. So queue.enqueue adds the item to the queue itself. If the queue count, the number of items in the queue is greater than 0, we create a temp node and we dequeue the item on the queue into that temp node, and then we write out the data. We do these checks. If temp node.left is null, we enqueue, add temp node left to the queue, and then we do the same for temp node. We enqueue that to the queue if it's not null, and then we just continue to call that while the queue count is greater than 0. And that will essentially produce the shortest path through the data that we're passing in. In this case, because the data is so small, it's just going to essentially look like the in-order traversal. It's just going to show it in the order in which it was produced. So those are our 4 algorithms, and now we'll go ahead and run the application and we'll see the results. All right, so there's our pre-order traversal, 50, 30, 20, 40, 70, 60, 80, which is what we would expect based on how that pre-order traversal is meant to work. Starts with the root, moves to the left branches, and then moves to the right branches. In-order traversal should go from lowest to highest, 20, 30, 40, 50, 60, 70, 80. So that produces the values in the numerical order that we have in our array. Post-order traversal starts at the end and moves towards the root. So here we have 20, 40, 30, 60, 80, 70, 50. So if you look at that array, you'll see that it does move in that order that we would expect for a post-order traversal, adding the items at the end first and then moving towards the root. 50 at the end there is our root value. And then level order traversal, finding the shortest path through the array, items in the same order that they are in the original array, because that's the fastest way through the array, 50, 30, 70, 20, 40, 60. This is a very simple example of how you can use these different algorithms to traverse this binary array of values and how each will approach the order of the items in the array based on what you're trying to accomplish when you're traversing it.
Connections shape how we understand the world, from the order of tasks in a project to the friendships we build. By understanding directed and undirected graphs, we can organize and represent these connections in powerful ways. In this video, we'll explain the differences between directed and undirected graphs and their real-world applications. Let's start by exploring what a graph is and why it's useful for representing different kinds of connections. In back-end development, a graph is a data structure consisting of nodes or points representing items like tasks or people that are connected by edges or lines. These represent relationships or connections between the nodes. Graphs help us organize relationships like tasks in a project or connections between friends. Now that we understand what graphs are, let's explore some of the graph concepts, starting with directed graphs. Directed graphs show connections with edges that have a specific direction, indicating one-way relationships between nodes. This makes them perfect for organizing steps or tasks that follow one another. For example, imagine you're managing a project with tasks that must be completed in a specific order. Task 1 must happen before Task 2, and Task 2 must happen before Task 3. In a directed graph, each task points to the next, showing the sequence clearly. Directed graphs are perfect for this type of structure because they show how each step flows logically to the next one. Now let's examine undirected graphs. An undirected graph is a graph where edges have no specific direction, representing mutual or bidirectional relationships between nodes. Undirected graphs are perfect for equal relationships or those without a set order, like friendships or shared interests. For example, consider a friendship network. If person 1 is friends with person 2, then person 2 is also friends with person 1. This relationship is mutual and bidirectional. An undirected graph represents this scenario perfectly, with each connection equal in both directions. While these two types of graphs are distinct, they can be used in similar ways, such as on a social media platform. For instance, imagine that you want to leverage graphs to model your favorite social network platform. Mutual friendships where both users agree to be connected, for example, Facebook friendships, could be represented by undirected graphs. However, one-sided interactions or relationships, such as following on platforms like X, where one user follows another without mutual agreement, could be represented as directed graphs. By combining both types of graphs, you can effectively model the complex relationships between users on the platform. In this video, you learned about the differences between directed and undirected graphs and their real-world applications. Understanding when to use directed and undirected graphs helps us organize information clearly and logically. In this lab, we're going to implement a depth-first search, or DFS, and a breadth-first search, BFS, in a .NET Core application. These are two different ways to traverse data trees. In step 1, we want to define the graph structure. So I've got a graph.cs file here, and I've got a class called graph. In this class, we're first defining a dictionary object called adjacency list. And then we've got the graph method that's run when the class is instantiated, and it essentially creates an instance of that adjacency list that we can use in our methods. Then we have an add edge method, and in this we're going to work through the items in that adjacency list. So the first thing we want to do is check and see if the adjacency list contains a specific key. That method is defined elsewhere. If it is, then we add that item to the adjacency list. And then we do the same thing looking for node 1 and then node 2. And then we're constantly adding these nodes in the right order based on those evaluations. In this line, we do adjacency list node 1.add. We do the same thing for adjacency list node 2.add at the bottom there. And we continue to loop through to create those edges in our list. We have a dictionary called getGraph as well. And that just allows us to get the graph that we created in add edge. It just returns the adjacency list that we created. In step 2, we're going to implement depth-first search. We have a class called graph traversal here that will do the search. Depth-first search explores as far as possible along each branch before backtracking. When it's trying to find a way through the graph, it's going to visit as far as it possibly can along the branches first, and then it will backtrack as needed. We have our method DFS. We're passing in the graph the starting point and then a hash set of visited nodes. We have an if statement here where we're doing our comparison. If the visited contains the start, then we return because we found our end goal. If not, then we write to the console the start plus space, and then to the visited hash set, we add that starting node. And then in our for each loop, we're just going through each of the neighbors in the graph. We're defining neighbor as a variable, and it's just the items that are in that getGraph method call that we're making. And then we recall DFS passing in those same items. So that's how we traverse the tree. It's a recursive call to get to the end goal that we want in this depth-first search. In step 3, we're implementing breadth-first search. Just for simplicity's sake, I rename this graph traversal BFS, so it's a different class. And then we have a different method called BFS, where we're doing the similar thing. We're passing in the graph and the starting point. Here we're creating a queue, and we're going to NQ and DQ and add items and take items out of the queue as we move through the algorithm. We also create a hash set called visited here. We start the process by adding the start node to the visited object as well. This is our beginning point. And then we check the size of the queue. While it's greater than 0, we're going to process the information. We're going to run through each of these items inside the while loop.
First, we set a variable called node equal to whatever is the current item in the queue. We put that into node, we write that out with a space, and then run our for each loop, and we're checking for each neighbor and doing that call where we're enqueuing neighbor items, adding the visited items, and then running through that process again. It stays within the loop as long as the queue count is greater than 0. You'll remember in a breadth first search, it explores all the neighbors at the current level before moving deeper. In this code, the way that BFS traversal will work by using this queue in the hash set in order to keep track of where it's been and where it needs to go. These are two ways to implement tree traversal. Which one you use is always dependent on your use case, but these are how you can implement these algorithms in a .NET application. Load balancing distributes incoming requests across multiple servers to ensure stability, efficiency, and reliability. Effective load balancing is essential for scalable systems that handle high traffic demands. In this video, we will explain the purpose of load balancing and the challenges it solves in scalable systems. To begin, let's define what load balancing is and explore why it's essential for managing high-demand applications. Load balancing is a technique for distributing network traffic across multiple servers to ensure systems stay available and reliable. It helps handle heavy traffic and keeps systems well-performing and responsive. Think of a busy customer service center where incoming calls are routed to the next available agent, reducing wait times and ensuring each caller receives timely assistance. Similarly, load balancing directs incoming requests to multiple servers, working together to share the workload. This system helps ensure that each server handles a manageable number of requests, keeping the system fast and reliable for users even under peak load. Now that we understand load balancing, let's explore some of its key components, starting with the server pool. A server pool is a group of servers that share incoming requests, dividing the load so no one server is overwhelmed. In a load balancing system, new requests are sent to the best available server so the system stays responsive as demand scales up. By dynamically directing traffic to the most appropriate resource, server pools help ensure fast, reliable service. For example, imagine a restaurant staffed with multiple chefs. When an order comes in, the kitchen manager assigns it to an available chef so that the order is filled with the minimum possible delay. By having a staff of chefs available and assigning incoming orders to those chefs who are ready to handle them, the restaurant can ensure that customers are served as consistently and smoothly as possible. Similarly, a server pool allows requests to be routed to servers with available capacity, preventing any one server from becoming overloaded to the extent that it causes the system to slow down or stop. Now let's explore what a single point of failure is and understand why load balancing helps to prevent it. In the context of load balancing, single points of failure are components or nodes whose failure would cause the entire system to stop functioning. A load-balanced system aims to manage and reduce the critical risk represented by single points of failure to ensure high availability, reliability, and interrupted service, even if individual components fail. For example, imagine a busy airport with only one security checkpoint. If that checkpoint closes, all passengers are stuck and no one can get through. However, with multiple checkpoints open, passengers can keep moving even if one line closes temporarily. Load balancing minimizes single points of failure in much the same way by distributing traffic across multiple servers or resources, thus ensuring that no single component's failure can disrupt the entire system. Another important aspect of load balancing involves the systematic use of health checks. Health checks are regular tests to ensure that servers are ready to handle traffic. These checks help ensure that traffic is routed only to healthy servers that can handle requests, thereby improving system reliability and performance. For example, imagine a sports team's manager checking in on each team member to ensure they are fit and ready to play. Positions will only be assigned to those who are fit and prepared to play, ensuring that everything runs smoothly during the game. In the same way, load balancing uses health checks to ensure that traffic is routed only to healthy servers that can effectively handle those requests.
Finally, another important concept in load balancing is the interplay between latency and throughput. Latency is the time delay between a user's request and the system's response. It reflects how quickly a system can react to user inputs or process tasks. For example, imagine ordering a meal at a busy restaurant. When you place your order, the kitchen starts preparing it, but it depends on how busy they are and how far your table is from the kitchen. There's a delay before your food arrives. The time from when you place the order to when it reaches your table is the latency. If the kitchen is efficient and the server is quick, the latency is low. If the restaurant is overwhelmed or the server is slow, the latency is higher. Load balancing aims to minimize latency by distributing incoming requests evenly across multiple servers, ensuring no single server becomes overloaded and responses are processed efficiently. Throughput refers to the amount of data or requests a system can process within a given time frame. Throughput is directly influenced by latency. The higher the latency, the less the system can process tasks or data within a given time, and therefore the lower the throughput. For example, imagine throughput is the number of cars passing through a toll booth in an hour. If the toll booth operates efficiently with minimal delays, in other words low latency, more cars can pass through. In other words, the throughput is higher. However, if each car takes longer to process due to delays or inefficiencies, fewer cars can get through in the same amount of time, reducing throughput. A load balancing system optimizes performance by minimizing latency through efficient traffic distribution and maximizing throughput by evenly allocating workload and resource utilization. This ensures that requests are processed quickly, servers are not overloaded, and the system can handle effectively high volumes of traffic. In this video, you learned about the purposes of load balancing and the challenges it solves in scalable systems. Load balancing keeps services stable and efficient as demand grows. It also helps ensure that users have consistent, responsive experiences even under heavy load. When you think about writing algorithms to balance load, and you can think of this in the context of servers where you're trying to send traffic to servers based on a specific need, it depends on what your goals are for how you're going to load balance and what type of algorithm you want to use. In this screencast, we're going to demonstrate how load balancing algorithms work and their role in improving application performance. I've got a simple console application here, and these are all going to be algorithms or routines that simulate servers and being able to balance load between those servers. We're going to use different types of algorithms for this purpose. The first one we're going to look at is called round robin. And the round robin algorithm essentially just assigns each incoming request to the next server in a loop. It's super simple and effective when servers have similar processing power or you have a known environment where you're always wanting to spread the load between all the different servers. In this example, we have a list variable. It's a list of strings called servers and an index 0. And then we've got a round robin LB method where we're passing in that array of servers and we're assigning that to the server's variable that we created above. And then we have another method called getServer. So we're getting a specific server within the index. We're going to use this modulo operator, which ensures that the index that we're working with is always within the range of the number of servers that we have available. We're going to get that index, and then we're going to return the server item to the calling function. And remember, the index is going to be stored in that member variable that we created above. Now, in the program itself, in the main method, we define that server list, that array of servers. We create a new instance of the round robin LB object, passing in the servers that we defined. And then you can see how simple the load balancing, quote unquote, works here. We're essentially going in a loop from 0 to 6, and we're going to write out to the console the server that we're working with. And we're doing it twice just to show how we can go through each of the servers, and we're going to get through each server in turn. The round robin starts at server A, goes to B, and then goes to C. When we run this, we go from server A to server B to server C, and then we just loop again. You can imagine a situation where you get a bunch of incoming traffic, and for every request, this algorithm just spreads that traffic across all the servers that it needs. Now, in the second demo, we're going to
write an application that essentially tries to find the server with the least amount of connections. You can imagine a situation where you have a set of servers and you're watching how many connections are associated with each server. And when the next request comes in, you want to balance the load by sending the request to the server that has the least amount of connections. In this demo, we're first creating a dictionary of server connections. This is a dictionary that has a string and an int value in it. It's instantiating a member variable called server connections using that structure. Then we have a least L connections LB, which is a method that we're using to populate that server dictionary. We're passing in a server item, and then we're going to fill the server connections with the items in that dictionary. Then we have a set initial load method, and this is just to simulate server connections, adding different number of server connections at the beginning so we can show how the load balancing works when servers have any number of connections. So in this case, we're going to set this server 0 starting out with 7 connections, server 1 with 9 connections, and server 2 with 5 connections to preload how many connections each server has. Then we're going to use this get server method to get a particular server. When we get that particular server, we're going to add another connection. So we're simulating a new connection, and then we're going to return the server. In our main program, we're going to first define our servers list, server A, server B, server C. Define our LB variable, which is instantiating the least connections LB object, passing in our server list to that object. We're going to set the initial load on all the servers. And then we're going to go through another loop, 1 through 6, and call that LB get server method every time we loop through. Now what this should do is look for the server that has the least amount of connections as it's attempting to pass that quote-unquote load to the server. It's going to use this function get server to find the one that has the lowest number of connections and then add a connection and then return whatever server that was. We can go ahead and run this now. Let me clear the console. Here we have server C, server A, and the next round through it's server C, server A, server C. And the reason for that is because we preloaded server B on the second server with 9 connections. Server A only had 7, server C only had 5. So the first couple of times through, it obviously goes from 5 to 6, 6 to 7. Server C is going to be at the top of the list. And then the third time through, server C should have 8 elements. That gives server A 7 elements, and that's why we see that here. And then you can see how it goes back and forth. The server with the least number of connections at any given time that we're monitoring will get the connection. It will now have another connection as a part of it, so it increases its connection, then the algorithm will go ahead and look for the next one that has the lowest number of connections. This is a least connections type of algorithm for balancing load. The next type of algorithm we're going to look at is called a weighted round robin. It uses a similar method to the round robin where it goes in order for each server, but we're going to assign each server a weight. And in this demo, we're just going to use a weight to signify like power. The server might have a more powerful CPU or whatever, or networking capabilities. We're going to use that weight as we evaluate which server to assign it to. We do a similar thing that we did with previous algorithms. We create a string list of servers and an index as member variables for our class. Then we have a weighted round robin LB, which passes in that dictionary and server weights. So now we're introducing this idea of server weights. We look at the servers, and then along with that, we have the server weights index. And for each server in server weights, we're going to add the server key for that. This is just setting up our object. We're going to add the key to that server's list. Then our final method is get server. Here we use that modulo operator again, which just ensures that the index that we're retrieving falls within the number of servers that we actually have. That produces the remainder of a division operation, so it just helps us to guarantee that we're going to get the right index number back without going beyond the end of the index. That modulo operator helps us do that, and then we return that server back to the con function. In our main function, we define server weights as a dictionary, which has a string member and an int member. Here we have server A is 2, server B is 1, server C is 3, with 1 being the most powerful, 2 being the second, obviously, and 3 the third most powerful. We're going to favor higher weight servers more often than we would with lower weight servers. That's what we do in our get server function here. We're looking at the weights of those servers and then we're returning the one that has the more power. Let's go ahead and run this version. Here we have server A, server B returned in our first round, and then the next one we have server C being returned for all 3. And that is happening because we are increasing the load on each of the servers as we run through that. Server A got the most power at the beginning because of where it's weighted in terms of the order and the power. Then it went to server B because that was the next powerful one. And then it went to server C as we added more load to each of these servers. It increases the load. So higher weight servers get favored more often in these scenarios. This is a round robin, but by using those weights, we can influence which server will get the traffic because we've added a scoring system to make sure that newer servers or more powerful servers get more of the traffic. The final type of algorithm that we're going to look at is using a hashing approach. In some cases, you may want these computers with the same IP address to always get the same server. And this can benefit and improve performance because the server load system doesn't have to go looking for which server to give to that requester, particularly if that individual IP address is making a number of requests all at the same time. By just assigning it the same server, it can decrease the amount of time it takes to look for a server and improve performance that way. So we're going to use a hash algorithm to provide a unique value for each server and then use that modulo function to make that assignment. In this algorithm, we create an array of strings called servers as a member variable. And then we have an IP hash LB where we pass in our servers and assign it to that member variable as our first method. The next method is get hash method. This is where we actually can create our hash out of the IP address that we're going to pass in for our servers. We're using that MD5 create method, creating an array of bytes using the MD5 compute hash method, passing in that IP address, and then we return an int 32 bit converter object back to the calling function. The next method is the get server method. This is where I actually do the work of finding the server that we want to assign to the specific IP address. And then again, we're using that modulo operator against the server.count to make sure that we're getting the right index back and that the index doesn't go beyond the end of the array. Now notice too, here we're using math.abs, which gives us a positive number. And then we're hashing the IP address, which should always be the same when we do that hash. And then when we do that division operator, get the remainder using the modulo function operator, we should always get the same index number back to make sure that we're sending it to the right server. We return the specific server using that index number to the calling function, that we're always getting the same one every time we make the call. Let's look at our main method now. We create that servers list, server A, server B, server C, which is a list of string items. We create and instantiate an LB object using IP hash LB and passing in the servers, just like we've done in the past algorithms. And then we write out to the console. We're going to pass in our IP address for a specific request, simulating a request, to the lb.getServer method. And we should always get the same server back each time we call it. Now I'm going to run it once here first, and we should see server A and server B. They consistently get to the same method. Let's go ahead and add a couple of more of the same IP address to see if we always get the same one back. Let's go ahead and run that. So you can see as I added 192.168.1.1, we're always getting the server A because that's what it's assigned to essentially. If we change this last one to 2, we should see B as the last item. So then we get server A, server B, server A, server B based on that type of request. So you can imagine these are all different requests. And this is always going to send those requests for any specific IP address to those specific servers in our list using this get server method. So it's the type of load balancing in that an individual client will always get the same server which can improve performance and keep the connection performing at optimal speed instead of having to go through and look for a different server at a different time. Those are 4 different ways that you can load balance using the simulated environment. And these are what the algorithms look like if you're going to load balance across either servers, or you can actually load balance many different things. And these are different ways that you can accomplish those goals. In this lab, we're going to implement simple load balancer algorithms in a .NET Core application. We're going to work with one primary algorithm called a round-robin algorithm for balancing load between servers. In step 1, we're going to set up our application. We're going to first use a namespace called load balancer. You can use any namespace you want, but the load balancer namespace will allow us to group classes together as our application gets more complicated. We're not going to use that namespace very much in this application, but we do want to set that so that we can group our classes accordingly. And then the next thing we do here is we set up our main method. We're in our program.cs file. Our main method will run when the application starts. And very simply, we just write out to the console that we started the load balancer simulation. We create a list of servers. These are the servers we're going to use to balance the load as requests come in. And then we have this round-robin class that we're creating, the load balancer object, will allow us to send requests to different servers as they come in. And then we have this for loop, which is simulating requests. You can think of this for loop goes from 0 to 9 or 10 requests. As each request come in, our round-robin load balancer object has a getNextServer method, and it will just find the next server available in line and then send the request to that. And that's what we're simulating here with our server.processRequest method. So in step 2, we're going to create the server class. And this is very simple. The servers just have an ID, so we know what server we're working with. We're going to create that ID variable. Then we have a public void method called processRequest. It doesn't return any value, that's why it's void. And all it does is just write out to the console which server we're processing the request on. And then, of course, we're using the ID here for whatever ID is being set for that server. That's the one that we're going to show on screen. That's the request that's being processed. In step 3, we're going to implement the round-robin load balancer, and here's where the real work is done. Our round-robin load balancer has a private variable called servers, and then a private variable called current index. Now we're setting that current index so we know which server we're currently working with and which is the next server we want to pass the traffic to. So if you think of a load balancer as distributing requests across multiple servers, round-robin just goes in order in a specific line. So if there's 3 servers, it's going to attempt to evenly divide the request among those 3 servers as requests come in. And then we have our round-robin load balancer method, which is what is run when the class is instantiated. You can see we're passing in our servers and we're setting our private variable servers to the value that we're passing into this method when we instantiate the class. Now we have our list of servers, so the getNextServer method knows what to work with. Finally, we have our getNextServer method that actually manages the requests and distributes them among the servers. We're using the server objects. That's the type of value that's returned when the method is called. We use server there. That's declared up here in our server class. We're returning that object back to the calling method. And then we set our server to the list of servers in the current index. Our server is whatever the current index is. And then we update our current index to current index plus 1. Again, just going in line there. We use the modulo operator to ensure that the server that we're trying to assign to current index is actually available among the number of servers that we have. And that modulo operator allows us to do that. It's always going to be 0, 1, or 2 in this context, and then because it's a 0-based array. And then we set that current index, and then we return the server back to the calling function. Whatever server we are using in our current index, that's the one that gets assigned to that particular request, and our current index gets updated. So when the next request comes in, it goes to the next server. Now let's test this and see how this works. We'll run our application. Our load balancer simulation has started, and then it just goes in line. It processes the request in server 1, 2, and 3, and then the next set of requests goes back to 1, it goes next to 2 to 3, and then it does that again, 1, 2, and 3. And then it finally ends on server 1 because we made 10 requests, and it goes through each of those servers in order. So that's a very simple load balancer technique. Round robin load balancers work really well in very specific contexts. When you get millions of requests a day, the round robin load balancer can not be as intelligent in the sense that if a server is overloaded or if a server goes down, sometimes it can't adjust, so you might need to add code to improve the round robin. But in terms of distributing load in a very specific tight context, this type of load balancer works really well. Well-designed apps remain fluid and responsive no matter the number of tasks they handle or the number of users they have. Asynchronous processing makes the level of performance possible, helping apps stay fast and scalable. In this video, we'll describe the concept of asynchronous processing and its importance for scalability. First, let's define asynchronous processing and examine how it allows apps to stay responsive while handling multiple tasks. Asynchronous processing enables an app to run tasks in the background, keeping it responsive to users. For instance, an app can sync data on a server in the background while users keep interacting with it, so the user experience feels faster and more seamless. Now that we've defined asynchronous processing, let's explore some of its elements, starting with thread blocking to gain a better understanding of how it works. If you think of a process as a single program, threads are independent sequences of execution within that process. Thread blocking occurs when a thread is forced to wait before it can proceed, usually because it is waiting for a resource to become available or another thread to complete its execution. This means the thread becomes inactive and can't proceed with the task until the awaited condition or event is fulfilled, potentially slowing down the user experience. Thread blocking is an inherently synchronous behavior, and asynchronous processing is specifically designed to limit thread blocking. For example, imagine waiting in line at a store where each person must check out before the next one steps up to the register. In the context of user experiences, users have to wait to interact with the app until it finishes processing a particular task, which can make the app feel sluggish. Now let's examine non-blocking processes, where tasks allow execution to continue immediately rather than forcing the app to wait. Non-blocking processes initiate an operation and then move on to the next task without waiting for the operation to finish. When the task completes, it notifies the system so it can process the result. By minimizing thread blocking, non-blocking processes help keep applications responsive, ensuring they can handle multiple operations efficiently. For example, think of ordering coffee at a cafe where you can browse your phone or talk to friends while waiting for your order to be ready. Similarly, a non-blocking process allows users to continue interacting with other app features while its tasks run in the background, keeping the experience smooth and performing well. Asynchronous processing also allows tasks like user saves or file uploads to run in the background while users continue interacting with the app. Allowing these core tasks to run transparently in the background enhances focus and interactivity and provides a more seamless user experience and workflow. Additionally, asynchronous API calls allow an app to retrieve data from external sources without freezing the user interface. For example, an app can fetch the latest weather updates or sync stock prices in the background while the user continues interacting with other features. To make handling asynchronous tasks easier, developers often use special tools called frameworks to help manage tasks effectively in the background. Asynchronous frameworks are programming tools or libraries designed to handle tasks independently of the main execution flow without blocking other operations. They use techniques like event loops, callbacks, and promises to efficiently manage operations like inputs and outputs operations, networking, or database queries.
enabling responsive and scalable applications. For example, the C# frameworks like await and async and the Task Parallel Library, or TPL, allow developers to manage multiple tasks at once, making apps more efficient without adding complex code. Now that we understand some of the core concepts of asynchronous processing, let's explore some of the specific benefits it provides, starting with increased responsiveness. Asynchronous processing improves responsiveness by allowing apps to handle multiple tasks with fewer delays, making the user experience feel quicker and more responsive. For example, a messaging app can load new messages in the background while the user types a reply. This ensures the app remains responsive to user input without waiting for the server to fetch messages. Asynchronous processing also enhances scalability by allowing apps to support more users by efficiently handling background tasks. For example, it can enable a chat app to handle numerous simultaneous conversations without slowing down even as more people join in. Asynchronous processing enables efficient resource use by optimizing memory and processing power so that even resource-heavy apps can perform smoothly. For example, a web server handling multiple client requests can use non-blocking inputs and outputs. Instead of waiting for one request to complete, the server processes other requests. This reduces idle time and more efficiently utilizes limited resources like CPU cycles and memory. In this video, you learned about the concept of asynchronous processing and its importance for scalability. Asynchronous processing enables developers to create apps that can keep up with user demand and reliably deliver seamless, scalable experiences every time. Using asynchronous methods can greatly improve the performance of your application by allowing tasks to run in the background and keeping your user interface active while those tasks are running. In this screencast, we're going to demonstrate how to implement asynchronous tasks using async and await in .NET Core. I've got a simple .NET application here. For this first version of this app, I'm going to just do a very simple structure to show how async tasks work. I've got a main method, which runs when the program starts, and then a perform task async method that we're going to call from our main method. The first thing to notice about these async tasks is first we're using the system.threading.tasks library to run these tasks. Both methods use the async and task keywords. That tells .NET that these are asynchronous tasks, and you have to include those keywords when you're setting up your methods. We're also using the await keyword, which will allow the program to run in the background. So it's waiting for that task to complete before it moves to the next line. The main method writes out to the console that the task is starting. It then calls into this perform task async, which just has a simple delay. And we're using the await keyword on that method as well. We're going to delay for 3 seconds. It's going to show processing the task, wait for 3 seconds, show that the task is completed, send control back to the main method where it will say task completed. This is just a very simple structure to show how async tasks are designed. I'm going to go ahead and run this. Those messages pop up on the screen. So starting task, it's then processing because it's in the perform task async method, waits for 3 seconds, writes out the task is finished, and then the task is completed. What's happening is that this perform task async is running in the background. We could do other things in our main method, which we'll show next. And then when that task is completed, it returns control back. Let's look at a different approach where we can actually see how we can interact with the app while it's running that asynchronous task in the background. I'm going to replace the main method and my perform task async method with 2 different methods. Still have the main method, but now we have a fetch data async. So this is going to simulate fetching data from an API, and we're going to delay for 2 seconds. In this call though, I'm going to actually be able to interact with the application by entering my name, and then it's going to produce a message, hello, and then whatever I enter in there while it's running this simulated delay in the background. So it's going to show how the application stays active. I can actually do things with the app while this is running. It's going to create that fetch data task object by calling fetch data async. I can interact with the app, and then it'll return back to the main method after that call is done. Let's run this.
See, I'm going to put in my name here. Because there's only 2 seconds, it returned back to the main method before I could actually complete the action, but it did allow me to complete the action. But it's running in the background. The 2 seconds was up before I hit enter. It wrote out the data retrieved successfully, and then I was able to hit enter, and then it wrote out hello, Paul. So let's increase that amount of time that the task takes. Let's run that again. And now I'll put in my name. And then it says, hello, Paul, and then it will complete the task and write out that message, data retrieved successfully. That's an example of how, even though it's running in the background, we can still interact with this console application. If we're going to look at a different approach now, I'm going to do the same thing and replace the code in our application with some other methods here. In our main method, we're going to call out to this get message async. This is just another delay for 1.5 seconds. Instead of writing out to the console, it's going to return a value. And that value is hello from async world. It was just a string. In this main method, this time we have this message task dot continue with. So it's still calling out to that get message async method, creating that message task object, but it's going to return a value. And when that value is returned, it will write out message received, hello from async world. But notice that it's going to make this call, and because it's working in the background, it's not going to produce this message received until that 1.5 second delay is complete. However, it will write out to the console doing other work in the meantime. So essentially registers this call with the framework, writes out this message, and then when that get message async call is complete, the delay is done, it will actually run this line, console.writeLine message received. This functions like a callback. When the task is complete, then you can run some other code. Let's run this one. It's fetching message, and then it goes to doing other work. And then when the delay is up, then we get our message received, hello from async world. This is a very powerful way to allow you to do work in the background while your program continues to operate. You can ask for user input, you can read from a database, you can do anything you want while that task is running in the background. You think about that get message async as doing a complex calculation or looking up something from a database or getting data from an API call. The last thing I want to demonstrate is error handling in asynchronous code. So we're going to replace our application code again. And trapping errors in async code is very similar to trapping errors in other types of code. We're simply going to wrap our async calls in a try-catch block. This is still an async task method, fetch data with error async. We're still using await in our call, but when we throw the exception, it's just going to be caught in this catch block after the exception is thrown, even though this is an async task. It operates very similar to just general C# code, but we can use error trapping in our async code as well. It starts the API request, then it says fetching data, which is here, delays for 2 seconds. We throw this fake network failure exception, which is caught by this error network failure. And then it returns the control back to the calling method, console.writeLine execution continued after handling error. Those are different ways that you can implement async tasks in a .NET application using async task keywords and then the await keyword when you're working with specific methods within the async task. When working with back-end applications, using asynchronous processing can really speed things up and make the application more performant. In this lab, we're going to apply asynchronous processing to optimize a back-end application. In step 1, you're setting up the .NET Core project. You're going to use the command makedir to make a directory, and you're going to use async demo as the name. And then this & command will just switch to that location. That's the command you would use since we already have the application up. I'm not going to repeat that, but this is the command you would use to create that directory. And then you're going to use the .NET new command to create that application itself. You would type .NET new and then a console application. And then .NET will create that application in the folder that you're in. By creating that folder async demo and switching to that folder, then you can create a new application right in that folder. In step 2, you're going to implement the application code itself. We're going to implement some async processing. I have the application here already, and we're going to make sure that we have the system.threading.tasks library in our using statements above so that we can use that library for our asynchronous processing. And then we have our main method under the program class. This is the method that runs when the application starts up. We're using async and task keywords with our main method. That tells the .NET framework that this is an async operation and that we can run asynchronous code within it. We have to make sure that those keywords are in place. We have a console write line that just says starting API request, which is simulating a request out to an API. The line where we're actually doing the asynchronous work is in that next line. We're setting the string variable result to the result of the fetch data async method. We're passing in single request into that method. Also, we're using the await keyword here, which tells the application that this is a background process and that we need to wait for it to complete before we run the next line. So using that await keyword will allow us to do that. The fetch data async method. This is a async task method as well. Returns a string value. And we're going to use the same name, fetch data async, that we used in our await call, fetch data async. So these just need to be the same. We're calling the method and we're putting the same method name, passing in that string request name. This just does a simple task.delay, also using the await keyword. Waits for 2 seconds to simulate a call out to an API, and then returns API request completed. And that will give us what we need. So let's run this. It starts the API request, and then the API request is completed. And that's what you need to do to complete step 2. In step 3, we're going to handle multiple asynchronous requests. Let's go down to this method. Here we're going to actually run 3 tasks, fetch data async. We're going to do them all at the same time. And because this is an asynchronous method, we can run these at exactly the same time, and they all run as separate processes in the background. Then we're going to get the results back in this string array. Again, we're using the wait keyword, and we're using the task.whenAll method to wait for all the tasks to complete. When all the tasks are done, then the next line will be run. This whenAll just is a method that we can use to wait for all the tasks to finish. In a real-world scenario, you might be making 3 different API calls, or an API call and a database call and something else. And they might all take different times to complete. So the API call might take a little longer than a database lookup. But as you're running these tasks in the background, you may not want to move on to the next task until everything's back. For example, if you're looking up something from an API and then want to verify that against data in your database, you might run those as background tasks concurrently. And then when both have completed, then you'll process the data to do the comparison that you need to do. In this case, we're simulating that by just calling that fetch data async, which will run for 2 seconds each. Then we'll bring the results back. And in our console.write line, we're going to show the number of tasks completed. Now, the fact that these are 3 different tasks running at the same time, we should only see 3 results each time because we're not going to see any results until all the tasks are done. So I'm going to comment out these 2 lines, and then we'll run our handle multiple requests async, and we'll go ahead and run that. The number of completed requests is 3. We sent those 3 requests to fetch data async, and we got them all back and then ran the console write line. Those are ways that you can implement asynchronous processing in a .NET application, and this lab demonstrated how to do that. Understanding how data is structured and processed is essential for building scalable and high-performing back-end systems. Trees and graphs provide powerful ways to organize and navigate complex relationships, while techniques like load balancing and asynchronous processing ensure efficiency under heavy workloads. We began by examining tree structures such as binary trees, binary search trees, and balanced trees, exploring how they store and organize hierarchical data to support faster retrieval and processing. Next, we developed tree traversal algorithms to efficiently access and manipulate tree-based data structures. This ensures seamless data processing in back-end applications. Then we explored fundamental graph theory concepts, uncovering how graphs model relationships and provide solutions for complex connectivity challenges in real-world applications.
After that, we applied load balancing techniques to evenly distribute workloads across backend systems, improving performance and ensuring seamless scalability. Finally, we utilized asynchronous processing methods to enhance system responsiveness and support the scalability needed for high-demand applications. Mastering data structures, graph theory, and optimization techniques is essential for building efficient and scalable backend systems. Effectively applying these concepts will enhance data processing, improve performance, and ensure seamless system operations under heavy workloads. Welcome to Advanced Algorithms and Problem Solving. In this module, you'll dive deep into powerful algorithmic techniques that drive efficient backend development. From mastering dynamic programming and greedy algorithms to optimizing search operations with hashing, you'll gain the skills to tackle complex challenges. You'll also apply your knowledge in a hands-on performance optimization project and analyze algorithmic trade-offs to make informed development decisions. We will begin by exploring dynamic programming and greedy algorithms, and understanding how they efficiently solve complex optimization problems. Through real-world examples, we'll see when to apply each approach and how they differ in decision-making strategies. Next, we will implement dynamic programming algorithms to break down problems into overlapping subproblems and solve them efficiently. We will practice writing code to reinforce key techniques like memoization and tabulation. Then we will examine hashing and hash tables, uncovering their role in optimizing search operations within backend systems. By studying their structure and applications, we will learn how to enhance data retrieval and overall system performance. After that, we'll tackle a performance optimization capstone project applying advanced algorithms and AI-driven tools like Copilot to refine backend efficiency. This hands-on experience will strengthen our problem-solving skills in real-world scenarios. Finally, we will assess algorithmic trade-offs, analyzing different approaches in backend development. We will develop the critical thinking needed to choose the best solutions for diverse challenges by comparing efficiency, scalability, and resource consumption. By the end of this module, you'll be equipped to build scalable, high-performance backend systems using advanced problem-solving strategies. In backend development, solving complex problems efficiently can make the difference between a fast, responsive application and a sluggish one. Dynamic programming is a key optimization technique that helps tackle complex problems by breaking them down into smaller parts and reusing solutions to save time. In this video, we'll explain the concept of dynamic programming and how it solves complex backend problems through overlapping subproblems. To begin, let's define dynamic programming and explore why it's essential. Dynamic programming is a technique for solving complex problems by breaking them down into smaller, manageable parts and storing results to improve efficiency and avoid repeating calculations. For example, imagine a navigation system finding the shortest route between locations. Dynamic programming can simplify this by solving and storing shorter paths between key points. When these paths are needed again, the program can pull from stored results instead of recalculating them, making the overall process faster and more efficient. Now that we've defined dynamic programming, let's go through the key steps involved in using dynamic programming to solve complex problems. Dynamic programming starts by breaking down a complex problem into smaller, simpler subproblems that are easy to solve. These subproblems often recur, meaning the same smaller problems are solved multiple times during computation. Dynamic programming identifies and solves each repeated subproblem only once, speeding up the computation process by avoiding duplicate work. For example, one of the common repeatable processes in building a house involves putting in walls. While multiple walls exist in a single house, similar rooms will require a similar wall design. To make the process more efficient, the same wall construction method is reused again and again, rather than starting from scratch each time. This reuse of completed components optimizes the process, much like dynamic programming reuses solutions to overlapping subproblems. Now that we've defined dynamic programming, let's explore a technique called memoization, which plays a key role in it. Memoization is an optimization technique where the results of expensive function calls are stored or cached so they can be reused when the same inputs occur again, avoiding redundant calculations and improving performance. Memoization works in the same way as data caching. If something is used frequently, we save it temporarily to avoid reloading or recalculating it. It also supports dynamic programming by making it faster and more efficient. Since memoization is essential for optimizing repeated computations, let's now explore how it is applied within dynamic programming. In dynamic programming, we also use memoization to store each result in a table or cache, allowing us to reuse previously computed values and avoid redundant calculations. In our construction example above, this would be like creating a blueprint for a specific wall design. Once you've built one wall using that blueprint, you can save it and reuse it whenever you need the same design for other parts of the house. This avoids rethinking or recalculating how to build the wall each time, saving effort and time. Similarly, in memoization, solutions to subproblems are stored and reused instead of recalculating them repeatedly. Finally, dynamic programming combines the stored results from each subproblem to solve the main problem more efficiently. The solution is built up by assembling each stored result without unnecessary calculations. For example, consider packing a bag for regular weekend hikes. The goal is to maximize the utility of items that will fit into a limited space. By tracking different configurations for each item and weighting combinations, we avoid revisiting configurations we've already solved. This allows us to optimize the packing process by assembling the best combination of items based on our needs. Now that we have explored the key steps of dynamic programming, let's explore how it applies in different use cases, starting with the Fibonacci sequence. The Fibonacci sequence is a series of numbers starting with 0 and 1, where each number is the sum of the two preceding ones. The sequence follows this pattern: 0, 1, 1, 2, 3, 5, 8, 13, etc. Each new term is calculated by adding the previous two terms. This sequence appears in many natural and computational contexts, like modeling population growth and financial forecasting. Dynamic programming optimizes the Fibonacci process by breaking the problem into smaller, overlapping subproblems using memoization to store the results of previously computed Fibonacci numbers in a table or cache. It then reuses them to calculate larger numbers in the sequence without redundant calculations. In this example, the Fibonacci sequence is calculated using recursion, starting from F4 and breaking it down into smaller Fibonacci numbers. The red highlighted F2 appears more than once, showing repeated calculations which dynamic programming can avoid by storing and reusing previous results. Dynamic programming also enhances text processing tasks like finding similarities between sequences. One such application is the longest common subsequence, or LCS. The longest common subsequence identifies the longest sequence of characters that appear in two strings in the same order, though not always consecutively. It is widely used in text comparison, such as detecting similarities between DNA sequences or helping search engines find relevant documents. Dynamic programming breaks down LCS problems into smaller overlapping subproblems, storing partial results for reuse to speed up comparisons and avoid redundant calculations. In search engines, dynamic programming is often used to find the longest common sequence between a user's search query and a document title to measure their similarity. For example, if the user query is cat and the document title is catalog, the LCS algorithm compares the characters sequentially and identifies cat as the longest sequence that appears in order with that title. This allows the search engine to rank catalog higher because it contains the query as a subsequence, even if the characters are not next to each other. This method helps improve search relevance by identifying meaningful matches between user queries and content. In this video, you learned about the concept of dynamic programming and how it solves complex back-end problems through overlapping subproblems. Dynamic programming is critical in back-end applications because it allows for the efficient solving of complex problems by breaking them down into smaller overlapping subproblems and storing their solutions to avoid redundant calculations.
In this screencast, we're going to demonstrate how greedy algorithms work by making locally optimal decisions. A decision is locally optimal when the decisions are made at each step without regard for future consequences. So it's not an all things considered approach. There may be a lot of other things that you want to consider when you're making decisions on how to sort or rate certain tasks. Greedy algorithms just make decisions without thinking ahead about what's going to come after the decision it's making. In this application, we have a class called task where we set up the name, deadline, and reward, and we're just defining that object here. And then in our program, we have a greedy task scheduler method into which we're passing tasks. And we'll go through this method in just a moment. And then in our main method, we're going to define our tasks. We've got 4 tasks here. We've got the name of the task. We've got a time slot that the task can fit into, and a reward number. So the higher the number, the more reward you get for completing that task. We've got 4 here, each with a different time slot. Task A and task C can fit into time slot 2, and task B and task D can fit into time slot 1. We're only going to get 2 tasks back because we're only allowed to keep 1 task per time slot. And that's how the greedy algorithm will take care of it. So then we instantiate our greedy task scheduler object using scheduled tasks, and then write out the tasks that the greedy algorithm will produce. In our greedy task scheduler, the first thing we're going to do is sort by reward. And this is where the greedy task algorithm really shows up, right? So we're sorting the tasks by reward. So we're going to have the highest reward at the top, the lowest reward at the bottom. And then it's going to go through and filter and find out which task to put in each time slot. There's going to be 1 for time slot 2 and 1 for time slot 1. We create 2 new objects, a schedule and a time slot object that we're going to fill with our tasks. And then we have a for each loop for each task in the list. So there's going to be 4. And then we've got a for loop that will actually fill and populate that task object. I put a breakpoint here, and I'm going to run this in the debugger and set some watches so that we can see what's going to happen as we're working through those. So we've got a task object here that we're watching, and then the time object that we're watching. When we sorted our tasks, we went from 100 down to 20. Our list is going to be 100, 70, 50, and then 20. So it's going to be task A, task D, task B, and task C. Our first task is in fact task A because it was weighted the highest, and that's what we sorted by. So it's going to be the highest one in the list. And it's at time slot 2. The next line of code checks to see if a time slot has been filled yet. If the time slots contains an item for slot 2, then it will move on. If it doesn't, which in this case it doesn't because it's the first time through, we're going to add our time slot, which is 2, and then our task, which is task A. And then we go back up to our for each, and we work through this again. We've got now our task D because that was second in the list based on our sort. And it's also at time slot 1. Because there's no entry for time slot 1 yet, then it will also add that task. Now we have our 2 tasks added. And this is what the greedy algorithm has done. It's looked at the ones with the highest reward and then filled the time slot as it just goes down that list. It's not considering anything else other than that reward as the highest priority. It's skipping over these other tasks because time slot 1 and time slot 2 have already been filled. There's nothing else to add. I'm going to go ahead and run this, and then we can see our output. So now we have task A, deadline is 2, but the reward is higher, so that came first. And task D, which is in slot 1, and that reward was 70. Skipped over task B and task C, because even though they had the time slots 1 and 2, the reward was lower, so they didn't get added to the list. Greedy algorithms work really well for scenarios like that, where you're just considering that one without looking ahead or thinking about other considerations. One area where greedy algorithms really shine is in mapping a path from one point to another. So you can think of a mapping app or a network app, and you're trying to find the quickest and most efficient route from a starting point to an end point. I have this graph.cs file. This is using what's called Dijkstra's algorithm, which is a popular mapping algorithm. I'm not going to go through the entire algorithm here, but we're going to pass in points and edges for a mapping system. And this algorithm is going to sort that out. It's going to figure out the quickest path from one point to another. I'm going to go back to my program, and I'm going to paste in some code that will instantiate that graph and then call the Dijkstra algorithm to figure out the quickest path through those items. We've got our graph object here, and we're going to add items to it. There's relationships set here. A to B, A to C, B to C, B to D, C to D. We want to go from A and end up at D. And Dijkstra's algorithm is going to figure out which of these relationships creates the quickest path through that set of edges. We're passing in A as the starting point. That's where we want to begin, and we want to go to D at the end. And it's going to figure out the shortest path to get us there. I'm going to run this in the terminal to see how this greedy algorithm works. It went from A to D on the left-hand side, and then these are the points that it uses to get to that. It skipped over 2. Started at 0, went to 1, skipped to 3 because that's the shortest path to get from B to C, and then goes from C to D using 3 to 4. That is how the greedy algorithm determined is the quickest path through all of these nodes in the items that we passed in. Dijkstra's algorithm is a great example of a greedy algorithm. It's trying to find the fastest path. If you were thinking about a mapping application or a network application, it doesn't consider anything else. It's just looking for the points that are the closest to one another to get from one point to the other. In dynamic programming, you might consider latency, you might consider traffic in a mapping app, for example. This application doesn't. It just figures out the quickest way to get from point A to point D. These are two illustrations of a greedy algorithm and how they are really efficient in terms of finding the highest order thing that you're looking for or the quickest path through a network or a map. But in some scenarios, you may want to consider other things. And this is where greedy algorithms wouldn't be a great application. You'd want to use more of a dynamic programming approach. But greedy algorithms are really good for a certain context if you want fast and efficient sorting. Efficient back-end systems rely on smart techniques to handle growing demands, optimize performance, and prevent overload. Dynamic programming enhances system efficiency by storing and reusing important data, reducing redundant computations. In this video, we'll identify practical coding scenarios for dynamic programming in back-end systems. To begin, let's explore concepts of dynamic programming in back-end applications, starting with API rate limiting. API rate limiting limits how many API requests a user can make within a certain time period. By storing information about each request, the system can quickly check if a user has reached their limit without recalculating each time. This ensures fair usage, prevents abuse, and protects system resources by restricting the number of requests a user or client can make within a specific time frame. Imagine a web app that controls how often users can request data. API rate limiting is implemented to ensure fair usage and protect the server from being overwhelmed. For example, users may be allowed up to 100 requests per minute. When a user sends a request, the system checks a counter associated with their API key or IP address. This counter tracks the number of requests the user has made within the current time window. If the user exceeds the limit, the server denies further requests and responds with a 429 too-many requests error, often including information about when the limit will reset. The counter resets after the time window, allowing users to resume making requests. This mechanism ensures resources are shared equitably, preventing abuse and helping maintain consistent performance for all users. Next, let's examine cache optimization, which stores frequently used data so the system can retrieve it instantly. Cache optimization is the process of improving the efficiency of a system by storing frequently accessed data in a cache for faster retrieval. It applies approaches like memoization and web page caching to store and reuse the results of expensive operations, reducing redundant computations and improving system performance. For example, consider a website where users often search for popular products. Instead of querying the database each time, the results for frequently searched products are stored in a cache, such as in-memory storage like Redis. When another user searches for the same product, the cache results are retrieved instantly, bypassing the need for a database query. This approach not only reduces server load, but also significantly speeds up response times, as accessing cache data is much faster than querying the database. Additionally, the cache can be periodically updated to ensure data remains accurate, balancing efficiency and freshness. This enhances scalability and improves the user experience, especially during peak traffic times.
Finally, let's explore scheduling algorithms, which arrange tasks to optimize resource utilization, meet deadlines, and improve overall system efficiency. Scheduling algorithms are methods used to determine the order or allocation of tasks or processes to resources, such as CPU and memory, in a way that optimizes specific objectives like minimizing wait time, maximizing throughput, or meeting deadlines. These algorithms store data like task queues, resource states, and priorities to make informed decisions. By reusing historical and intermediate data, they adapt dynamically, reduce redundancy, and balance workloads efficiently. For example, an email server processing a large volume of emails uses a scheduling algorithm to handle tasks by organizing emails into a queue based on factors like priority, size, and delivery deadlines. The algorithm continuously monitors server resources such as bandwidth, CPU usage, and memory availability to decide which emails to process and send first. High priority or time-sensitive emails are sent promptly, while lower priority ones are scheduled when resources are less constrained. By storing and updating data about task statuses and resource availability, the algorithm avoids redundancies, ensures fair resource distribution, and prevents server overload. This ensures timely delivery and maintains consistent performance even during high traffic. In this video, you learned how to identify practical coding scenarios for dynamic programming in back-end systems. Each of these dynamic programming techniques, rate limiting, caching, and scheduling, helps back-end systems be smarter and more efficient by reusing stored information to handle tasks quickly and reliably. Memoization is the ability of an application to remember commonly used or previously used calculations or data without having to recalculate or go back to a database or an API call to get that data. It's a form of caching where the application does keep those items in memory and then reuses them as needed. In this screencast, we're going to demonstrate how to implement memoization for cache optimization in .NET Core. So in this application, I've got a dictionary that I'm creating at the top called memo, and then I've got a Fibonacci method, and this just does a Fibonacci calculation. And in this Fibonacci calculation, we're actually going to save the calculation to the memo at a specific point. If that memo does contain that calculation, then we're going to reuse it. Otherwise, we calculate it in the method. This main method, which runs when the application runs, we're passing in 40. So that's the calculation we want to do. And we're passing it into that method, and it's just going to do the calculation and then store it. Now, the first time through, it will do the calculation because it doesn't have anything in memory. So here's where we have that memoization function here in the if statement. If the memo contains the key n, which is what we're passing in, then it's going to return whatever's in the memo. And that's where it doesn't have to do the Fibonacci calculation again. If that's not true, then it calculates the Fibonacci sequence here, stores it in the memo, the dictionary that we created above, and then returns the result. This is a very simple example of how you can use a dictionary as a memoization technique to save your program from having to recalculate. Now, this is a very simple calculation. You can imagine that this could be something like an API call, a database lookup, or a very complex calculation, where once it's done, if it's a repetitive calculation or a repetitive call, you can store it in memory so that you don't have to do that again and save the time and effort of having to make that call or do that calculation. Let's put a breakpoint here, and we're going to run this in the debugger so we can see what this looks like. It will stop at this if statement. The memo does not contain n. The n is 40, that's what we're turning in. If the dictionary did contain that item, it would return immediately, but we're going to skip over that because it does need to do the calculation. Calculated the Fibonacci sequence, and then it goes through again and checks it to see if it's in the memo. You can see it's doing that calculation here again and again, which is what we would expect. And then let me set another breakpoint. Take this one off and we'll run it. This is the result of that calculation, and then it's going to return it to the calling program.
The Fibonacci of 40 is this sequence here, and that's what we have now saved in the memo. If we were to call that again, it would skip over the calculation and just return the value that was in the memo. And so that's a version of memoization. Now, as we were stepping through, you can see it had to go through that sequence. It had to calculate that sequence over and over again. On a computer like this with that simple calculation, it would seem almost instantaneous, but there's lots of scenarios where that process would take much longer. Storing it in memory would be a much better approach. Now, what I'm going to do to illustrate how this works is to create another console write line. It's going to pull from this line here, from the memo contains. We have to do this twice because it has to stay in memory. We're not writing out to persistent storage for this example. Let's put a breakpoint here, and then we'll step into the code when it gets to this breakpoint. Let's run this again. We've got our first Fibonacci sequence, and now let's go ahead and step into the method again. It should evaluate here. If memo contains n, it should contain n, so it should return immediately. It returned. It didn't have to do the calculation again. And then it writes out to the console, second Fibonacci of 40. So that's the example of how memoization works in this context. Now let's work with an API call. We're going to simulate an API cache using this memoization approach. I'm going to go ahead and stop the debugger. And I'm going to replace my program with the simulated API call. Here we have a fetch data method. We're creating a dictionary again with a cache. And we have a fetch data method. We're going to evaluate the cache to see if it contains the query that we're looking for. If it does contain the query that we're looking for, we're going to return the cached value for that query. And if it doesn't, then we're going to pretend like we're fetching data from the sleep for 2 seconds just to simulate that call, and then return the data for that query. Here we have two of the same query, user:123, twice. The first time through should be data for user123. The second time should be return cache result for user123. And then the third should be data for product 456. It's using the cache data the second time because we're sending in the identical query. And then it's going to have to rerun that API call for product 456. Let's run this in the terminal. There it's waiting for 2 seconds. And then it goes back and says data for user123 because I got it from the cache. Return data for user123. And then it's going to fetch data from the API for product 456 and then return the data for product 456. So that second result was much quicker because it didn't have to sleep for 2 seconds while it made the simulated API call. It just returned data from the cache. Now, one impact of using memoization in this way is that you do take up memory. So you have to have a computer system that can actually be able to store the data that you need to store in the cache. You can run into resource issues like memory, and if you're storing it to disk, it could cause issues with the disk space as well. So you got to think through those kinds of things. But in general, memoization techniques and caching always improves performance and is a good option when you're thinking about how to architect and design your application. In this lab, we're going to implement a dynamic programming algorithm to solve a resource scheduling problem in .NET Core. I've got a console app here, and we're going to use the knapsack model to figure out how to fill variables. In step 1, we're just setting up the application. So you're going to use .NET new console -n scheduling app, and then change into that directory, cd scheduling app, and then type code space period to open up the app in its own instance. In step 2, we're going to implement the recursive knapsack algorithm, which is what we see on screen now. We've got our knapsack method, and we're passing in values, weights, capacity, and then an integer n. And what we're doing in this is we're going to first check to see if n is equal to 0 or if capacity is equal to 0. If either is true, we're going to return 0 from whatever method called this method. Just return back from that function. If either is not 0, then we're going to check here for whether the weights of n minus 1, because it's a zero-based array, is less than or equal to the capacity. We're going to run this math.max function, and we're also going to run it again recursively, passing in values into the knapsack again. We're actually getting another value and returning the value for that as we call that. We're running it a couple of times here. We're passing in capacity minus weights n minus 1, and then capacity with n minus 1. And we're doing n minus 1 both times because it's a zero-based array. This is our regular knapsack function. And then in step 3, we're going to apply a memoization to the knapsack function. In order to do that, I'm going to add a line of code. We're going to create a dictionary called memo, and that's just going to be a dictionary of string and int objects. We're going to instantiate that at the top of our program. And then I've got another method here, knapsack memo. And here we're just going to store calculations so that we don't have to recalculate if we've already done the calculation. I've got another method here called knapsack memo. And here we're going to use memoization, which is just storing pre-calculated values in that dictionary object that we created above. We're going to store them, and then if the result of that calculation is already in there, we're not going to recalculate, which should save time as we run the application. So the first thing we're going to check is if the memo contains the key that we're using here. And the key is just made up of the number, a dash, and then capacity. So we're checking to see if that's in there. If it is, then we just return the value that's at memo at the key index. If not, then we again check to see if n is equal to 0 or if capacity is equal to 0. If either is true, then we return 0, and then otherwise we just run through essentially the same algorithm that we did in the original knapsack method, except here we're going to also add the memo with the index of key to the result of knapsack memo, just so we can store that, then use that again in the future when we do this evaluation up here at the top. And then otherwise we're going to return memo.key back to the calling function. These are two different ways that you can implement dynamic programming. Dynamic programming does allow you to adjust to data that's coming in. Using memoization can actually improve the performance of a dynamic program like the one we just looked at.
Efficient data management is at the core of modern back-end applications, ensuring fast and secure access to information. One key technique used to achieve this is hashing, a method that transforms data into fixed-size, unique codes for quick searches. In this video, we'll describe the mechanics of hashing and how it enables fast searches in back-end applications. To begin, let's explore some key concepts of hashing, starting with examining what it is. Hashing is the process of converting data, like usernames or passwords, into a unique fixed-size code or hash for quick retrieval. It works by applying a mathematical function known as a hash function, which converts input data of any size into a fixed-size value or hash. This hash acts as a unique identifier for the data, allowing it to be quickly located in structures like hash tables or caches. Hashing makes processes like data retrieval, authentication, and indexing highly efficient. For example, instead of storing a password directly, the system stores a version that has been securely hashed using an algorithm. When a user logs in, the system takes the entered password, applies the same hashing algorithm, and compares the result to the stored hash value. If they match, the password is verified. This method also protects sensitive data. Even if someone gains access to the stored values, they cannot easily reverse the encoding to retrieve the original password. Hashing converts data into unique codes, but we also need to be able to store and organize those codes efficiently for quick access, which is where hash tables come in. A hash table is a data structure that organizes data by its hash for fast, efficient access. A hash table stores data as key value pairs, meaning each piece of data has a unique key that points to its location. This setup allows fast retrieval by searching the hash rather than searching through every entry. For example, a hash table can store active session data by hashing each session ID and using the resulting value as a key to map to the associated session information, like user preferences or authentication tokens. When a user returns, their session ID is hashed again, and the hash table is queried to quickly locate and retrieve the corresponding session data. This ensures efficient access, reduces search times, and supports a seamless user experience, even in systems handling a large number of concurrent sessions. In some cases, different pieces of data produce the same hash, which can cause a collision, where multiple entries are mapped to the same location in the hash table. And this is when collision handling keeps data organized. Collision handling is the process of resolving situations where multiple pieces of data produce the same hash value and are mapped to the same location in a hash table, causing them to collide. Collision handling is achieved through techniques such as chaining, where colliding entries are stored in a linked list or similar structure at the same location or opening address, where the table is searched for the next available slot based on a specific probing strategy. By resolving collisions efficiently, these methods maintain the hash table's performance and ensure data integrity. Now let's explore the three most common collision handling techniques, beginning with chaining. Chaining is a collision handling technique where multiple entries that hash to the same location are stored together in a linked list or similar data structure. When retrieving data, the hash table searches through the list at that location to find the correct value, ensuring accurate and efficient access even in cases of collisions. Another collision handling technique is open addressing, which works well when the hash table has sufficient empty space. Open addressing involves finding an alternative empty slot in the hash table using methods like linear probing or quadratic probing when a collision occurs. This approach ensures that all entries remain within the table and collisions are resolved by relocating new entries to open slots, maintaining efficient data storage and retrieval. Finally, collision handling can employ double hashing. Double hashing is one of the most effective and commonly used collision handling techniques used in high-performance hash tables. Double hashing involves using a secondary hash function to determine the next slot when a collision occurs. It calculates a unique step size for each key, allowing the system to probe different slots in a more distributed manner. When a collision happens, the secondary hash function helps ensure that entries are spread more evenly across the table, avoiding repeated collisions at nearby slots. This approach improves efficiency and keeps retrieval times predictable, even as the table becomes more populated. Now that we understand how hashing optimizes backend systems, let's explore a few examples of how it's applied in real-world scenarios. One of the scenarios where hashing can be useful is session management. Recall that session management ensures that a user's interactions with an application are tracked and consistent. The session ID is the core of session management. It's a unique identifier that links a user to their session data, such as login status or preferences. However, session IDs are vulnerable to attacks like hijacking or tampering, and hashing is a key technique for enhancing their security. Hashing transforms session IDs into fixed-length, irreversible values, making it nearly impossible for attackers to reverse engineer the original ID, even if they intercept the data. Another common hashing scenario involves caching. Caching and hashing work together to optimize data retrieval and enhance web application performance. Caching temporarily stores frequently accessed data to reduce latency and server load, while hashing ensures efficient data identification and retrieval within the cache. When caching, a hash function is often used to generate a unique key for every data entry. This hash key allows the system to quickly locate cached items without scanning the entire dataset. Lastly, password hashing is a security technique that protects user passwords by converting them into irreversible fixed-length hash values. Instead of storing plain text passwords, systems store these hashed values, ensuring that even if a database is breached, the actual passwords remain secure. When a user logs in, the entire password is hashed using the same algorithm, and the resulting hash is compared to the stored value. If they match, access is granted. In this video, you learned about the mechanics of hashing and how it enables fast searches in backend applications. Hashing allows for fast data retrieval by mapping data to unique hash codes, enabling constant time access to values. This technique improves efficiency in searching, indexing, and quickly searching data in large datasets or systems.
can generally speed up searches by using a hash table. A hash table is a way to store and retrieve data, and it can really improve performance when you're looking items up. In this lab, we're going to demonstrate how to implement a hash table in .NET Core for fast lookups. In step 1, we're simply setting up our application. We are calling this application hash table demo. We use the .NET new console keywords to create that application. In step 2, we're going to implement the hash table class, which is what we have here. I've got a hashtable.cs file, and I have a public class passing in 2 variables, k and b. Inside that class, we're going to instantiate 2 member variables, a private variable, it's also constant, and an int. We're calling that size and setting that to 10. And then we're creating a private linked list, which uses the key value pair type. It's an array, and we're calling that buckets. And then the method that runs, the hash table method, that's the same name as our class. This runs when the class is instantiated. It's going to create an empty table. So that buckets, think of it as a table. And it's going to use the linked list type. And it's going to create a number of records based on that size variable that we created earlier. So it's essentially going to create a new array that's able to hold 10 records. And then we iterate through the size variable. So we iterate over 1 to 10. And then for each item in our buckets array, we add a new linked list type item there so that we're creating those empty buckets. When this is finished running, we'll have an empty array essentially called buckets that we can insert data into. And then we have a get bucket index. This is where the hashing occurs. So we're going to create an index for each of the items that we want to insert. What we're doing here is using math.abs, which returns a whole number rather than a negative number. And then we're using the get hash code method against key, which is a part of the .NET Framework's object library. And that's just going to create a hash code. And then we're using the modulo operator against the size variable to produce a single number between 1 and 10. We're figuring out where to put items into that buckets array. And so we're getting a single number back between 1 and 10 that will help us to know where to insert the item into the hash table. And this get hash code method using the modulo operator and size will give us that index number. And then we have an add method where we're adding items to the buckets. We get our index using that method we just looked at, get bucket index. And then we set our bucket we want to add the items to using buckets.index. So now we have a single bucket that we're going to place items into. And then we're iterating over each pair in bucket. We're just checking to make sure we don't overwrite any items. And this avoids collisions when we're trying to add items to our hash table. We're going to throw an exception. Otherwise, we're going to add the key value pair that we passed in to that row in our hash table. And then we have a get method that will allow us to get items out of the hash table. We're getting our index here. We're going to get the bucket index key. Always should return the same number because we're using it against the key value that we're passing in. And then we're going to set our bucket again. And then we're looking for pair key dot equals against that key that we passed in. But if that occurs, then we know that we have the right item and we'll return the value from that key. So you can think of it as a row, and we look up the key in one column and then return the value in the other column. And then otherwise we throw an exception that the key wasn't found. So that's our hash table method. In our program, we're instantiating the hash table. We're going to place that in the hash table variable. And then we use the add method on that object that we just created, hash table.add. We're going to add 3 records, Alice with an age of 25, Bob with an age of 30, and Charlie with an age of 35. And then we simply write out to the console the different ages. So we're going to use that hash table.get method that we just looked at. We're going to pass in the key. It's going to look up the items and then return the age. And then in step 4, we're going to test the hash table implementation. So now we're going to retrieve values. So let's go ahead and run this. We passed in Alice, Bob, and Charlie. We looked up the age for Alice and got 25, which is what we expect because that's what we passed in. And the same for Bob. We get 30 back. Our code is successfully able to add items to the hash table, and we also can retrieve items from the hash table. Using a hash table makes lookups very quick, and this code ensures that we can handle collisions so that we don't overwrite any data as we add items to the table.
Imagine a tool that doesn't just support your coding, but actively enhances performance, speeding up processes, optimizing data access, and reducing errors as you work. With its AI-driven insights, Copilot offers real-time suggestions that make applications smoother, faster, and more efficient. In this video, we'll describe how Copilot's LLM assists in performance optimizations across code and databases. To begin, let's explore how to use Copilot for optimization, starting with its AI-powered assistant, Copilot. Copilot is an AI assistant designed to enhance your productivity. It provides code suggestions, optimizes database queries, and detects potential issues across your workflows. As you code, Copilot integrates directly into your environment, offering real-time insights that help you identify inefficiencies and implement improvements without interrupting your flow. Now that we understand what Copilot does, let's examine how it uses performance metrics to pinpoint opportunities for optimization. These metrics highlight where your code and databases can be made faster and more efficient. Performance metrics are key indicators of how well your code and databases perform. These include response time, memory usage, and query execution speed. By analyzing these metrics, we can identify inefficiencies, allowing for targeted optimizations that make applications faster and more resource efficient. One of Copilot's strengths is suggesting code refactoring. This helps you improve clarity, streamline performance, and follow best practices for more efficient, maintainable code. These optimizations allow applications to load data quickly, enhancing the user experience, especially when handling large volumes of information. For example, imagine you're retrieving user data from a database, but the query is slow. Copilot might suggest improving the query's indexing and reorganizing the data so it can be retrieved faster. This reduces memory use and speeds up response time, optimizing your data for quick access. By focusing on these optimizations, Copilot helps ensure that your applications perform well and provide a smooth user experience, even when dealing with large data sets. Beyond code and database structure, Copilot can recommend algorithm enhancements for complex tasks. Suggesting more efficient approaches helps you process data faster while conserving resources. For example, consider a basic search function that struggles with a large data set. Copilot might suggest switching to a more efficient search algorithm, significantly reducing processing time. In this video, you learned how Copilot's LLM assists in performance optimization across code and databases. With Copilot's guidance, you can reorganize data for better performance and optimize your code for speed, highlighting the transformative impact of AI-driven optimizations. In this lab, we're going to implement Copilot's LLM-generated recommendations to optimize both code and database queries in a backend system. In this application, this console application, we're going to call this Fibonacci method, which calculates a Fibonacci sequence. In our main method, we start a stopwatch, and then we pass in the number 40 into our method. And then this method calculates the Fibonacci number, and it's recursive, so it's continuing to call itself until it gets to the number that it needs. Then it returns that result back to the main method. We stop our stopwatch and we'll print out to the console the result of the calculation and the amount of time it took in milliseconds. In step one, we're going to do some initial performance testing to see how this code performs, and then we'll use Copilot to see if we can improve it. I'm going to run this first, and we'll see the results. We get our Fibonacci number back, and it tells us that it took 508 milliseconds to complete that calculation.
Obviously, this is a very simple application. It doesn't take very long, but Copilot can help us improve that. And so I asked Copilot a simple query to analyze the performance of the Fibonacci function and identify any inefficiencies in time and space complexity. We can use optimizations like memoization and iterative approaches to improve the performance. I've got this new method that Copilot provided, and I'm going to compare it to the original method that we used. In this new one, we have a dictionary object called memo that we were defining up above in our main method. We're passing that into our new Fibonacci method. And while it's technically not a database, it is storing data for us. Once we do a calculation, we're going to store the results of that calculation in that dictionary object. And then we're going to check and see if that calculation has already been done. If it has, we're not going to go through the process of recalculating. We're just going to use what's in the memo. And that should save us substantial time because instead of having to do the calculation again, it's just going to pull from essentially the database and then use that item in the database. And then it continues to do its calculation, placing items in the memo, checking to see if it's there, and then moving forward. Then it returns the memo object back to the calling function, which we have here. So let me go ahead and uncomment this code. And the calling function passes in that memo and the number, the int that we're defining above. And then we reset our stopwatch first. Then we call the function. We stop the stopwatch and print the result to the console. I've got this new method that Copilot provided, and I'm going to compare it to the original method that we used. In this new one, we have a dictionary object called memo that we were defining up above in our main method. We're passing that into our new Fibonacci method. And while it's technically not a database, it is storing data for us. Once we do a calculation, we're going to store the results of that calculation in that dictionary object. And then we're going to check and see if that calculation has already been done. If it has, we're not going to go through the process of recalculating. We're just going to use what's in the memo. And that should save us substantial time because instead of having to do the calculation again, it's just going to pull from essentially the database and then use that item in the database. And then it continues to do its calculation, placing items in the memo, checking to see if it's there, and then moving forward. Then it returns the memo object back to the calling function, which we have here. So let me go ahead and uncomment this code. And the calling function passes in that memo and the number, the int that we're defining above. And then we reset our stopwatch first. Then we call the function. We stop the stopwatch and print the result to the console. Within every responsive and efficient backend system is a well-chosen algorithm tailored to the problem at hand. Dynamic programming and greedy algorithms each offer unique strengths that can have an outsized impact on performance, especially in applications where every millisecond counts. In this video, we'll explain the trade-offs between dynamic programming and greedy algorithms and how to decide between them in real-world backend systems. To begin, let's examine the differences and similarities between dynamic programming and greedy algorithms, starting with dynamic programming. Recall that dynamic programming is a technique for breaking complex problems into smaller, overlapping subproblems and storing results to improve efficiency and avoid redundant calculations. It's ideal for back-end tasks that call for repeated calculations, as it reuses data to save processing time and resources. However, dynamic programming typically involves additional upfront setup time because it requires creating a table or data structure, like an array or matrix, to store intermediate results. This upfront preparation ensures that previously solved subproblems can be reused, allowing dynamic programming to optimize performance, especially for problems with overlapping subproblems and optimal substructure. Now that we've explored dynamic programming, let's examine how greedy algorithms approach solving complex problems differently. By comparison, greedy algorithms solve complex problems by choosing the best immediate decision at each step. They make a series of choices, each of which seems best at the moment. In other words, at every step, the algorithm selects the option that offers the most immediate benefit or appears to be the optimal choice without considering the overall or future consequences.
While they're faster to set up and use less memory than dynamic programming, greedy algorithms don't always guarantee the best solution. This is because they make decisions step by step, choosing what seems best at the moment without thinking ahead. This can sometimes lead to the wrong results for more complex problems. However, greedy algorithms work well when each small best choice adds up to the overall best solution, like in tasks such as finding the shortest path in the network or compressing data efficiently. Their speed and simplicity make them useful when a quick or good enough solution is needed. Now that we understand the trade-offs between dynamic programming and greedy algorithms, let's explore some back-end scenarios where each approach is used, starting with dynamic programming scenarios. Dynamic programming is used in API request caching to break down repetitive requests into smaller subproblems. It stores the results of previously computed API responses, similar to memoization, and reuses those stored results to avoid redundant processing. This ensures that identical API requests are not made multiple times, reducing server load, speeding up responses, and improving overall application efficiency. For example, if an API provides data based on certain input parameters, dynamic programming-inspired caching techniques can store the response for a specific input in a cache. When the same input is requested again, the cached result is returned instead of making a new API call. Dynamic programming also helps with task scheduling by solving smaller parts of the problem and using those solutions to build the best overall schedule. It's especially useful when tasks have constraints like deadlines, dependencies, or priorities. For example, in a task scheduling problem where each task has a start time, end time, and a priority or associated value, sometimes called profit, dynamic programming can be used to maximize the total profit of scheduled tasks without overlapping. It works by sorting tasks in order, checking which tasks are compatible or don't overlap, and deciding whether to include a task based on how it impacts the total result. This ensures that the algorithm explores all possible options efficiently and avoids redundant calculation. Now let's explore some scenarios where using greedy algorithms is optimal. Due to their simplicity and speed, greedy algorithms are suited for dynamic, real-time environments like load balancing and routing, where conditions change rapidly. Greedy algorithms are often employed in these scenarios because they can make immediate, locally optimal decisions based on current conditions to help distribute workloads or route data efficiently. They are also used to quickly distribute workloads among servers or route packets through networks without intensive global computations. Greedy algorithms are also used for efficient file compression in back-end systems to save storage space or reduce transmission time, both crucial factors for back-end storage and data transmission. They balance simplicity, speed, and optimality to quickly create the best way to represent data using fewer bits. At each step, they combine the least used characters first, which saves space without needing to try every possible combination. Now that we've reviewed some scenarios where dynamic programming and greedy algorithms are used, let's explore the criteria to help you choose the right approach for a given situation. The first consideration to keep in mind when choosing between dynamic programming and greedy algorithms is the complexity of the problem you're working to solve. You should opt for dynamic programming if your problem can be broken down into subproblems that must be solved multiple times, or when decisions depend on multiple factors or previous choices. However, you should choose greedy algorithms when solving your problem involves making decisions that are independent of each other, and when these decisions don't need to be made in a specific order to derive an optimal solution. The choice between dynamic programming and greedy algorithms can also depend on your particular performance needs. Dynamic programming is ideal when solving problems with overlapping subproblems and optimal substructure, but it often requires more time and memory due to its recursive nature and storage of intermediate results. This is in contrast to greedy algorithms, which make locally optimal choices at each step. These algorithms can lead to faster execution and lower memory usage, though they don't always guarantee a globally optimal solution. When your performance priority is speed and reduced complexity, a greedy approach may be preferable. But if accuracy and guaranteed optimality are crucial, dynamic programming is the better choice. Memory constraints are another critical factor in selecting between dynamic programming and greedy algorithms. Dynamic programming often relies on memoization or tabulation, which can result in higher memory demands. This approach is best when memory constraints are not stringent, and the problem requires exploring all subproblem combinations to guarantee optimality. In contrast, greedy algorithms typically use constant memory, or memory proportional to the size of the input, so they have minimal memory requirements. You should choose this option when memory constraints are tight, and your problem can best be solved using a step-by-step approach. In this video, you learned about the trade-offs between dynamic programming and greedy algorithms, and how to decide between them in real-world back-end systems. Choosing between dynamic programming and greedy algorithms in back-end development is an important consideration that helps determine how systems respond, perform, and scale. In this screencast, we're going to learn to implement a greedy algorithm in a back-end system. You'll recall that greedy algorithms attempt to accomplish a goal without really looking ahead. They don't take an all things considered approach. They just look at whether they can accomplish the goal that they're given with the data that they have, and then they work to accomplish that goal. In this .NET console application, we've got a main method that is going to run when the application loads, and we're going to simulate distributing a limited set of resources among multiple servers in an optimal way. The greedy algorithm is going to be very fast at doing what we're asking it to do, even though it might not be fully optimized. The first thing we're going to do is write a greedy algorithm. I could use an LLM to create this, so I can give the LLM Copilot a scenario, and I might get code back something like this. So we have our list of resources. These are the resources that are available. And then we've got our servers, which can hold capacity. Think of 30 as holding a set of resources. It can hold 5, it can hold 10, and then we would add another 10 to that to create 30. These are the allocations that we can give to the servers, and these are the capacities that the servers have. We have a resources variable that's array list and a servers variable that's an array list. And now we're going to use our greedy algorithm to go through and assign those servers the resources that are available. Pass in our resources and our servers. And then the first thing we're going to do is sort our resources in a descending order. This will allow us to make sure that we have the resources from highest to smallest, and that's going to help our greedy algorithm as we attempt to fill those servers with that capacity. And then we're going to create an originals capacity variable, which is a new list of the servers that we've defined above. Our allocation is a blank dictionary that we're going to use to determine our allocation and fill our allocation items. And then we just iterate over the servers and create a new allocation for each item with a blank list array. We create our allocation for each item in a new list array, which is blank, and we'll fill it later. Then the greedy algorithm goes through all the resources, one for each, and then it also goes through all the servers, and it attempts to assign each resource to each of the servers in a way that's maximized for the data that it has. It's going to have the resources in descending order, and it's going to go through the servers in the order that we gave it. That's going to be 30, 20, 50. And it's just going to assign allocations as quickly as it can based on the resource that it is currently looking at and the capacity of the server. And then once that's done, we're going to route to the console each server and how much capacity it was given based on what the greedy algorithm attempted to show. So let's go ahead and run this, and we can see how this works. It went through each of the servers and each of the allocations. So you can see the server with the initial capacity of 30, which was first in line, got allocated resources of 25 and 5. That fills up 30. 25 plus 5 is 30. It had an initial capacity of 30. The greedy algorithm found 25 first because it was in descending order. We assorted it in descending order. And then the next available item it could give was 5 because the server only had a capacity of 30. So it found 25 first, gave it to that server, and then had to go through the rest of the list until it found an item where it could fill up the rest of the allocation. And then it does the same thing for the server with a capacity of 20. That was next in line 20, so it only got one allocation because that was the maximum allocation it could give. And then it used the last two for our allocation of 50.
Now notice here, there's only 35 items allocated to the server with a capacity of 50, so that has more capacity, but there were no items left in our resources list to give to that server. We just found out over was left and gave it to that server. So this is how the greedy algorithm works. This may not be the most optimal way to allocate resources, but it's trying to accomplish the goal of allocating resources to a server in the quickest way possible given the data that it has. And it does a pretty good job, right? But there might be a more optimal way to divide up these numbers that dynamic programming would provide. But the greedy algorithm does a good job. Let's see if there's a way that we can improve this algorithm. So I'm going to copy this program out and give it to Copilot and see what Copilot provides as a way to improve on this algorithm. I'm just going to open up Copilot. I'm going to ask if there's a way to make this greedy algorithm more efficient. Show me the improved code just to make sure that it understands what I'm asking. And then I'm going to paste in my program and we'll give it to Copilot and see what comes back. It tells me it can be improved in terms of efficiency by refining how servers are chosen for resource allocation. It says instead of iterating through all the servers to find a fit, using a priority queue or mini heap to keep track of the servers will improve the efficiency. So let's take a look at the code. It's still working on it. This is a little bit simpler. It's using this construct called a sorted set to add items to the server. This is that resource heap that it was talking about. And by using that sorted set construct rather than iterating through the entire list, it's claiming it's going to be a little bit more efficient. Let's copy this out and paste it into our application and see if it performs differently. I'm just going to paste that right in as we don't need those twice, so we'll remove those. And let's run this again. We should get the same result, but it's just doing it in a more efficient way. I'm going to keep the previous results up there and see what this provides. It did provide the same results. We've got the server initially 30, allocated resources 25 and 5, same for 20 and the same for 50. It used the same process. It's still a greedy algorithm, but using this sorted set made that greedy algorithm more efficient. That's how you can use an LLM like Copilot to take code that actually works, but Copilot helped us make it more efficient and more performant by using just a different construction rather than the one that we were previously using. As you get more data, you would see performance improvements, and you can track whether the first way you were doing it or the second way was more performant by using a timer and checking and using debugging tools to make sure that all of this improvement works. Many times you don't want to just take what's given to you from the LLM. You want to make sure that it actually does the job that you want it to do. But that's one way that LLM like Copilot can improve our code. Mastering advanced algorithms is essential for optimizing back-end systems and solving complex problems efficiently. A deep understanding of techniques like dynamic programming, hashing, and algorithmic trade-offs enable developers to build scalable and high-performing applications. We began by exploring dynamic programming and greedy algorithms, two essential techniques for solving optimization problems efficiently. Using real-world scenarios, we explored how each method approached problem solving, when to apply them, and how their decision-making strategies differed. Next, we applied dynamic programming algorithms, breaking complex problems into smaller, overlapping subproblems for more efficient solutions. Through hands-on coding exercises, we strengthen our understanding of key techniques like memoization and tabulation. Then we explored hashing and hash tables, investigating how they improve search efficiency in back-end systems. We discovered how they accelerated data retrieval and enhanced overall system performance by analyzing their structure in real-world applications. After that, we undertook a performance optimization capstone project, leveraging advanced algorithms and AI-powered tools like Copilot to enhance back-end efficiency. This practical experience sharpened our problem-solving abilities and prepared us for real-world challenges. Finally, we evaluated different algorithmic approaches in back-end development, weighing their strengths and limitations. By examining factors like efficiency,
scalability, and resource usage, we honed our ability to select the most effective solutions for various challenges. Mastering advanced algorithms is crucial for building efficient and scalable backend systems. By applying these techniques, developers can optimize performance, improve data processing, and make informed architectural decisions. The skills gained in this module will be invaluable for tackling real-world challenges and designing high-performing applications. Welcome to Algorithmic Optimization and Advanced Problem Solving. In this module, you'll explore how Microsoft Copilot can enhance algorithm development, implement complex solutions, and optimize performance in a .NET Core application. First, we'll explore how Microsoft Copilot enhances algorithm development, streamlining the writing process, and optimizing data structures in .NET Core. Next, we'll dive into implementing complex algorithms like Dijkstra's shortest path and A-star search using Copilot to simplify and accelerate the coding process for backend applications. Then we'll analyze Copilot-generated code, evaluating its performance and identifying opportunities to optimize time and space complexity, ensuring efficient and scalable solutions. After that, we will refine and enhance existing data structures and algorithms, leveraging Copilot to improve efficiency and adapt them for real-world backend applications. By the end of this module, you'll be equipped to analyze, refine, and improve data structures and algorithms, building efficient and scalable backend systems. Having an assistant that can help you build, refine, and optimize code is a game changer. Large language models, or LLMs, like Copilot, are transforming backend development by automating essential tasks like code creation, refactoring, and optimization. This means developers can focus on building high-quality, scalable systems faster than ever. In this video, we'll explain how Copilot assists in code generation, refactoring, and optimization for backend systems. Let's start by defining what LLMs are and explain how they contribute to more efficient backend development. Large language models are advanced AI systems trained on vast text and code datasets. They understand and generate language, assist in tasks like writing, analysis, and programming. Microsoft's Copilot is an LLM that can assist users by generating code, providing real-time suggestions, and automating repetitive programming tasks. Copilot can analyze the context of written code and predict the next lines, improving efficiency and reducing development time. Now let's examine some of the key features of the Copilot LLM and what makes it so helpful to modern backend development. One important way Copilot can assist developers is through code generation, enabling the quick creation of essential structures. By describing the desired functionality, developers can prompt Copilot to produce basic code frameworks, saving time during the setup phase and allowing them to concentrate on refining and expanding their projects. For example, Copilot can generate foundational code for common development tasks, such as setting up a database schema or implementing an initial algorithm. This speeds up foundational work and simplifies the starting process. After generating code, the next step is refactoring it. Copilot makes this process more efficient by identifying areas with unnecessary complexity and outdated syntax, and it can suggest simplified, cleaner alternatives to use. For example, if you have a function that calculates a user's total shopping cart cost, but uses repetitive calculations, Copilot can suggest removing redundancy or simplifying loops to make the code easier to understand. Alongside refactoring, Copilot can also assist with optimization, which focuses on improving code speed and efficiency. Optimization makes code faster and less memory intensive. Copilot can suggest changes that enhance performance, which is especially useful for backend systems handling large amounts of data. For example, if your sorting function slows down as data grows, you could prompt Copilot with, "Optimize this sorting function for better performance." Copilot might suggest a faster sorting algorithm or ways to use less memory, making it more efficient. After improving the code through refactoring and optimization,
The next step is to assess its efficiency through time and space complexity analysis. Copilot can assess how code performs with large datasets by analyzing its time and space complexity, helping developers ensure their algorithms meet performance standards. For example, asking Copilot to evaluate a search function might return feedback like, "This function has order of n squared time complexity, which is inefficient for larger datasets. Consider optimizing it to order of n log n." This feedback allows developers to make informed adjustments and improve performance. In this video, you learned how Copilot can help with code generation, refactoring, and optimization for backend systems. As these tools evolve, they're reshaping what's possible, enabling developers to deliver high-quality solutions that scale effortlessly to meet demand. When attempting to implement data structures, it can be difficult to know how to get started. So we can use an LLM like Microsoft Copilot to help us get going. In this screencast, we're going to demonstrate how to prompt the LLM to generate and improve code snippets for data structures. I have a simple console application here. We're working with C# as the language. I don't have any code in it yet, so I'm going to use Copilot to help me implement a simple stack implementation. I'm going to open up Copilot on the web, and I'm going to give it a simple prompt. I'm telling it what language I'm working in. I'm telling it that it's a console application and I'm working in VS Code. Sometimes those details will be important, so it gives you the right code for the right environment you're in. And then I'm asking it to provide the stack class, the main method, and some test data so I can test the implementation. Send this prompt to Copilot. It tells me it's going to give me a stack class and a main method with test data so that I can test the class. It has our push, pop, peek, and an isEmpty method call that we can make. And then it gives us some test data that we can work with so that we can implement our stack. I'll just copy the whole code out of Copilot and get into my program. I've pasted this in and I can tell that there's no issues because I don't get any warnings in VS Code that anything's wrong. But it looks like it'll run fine. First of all, we're going to push these items onto the stack. And then we're going to pop some items off and write out to the console what we're doing. And then we're going to do another test here. We're going to add more elements to test overflow. So it's going to push more items onto the stack. And then it will write out that the program is finished. So let's go ahead and run this. It pushed elements onto the stack. It peaked 30 because that was the last item in the first batch of items that we put into the stack. Then it popped elements from the stack, starting with 30 and then down to 20. If the stack is empty, returned false. And then we went ahead and pushed more elements onto the stack to test overflow. And then it told us that the program is finished. So it's a very simple implementation of a stack. Let's go back to Copilot and ask it to optimize the stack to see if we can get better performance out of it. Because it has context, I don't need to tell it what code to work with. I just say this, and it knows based on the context that it already has that it's referring to this code that it just provided. We'll go ahead and submit that prompt. It gives us an optimized version of the stack with some improvements. It has dynamic resizing. It reduced memory overhead by utilizing array.resize, and it simplified the logic a little bit to make the code easier to read. Now we have our optimized stack implementation. It's also giving me a new version of the main method to test the dynamic resizing. We can just copy this entire thing out. In many cases, when you're working with a tool like Copilot, you may not want to copy out all the code. You may want to just copy the code that has been updated or improved. In this case, because it's a demo, we're just going to copy and paste everything back in. And so we can try some of these new test cases that it's given us. Now that we have this new implementation, let's go ahead and run this. I'm going to clear the console. So it pushed elements onto the stack again, did peak at 30, same as it did in the first implementation. Then it popped elements from the stack, 30 and 20, checked if the stack was empty, and then we can press the key to finish. We can actually improve these test cases if we wanted to ensure that these test overflow worked by providing more console messages. But this is a very basic implementation. And we use Copilot not only to create the first version, but then to even improve the version that it gave us the first time. We can take individual methods. For example, this push method, we can ask it to improve just the push method or the pop method if we wanted to. Add some more methods for deeper testing and for more optimization. You can continue to work with the LLM. Now that it has context, you can continue to converse with it, and it will continue to help you improve your code. Every responsive application relies on an optimized data flow, ensuring users get what they need as quickly and efficiently as possible. By using algorithms like Dijkstra's and A-star search, you can design backend systems that deliver high performance and scalability. In this video, we'll describe the mechanics and applications of Dijkstra's short path algorithm and A-star search for backend systems. Let's begin by defining these algorithms and exploring when to use them in backend systems, starting with Dijkstra's algorithm. Dijkstra's algorithm calculates the shortest path in a network where connections have specific costs, such as time or distance. It operates on a weighted graph, a network where points called nodes are connected by paths or edges, each with a cost that represents time, distance, or another factor. A node is any device that is connected to the network, such as a laptop, mobile device, or network router. An algorithm finds the most efficient route by starting at one node, selecting the connected node with the smallest known cost, updating nearby nodes, and repeating this process until it has explored all possible paths. Dijkstra's algorithm is widely used in complex networks with numerous interconnected nodes, such as navigation systems, network routing protocols, and mapping applications, where efficient and accurate path finding is essential. Calculating the shortest routes between nodes, Dijkstra's algorithm ensures data flows optimally between servers, minimizing delays and enhancing the user experience with faster response times. Now that we've explored Dijkstra's algorithm, let's examine the A-star search algorithm, which is written as the letter A with an asterisk. An A-star search algorithm identifies the shortest path while using a heuristic, an estimated best route, to guide the search process. It improves upon Dijkstra's algorithm by incorporating this heuristic function. The heuristic acts as an informed estimate of the remaining distance to the destination, enabling the algorithm to prioritize promising paths. These paths are more likely to reach the goal quickly while reducing unnecessary computations. An A-star search algorithm is ideal for scenarios where real-time performance is important, or your tasks are time-sensitive, such as GPS navigation, video game AI for pathfinding, and robotics. By incorporating a heuristic to prioritize the most promising paths, A-star search algorithms enable applications to efficiently handle high-priority API requests, ensuring users receive critical information as fast as possible with minimum delay. In this video, you learned about the mechanics and applications of Dijkstra's shortest path algorithm and A-star search for backend systems. Dijkstra's and A-star search are more than algorithms. They're essential tools for building faster, more efficient systems. Writing even a simple version of an algorithm like Dijkstra's algorithm, shortest path algorithm, can be complicated and time-consuming. But using a tool like Microsoft Copilot can help speed up at least the initial draft of that algorithm so you can get past that blank page problem and get to work. In this screencast, we're going to demonstrate how to generate and refine Dijkstra's algorithm using Microsoft Copilot. I've got an empty console application here. We're going to be working in C#. We've got our program.cs file open and ready to go. I'm going to open Copilot and prompt it to give me a version of Dijkstra's algorithm along with some test code. We'll open up Copilot and I'll put that prompt in. So I'm asking it to generate the algorithm. I'm giving it the language I need, what type of application I'm working with, and the tool that I'm working with, just so it has some context and knows what type of environment I'm working in. I'm asking it also to provide the main method and then some test data so I can verify the implementation. Let's go ahead and give that prompt to Copilot. It's generating that code and it's giving us the program with the main method, and then it's giving us other options here, the static dictionary, distances and previous, and then it's got print path method that it's providing. It looks like something may be missing here, but let's go ahead and copy this out. We'll paste that into our application and see if we get any errors. All right, so we pasted that in, and it looks like everything's actually okay. I'm not getting any compiler errors. So this should provide us with a basic Dijkstra's algorithm. We're not going to go through the details of the algorithm in this screencast, but we're going to trust that Copilot understands what Dijkstra's algorithm is and gave us the basic structure for that algorithm. And just from a glance here, it looks like it's doing what it needs to do based on previous work with Dijkstra's algorithm. To verify that this is exactly what you want, but we can give it a first try and see how it works. I'm going to go ahead and open up a terminal window and we can run this. So it's doing the shortest distance from 0 to 3. There's 4 steps, and then it provides the path it took, 0, 2, 1, 3. The test data that we're passing in is this list data here with all of our edges that we're going to provide for the algorithm to work with. We're putting that in a dictionary. We tell it that the source is 0 and the destination is 3, and then we run the algorithm. So we've got our Dijkstra's, we get the graph, which is this object here, the dictionary object, and the source is 0. And then we set the bar as distances in previous equal to the Dijkstra's result, the result of that calculation. Here's the function, the method that we're working with. We pass in this data here, and then this is the output data that we're working with. It looked like it did everything that we wanted it to do, and it did it well. We get that initial implementation. Now, based on our goal for application, we may want to modify this or change it in some way so that we can work with different types of data. But for the most part, this basic structure is in place. And now it gives us some meaty code that we can go in and start working with. Now let's suppose we want to try to improve the performance of this algorithm. Now that Copilot has the context for our class, all we have to do is work with Copilot in this context. We don't have to paste in the code or re-describe what we're trying to do. We can just ask it to improve this code, and it will know that this C# implementation refers to the implementation that it just gave us. I'm going to go ahead and just give it the simple prompt, suggest performance improvements. So it suggests, first of all, to use a mini heap, a priority queue instead of a sorted set, which is what it gave us initially. That could be a way to improve performance, avoid repeated removals in the priority queue, use a hash set, optimize edge relaxation, and some other items here. It provides us with the revised code, the entire code that we may want to work with here. So I'm going to copy this out and paste that right into my code block. Now, in many instances, I wouldn't replace the whole thing, but it's providing all that we need. It gave us our main method, it gave us our Dijkstra's method, and then our print path method. So everything is still in place. It just improved the way that the code was designed in all the ways that it describes in this list. What did it say? It made 6 improvements. You can actually do testing before and after just to see if actually the improvement happened. We're not going to do that in this case, but that's certainly possible to see if you can see any differences in how the app performs. So let's go ahead and run this one now. It gave us the same inputs that we're going from 0 to 3. It took 4 steps, and the path is 0, 2, 1, 3 again. It just did it in a different way, and it's using better code to do that. Our priority queue here is using NQ and DQ rather than the previous method to add items to the stack. In these cases, this just gives us the basic fundamentals that we'll want to work with, and then we can continue to work with Copilot to improve this and make it better for our purposes.
Efficient algorithms are crucial for building applications that can grow and handle increasing demand. However, inefficiencies in code can remain hidden until they cause slowdowns or scaling problems. By learning how to measure time and space complexity, you can proactively prevent performance bottlenecks and ensure your applications remain fast and reliable. In this video, we will explain how to measure the time and space complexity of LLM-generated algorithms. Recall that time complexity measures how an algorithm's execution time scales, and space complexity tracks the memory an algorithm requires relative to the size of its input. Each of these complexities can be measured using Big O notation, which helps you determine how to store and search for data. Using these two metrics, time and space complexity, Let's explore these concepts further, starting with how to find performance gaps in algorithms that have been generated by an LLM. Performance gaps are sections of code that consume more resources than necessary. To find performance gaps, start by evaluating areas that take more time or memory than expected, such as nested loops or recursive calls. For instance, when nested loops are involved, even small increases in input size lead to a slowdown. Now that we've explored how to identify performance gaps, let's examine refinement steps to optimize an algorithm and reduce time and memory use. First, label parts of the algorithm with their complexity, such as order of n or order of n squared. For instance, identifying a nested loop as having a time complexity of order of n squared helps you pinpoint where the scalability problems originate. Next, use large language models, or LLMs, like Copilot to get suggestions for your code. Improving an algorithm's efficiency can be challenging, but an LLM can help by suggesting improvements. For example, asking an LLM how to reduce time complexity might lead to replacing a nested loop with a hash table, bringing the complexity down from order of n squared to order of n. This refinement makes the algorithm more efficient for larger datasets. Finally, test and validate the refined algorithm to confirm it's improved. Compare the original and optimized versions to check if they use less time and memory, especially with larger datasets. For instance, after replacing a nested loop with a hash table, you should realize a noticeable increase in efficiency as the dataset grows. Let's apply these steps by working through an example. Imagine a web application has an algorithm to manage a list of user records. Initially it worked well, but as more users joined and data grew, nested loops in the algorithm slowed it down and increased memory use. This is a common issue where inefficiencies cause the algorithm to lag and use more memory with each added record. Developers used an LLM tool to identify which code was causing the slowdown and used its suggested fix to improve performance. In this video, you learned how to measure the time and space complexity of LLM-generated algorithms. Understanding time and space complexity separates code that works from code that scales. By measuring and optimizing algorithm performance, you can build applications that adapt to growing data and deliver consistent, reliable results. You can use AI tools like Microsoft Copilot to help you write code, but you can also use it to help you comment code and even annotate it if you want to be able to better understand how it's working. In this screencast, we're going to demonstrate how to analyze and annotate the time and space complexity of LLM-generated code. I've got Copilot up here. I'm going to ask it to generate a bubble sort algorithm for me in C#. It's just a simple bubble sort. And I'll give it a very simple prompt to help us do that. Tell it the language I wanted in and what I wanted. And so it comes back with a very simple bubble sort, a very standard bubble sort. And notice it also gave me the main method that I could use so that I could run and test this. And I can put this into VS Code in a simple console application to test this, which we'll do later. It provided the algorithm that I asked for. Now I want to annotate this function. Let's suppose I want to understand how this function works in terms of time and space complexity. I can ask Copilot to do that for me so I can understand what the algorithm is doing for both of those. So I'm going to ask it to annotate this function with time and space complexity using big O notation. It provides that immediately right back for me. It's a time complexity of order of n squared because these do take more time to run because of the way that they operate. They have to loop multiple times through the entire array to get the right items to the top. But in terms of space complexity, it's an order of 1 because it doesn't have to create duplicates of the array as it's sorting. It's better on space complexity, more time consuming on time complexity. And it's annotated that just in a comment. It's just put a code comment in there for me. Now, when I come back to this, and if I want to compare with other algorithms, I can certainly do that as it's now written in the code for me. Now I'm going to ask it to give me another algorithm. I'll just ask it to replace the bubble sort with a merge sort algorithm because that's going to be a little bit better on time complexity. So let's go ahead and ask it to create that for us. And just like the bubble sort, it gave me the main method, and it also created a basic merge sort algorithm. We've seen this in previous lessons. And this just looks like a very standard merge sort algorithm. Let's ask it to annotate this one too.
And then we can compare the two in terms of time and space complexity. There's the comment. Time complexity is order of n log n, and the space complexity is order of n. It tells us what this means. Best, average, and worst case is n log n due to the divide and conquer approach. It will have an impact on time complexity, but it can actually operate a lot more quickly than bubble sort. And it has an order of n in space complexity because it does require additional space for those temporary arrays that it's creating in the sorting algorithm. It's making copies of those arrays so that it can determine the midpoint and then go ahead and tear the array apart so that it can find the right sort order. It gives us that time and space complexity right in the code again. And if we were to paste this into our application, we would have those for comparison based on our needs. And you can think of having a library of algorithms that you would use based on the context. So now we've got a little bit of a different algorithm. Now we can test both of these. I've got Visual Studio Code up here with both a bubble sort and a merge sort that I had asked Copilot for previously. But I put these all into Visual Studio Code, made sure they run. But now we can test this and see which one is faster. This is going to go through an array of 1,000 items. And I'm setting a stopwatch before and stopping it after each of the algorithm is run and checking the milliseconds on the timing on these. So let's see what both of these do for an array of 1,000 items. Go ahead and run this. The bubble sort took 1 millisecond and the merge sort time took 0 milliseconds. It obviously took some time, but it was so fast it didn't even register. Let's add now 10,000 items to this array. I'm going to clear the screen, and then we'll run this again. Now the bubble sort took 148 milliseconds, and the merge sort just took 1 millisecond for the same amount of items. If we add one more 0 and make this 100,000, we'll see a more dramatic difference between the two. It will take some time for that bubble sort to run. It took 148 milliseconds for that bubble sort to run with 10,000 items, and we're multiplying that by 10 now. It's going to take probably 10x as long. But what this is illustrating is that you can have these two different algorithms that Copilot has provided. You can test the difference between them. You can use them in different contexts. If you have Copilot help you annotate the algorithms for you, you can get a quick glance and a quick sense of which is going to be faster and take up less space by just looking at the code comments. So that's a way that you can use LLMs to help you analyze and annotate the time and space complexity of code that it generates. Imagine if you could refine your code without painstakingly analyzing it every time. Using a large language model, or LLM, like the one utilized in Copilot, you can find inefficiencies and receive suggestions for optimizing your data structures and algorithms. In this video, we'll explain how to use Copilot to refactor and enhance data structures and algorithms. To begin, let's review the steps for using Copilot to refine your code. The first step in improving code performance is identifying the areas causing delays, known as bottlenecks. A bottleneck is any part of your code that unnecessarily consumes time or resources. Common examples include loops performing redundant work or data structures unsuitable for the tasks. Recognizing these inefficiencies allows Copilot to focus on specific areas for improvement. For example, imagine a recommendation engine that loops through every item in a database to check its relevance. If most items don't need processing, this loop becomes a bottleneck. Identifying this inefficiency highlights where you can prompt Copilot for optimization advice. Once you've identified a bottleneck, you can prompt Copilot to help refine your code. Clear and specific instructions about the issue enable Copilot to provide actionable recommendations. For instance, if a search function performs poorly on large datasets, you might ask Copilot, how can I improve the speed of this search function for large datasets? Copilot might suggest using a binary search, which is faster for sorted data and directly addresses the problem. After receiving Copilot suggestions, it's important to evaluate which ones will benefit your code the most. Focus on the ideas that improve both efficiency and readability without introducing unnecessary complexity. If Copilot suggests using a hash map instead of a list to speed up searches,
Consider whether your data and use case aligns with this approach. This process ensures that the suggestions fit your specific needs before making changes. Now that you have Copilot's recommendations, the next step is to decide how to refactor your code with Copilot's suggestions. Refactoring involves restructuring your code to make it more efficient while maintaining its original functionality. For instance, if Copilot suggests switching from a linear search to binary search, you'll need to adjust your code to work with sorted data. Apply each suggestion one step at a time, testing as you go to ensure the changes work as intended. Once the refactoring is complete, it's important to verify whether these changes actually improve performance. That's where testing comes in. Testing and validating your code allows you to confirm the effectiveness of the refactored code. Measure key metrics such as speed or memory usage, and compare them to the original implementation. This final step ensures the changes deliver real-world benefits. For example, suppose you implemented a binary search as suggested. Compare it against a large dataset and measure how quickly it finds specific items compared to the original method. This validation step ensures your changes achieve the intended improvement. In this video, you learned how Copilot can be used to help refactor and enhance data structures and algorithms. Continuous improvement with Copilot helps you create efficient, scalable applications that perform well in the real-world scenarios. Refined complex code structures can significantly enhance their performance and efficiency. With the assistance of an LLM like Copilot, you can make a few targeted adjustments to transform functional programs into optimized, high-performance tools. In this video, we'll demonstrate how to optimize a priority queue implementation with Copilot's assistance. Before we explore how to optimize a priority queue, let's first define what it is and why it's useful in back-end development. A priority queue is a data structure that processes items based on their priority, ensuring high-priority items are handled first. This is particularly useful in scenarios that require prioritization, such as task scheduling. For example, a hospital scheduling system might use a priority queue to ensure urgent cases are addressed before routine ones. Now that we know what a priority queue is, let's select the code base and start exploring the steps for Copilot-assisted refactoring. To begin selecting the code base, open a basic priority queue implementation in Visual Studio Code. Choose a working implementation that handles priorities correctly but may become inefficient when managing large datasets. This will give us a good starting point for applying optimizations. Next, once the code base is loaded, let's ask the Copilot LLM for optimization recommendations. Using a simple prompt like, "Optimize this priority queue for speed and memory efficiency," Copilot can analyze the code and provide suggestions. These might include replacing data structures or improving methods. For example, switching from a list to a binary heap might be recommended. A binary heap is a complete binary tree that maintains a specific order, ensuring efficient priority-based operations in structures like priority queues. It allows quick insertion and removal of the highest priority elements, making it a common choice for implementing priority queues. Switching to a binary heap reduces the time complexity of insertion, which adds an element while maintaining priority order, and deletion. This removes the highest priority element. It also makes the priority queue faster and more efficient for large datasets. After generating the optimization suggestion to use a binary heap, the next step is to apply these changes to your code base by carefully integrating it into your existing priority queue logic. As you make each modification, regularly test the implementation to confirm it's performing correctly and efficiently. Including clear comments throughout your code will help others easily follow your logic and understand the reasons behind each adjustment. To implement this change, select a suitable binary heap class, such as binary heap queue, or another dedicated priority queue class provided by an external library. Then adjust your existing code to initialize and manage priorities using the binary heap. Because a binary heap automatically maintains the order of items based on priority, insertion and deletion operations become significantly faster, improving overall performance and saving resources. Finally, after you have implemented the suggested changes, test and document to verify the queue is functioning as expected. Check if it handles priorities correctly and if its performance has improved when processing large datasets. Use comments to document the changes you made and the improvements they bring to your priority queue. For example, // switch to a binary heap for faster insertion and deletion operations. This documentation helps other developers understand the purpose of each change and makes your code easier to maintain and improve. In this video, you learned how to optimize a priority queue implementation with the assistance of Copilot. Starting with a basic implementation, we use Copilot's suggestions to identify and apply changes that improve the structure's efficiency. This illustrates how optimizing even a single data structure can be done with the help of an LLM like Copilot to enhance the performance of real-world applications. Congratulations on completing the Data Structures and Algorithms course. Mastering these concepts is essential for building efficient, scalable back-end systems. The ability to optimize performance, implement advanced algorithms, and leverage AI-powered tools like Microsoft Copilot will help you tackle real-world development challenges with confidence. We began by exploring core data structures such as arrays, linked lists, stacks, and queues, focusing on their functionality, operations, and efficiency. Then we evaluated their performance trade-offs in practical applications in back-end development. Next, we examined sorting and searching algorithms, applying quicksort and binary search techniques to enhance data processing efficiency. We assessed their strengths and limitations, identifying the most effective strategies for optimizing search performance in back-end systems. Then you analyzed tree and graph structures, exploring how they facilitate data organization and processing. You applied traversal and search algorithms, measuring their effectiveness in enhancing back-end system scalability and performance. After that, you explored advanced algorithmic methods, such as dynamic programming and greedy approaches, to tackle complex back-end challenges. You implemented hashing techniques to enhance data retrieval efficiency and assessed various strategies for optimizing system performance. Finally, you enhanced your skills in optimizing algorithms and data structures with Microsoft Copilot, utilizing AI-generated insights to boost efficiency. You worked with complex algorithms, evaluated Copilot-assisted code, and applied strategic optimizations to improve scalability and back-end performance. You now have the skills to design efficient data structures, optimize algorithms, and enhance performance in back-end systems. With your ability to implement advanced techniques and leverage Microsoft Copilot, you're ready to tackle complex development challenges and build scalable applications. Congratulations on completing the Data Structures and Algorithms course.